Welcome to The Midnight Scientists. Before we begin our journey tonight, I invite you to settle into the space around you. Adjust your posture. Let your shoulders drop away from your ears. If you are in a city apartment, listen for a moment to the distant, muffled hum of the world outside, the low frequency of life continuing elsewhere. If you are in a quiet village, notice the profound weight of the silence, the way it seems to press gently against the windows. Imagine for a moment the thousands of kilometers that might separate you from the next person hearing these words. Somewhere, across an ocean or a continent, another mind is drifting just as yours is. There is a vastness between you, a distance made of mountains, rivers, and the curvature of the earth itself. And yet, in this moment, you are sharing a structure. You are held together by the same sequence of thoughts, the same rhythm of breath. Tonight, we are going to explore the edges of that connection. We are going to look at the very fabric of distance and ask if it is as solid as it seems. Visualize, if you will, a void. Not a frightening void, but a calm, velvet black expanse. It is a place of absolute stillness, far removed from the clutter of the everyday world. In the center of this stillness, two tiny points of light appear. They are born from a single event, perhaps a high-energy photon striking a crystal or a delicate atomic decay. These are our particles. They are twins, born of the same mathematical womb. In the language of the laboratory, they are a system. But for us tonight, they are simply two travelers. As they emerge into the world, they begin to drift apart. Imagine them moving slowly, with a grace that only the microscopic world possesses. One moves to the left, towards the distant horizon of your mind. The other moves to the right. They do not look back. There are no tethers between them, no invisible silver threads, no radio waves, no whispers. They are, to all classical appearances, entirely separate entities. 1 kilometer passes, then 10, then 1,000. Now imagine an observer. Let us call her Alice. She sits in a quiet laboratory watching the traveler that moved to the left. She decides to ask it a question. In the quantum world, asking a question is called a measurement. She wants to know which way the particle is spinning. In her mind, she expects the particle to have its own identity, its own real state. She assumes that whatever the particle is doing, it is doing it independently of its twin, which is now thousands of miles away. But as Alice performs her measurement, something happens that defies every intuition we have about the world. The moment she finds her particle is spinning up, its twin, vastly distant and untouched, instantly assumes the opposite state. It spins down. There is no delay. There is no time for a signal to race across the gap. If Alice had a friend, Bob, watching the second particle on the other side of the planet, he would see the result the very microsecond she made her choice. Imagine the implications of this. It is as if two coins, flipped in different cities, always landed on opposite sides, even though nothing linked them. It is as if two hearts, separated by a lifetime of distance, beat in a perfect, synchronized counterpoint. This is the phenomenon that Erwin Schrödinger, in the quiet of the 1930s, gave a name that would haunt physics forever. He called it Verschränkung. In English, we know it as entanglement. Schrödinger did not see this as a mere detail. He believed it was the characteristic trait of quantum mechanics, the thing that forced us to say goodbye to the world of separate, lonely objects. Visualize the great Albert Einstein, a man who loved the order of the cosmos, sitting in his study. He is troubled. He looks at the mathematics and sees this immediate connection across space. He calls it spukhafte Fernwirkung, spooky action at a distance. To Einstein, the world was a collection of separate parts. A chair is a chair, A moon is a moon. Each has its own properties, influenced only by what touches it. This is the principle of locality. It is the comfort of knowing that what happens there cannot change what is happening here unless something, a light beam, a force, a physical push, travels the distance between them. But the travelers we are watching tonight do not seem to care for Einstein's comfort. They suggest a universe that is more like a single, seamless tapestry. If you pull a thread on one side, the pattern shifts on the other, regardless of how wide the tapestry may be. Drift with me now away from the laboratory and back into the history of how we came to think this way. Before we can understand the spookiness of entanglement, we must understand the world we thought we lived in, the world of Isaac Newton, of solid cannonballs and predictable planets, a world where everything was in its place and every place was its own. In that world, distance was a wall. In the quantum world, distance might just be an illusion. As we move forward, we will ask, if nothing travels between the particles, how do they know? Is there a secret code written in their hearts, or is the space between them not really space at all? Consider this as you drift. If two things are created together, can they ever truly be apart? As you continue to drift, let the velvet blackness of the quantum void fade for a moment. Instead, I invite you to visualize a grand, ancient library. The air here is cool and carries the faint, comforting scent of old paper and polished oak. Outside the tall, arched windows, the stars move in slow, majestic circles, precisely where the charts say they should be. This is the home of classical physics. For centuries, this was the architecture of the human mind. It was a world of separability, a beautiful and orderly island where every object had its own name, its own place, and its own life, entirely independent of the things around it. Imagine a single silver coin resting on a mahogany table. It has a weight you can feel, a diameter you can measure, and a position you can define with absolute certainty. If you were to take another coin and place it in a drawer in the next room, common sense tells you that the two coins have nothing to do with one another. What happens to the coin on the table, a scratch, a polish, a flip, cannot possibly change the coin in the drawer. They are separate systems. They possess what Einstein called their own real states. This was the great promise of Isaac Newton. Visualize Newton in the late 17th century, watching the world with a quiet, mathematical intensity. To him, the universe was a vast, intricate clockwork. Planets orbited the sun not because of mysterious telepathic bonds, but because of forces that could be calculated with the precision of a master watchmaker. In Newton's world, if a cannonball curved through the air, it was because of the push of gunpowder and the pull of the earth. If the moon stayed in its path, it was because gravity reached across the distance. But even gravity, as vast as it was, respected the individuality of things. The earth remained the earth, the sun remained the sun. They were separate bodies, interacting through forces, but never losing themselves in one another. This separability is the bedrock of our intuition. It is the reason you feel safe knowing that your house stays where you left it, even when you are miles away. It is the reason we believe that the moon exists even when no one is looking at it. It is the philosophy of the sum of parts.
The belief that if you understand every individual piece of a machine, you understand the whole machine. There are no ghosts in the gears, no hidden connections that defy the boundaries of space and time. But as the centuries turned, the library of classical reason grew even more sophisticated. Drift forward now to the 19th century. Imagine the world beginning to hum with a new kind of energy. You see James Clerk Maxwell standing amidst a forest of copper wires and magnetic coils. He is uncovering the secret language of light itself. Maxwell showed us that the space between things is not empty. It is filled with fields, invisible, continuous oceans of electricity and magnetism. When you move a magnet, you create a ripple in this field. That ripple travels outward like a wave on a pond until it touches something else. This was the birth of true locality. It meant that for one thing to affect another, a signal had to travel. Information had to move through the field, crossing the centimeters or the light years at a finite pace. And then, in 1905, Albert Einstein added the final heavy lock to the door of this classical world. Visualize a beam of light racing across the dark. Einstein realized that this beam is the fastest messenger in the universe. It moves at approximately 300,000 kilometers every second. To our human minds, this is instantaneous, but to the universe, it is a strict speed limit. Imagine two events occurring at opposite ends of a galaxy. If light cannot travel between them in time, Einstein told us, then those two events can have no causal link. They are space-like separated. They are truly, fundamentally alone. This is the heart of relativity. The geometry of space and time ensures that the here and the now are protected from the there and the then by the absolute barrier of light's velocity. In this world, everything is tidy, everything is local, everything is separate. It is a comfortable way to live. It aligns with the way we touch the world, the way we build our cities, and the way we understand our own bodies. We are islands of matter, interacting through the messengers of light and force, but always anchored in our own coordinates. But as we sit in this grand library of classical reason, notice a small tremor in the floorboards. A tiny, microscopic crack is beginning to form in the foundation. For all its beauty, this classical world began to fail when we looked too closely at the very small. We found that nature, at its deepest level, does not speak the language of billiard balls and clockwork. It speaks the language of waves that cannot be unpicked, of states that refuse to be divided. The island of reason is about to be flooded by a stranger, deeper ocean. We are moving toward a place where the sum of the parts is no longer enough, where two travelers can drift light years apart and yet remain, in a way that haunts our logic, the same thing. Before we leave this library, consider the comfort of the wall and the distance. Enjoy the certainty of the here and the there, because in the next chapter, we are going to watch the walls dissolve. We are going to ask, what happens to our reality when the speed limit of light is respected, but the particles don't seem to need a signal at all?
Close your eyes for a moment and return to that grand library of reason we visited before. Feel the weight of the oak tables and the stillness of the air. Everything here is accounted for. Everything has its place. But now, I want you to notice a small, persistent flickering at the edge of your vision. Imagine a small piece of iron resting in a dark furnace. As the furnace heats, the iron begins to glow. First, a dull, deep red, then a vibrant orange, finally, a brilliant, blinding white. To the scientists in the library at the end of the 19th century, this glow was a problem, a small, nagging wrinkle in their perfect tapestry. According to the old laws, the energy pouring out of that hot iron should have grown infinitely stronger as the frequency increased. It should have drifted into the ultraviolet, releasing a torrent of energy that nature simply didn't provide. They called it the ultraviolet catastrophe. It was a sign that the clockwork universe was starting to stutter. In the year 1000, a man named Max Planck stepped toward the furnace. Imagine him, a quiet, meticulous thinker, staring into the heat. To solve the riddle, he proposed something that he initially thought was merely a mathematical trick, a clever way to make the numbers behave. He suggested that energy does not flow like a continuous, smooth river. Instead, it moves in tiny, indivisible packets. He called them quanta. Visualize a staircase. In the classical world, you could stand anywhere on a ramp, at any height you chose. But Planck's world was a set of stairs. You could stand on the first step or the second, but never in the empty space between them. Nature, it seemed, was granular. It had a minimum size. He discovered a number, a proportionality constant we now call Planck's constant, denoted by the letter h. It is a number so small that it escapes our daily senses, roughly 6.6 times 10 to the minus 34 joule seconds. Imagine a decimal point followed by 33 zeros before you reach a digit. It is the heartbeat of the microscopic world. Because it is so small, the stairs of our daily life look like a smooth ramp. We don't feel the grains of energy when we turn on a lamp or feel the sun on our skin. But at the foundation of reality, the river had turned into a spray of droplets. Drift with me now into the 1920s. The library is changing. The walls are becoming translucent, and the books are no longer filled with certainties, but with probabilities. Imagine you are standing in a room made of pure light. This is the abstract space the mathematicians call Hilbert space. It is not a place you can walk through with your feet, but a place you can explore with your mind. In this space, a particle is no longer a tiny billiard ball with a definite location. Instead, it is a state vector, a shimmering arrow pointing through a forest of possibilities. Think of a wave traveling across a vast, dark ocean. This is the wave function, the mathematical soul of the quantum world. Before Alice or Bob, our observers, look at a particle, the particle does not have a position. It is the wave. It exists in a state of superposition.
Visualize a coin spinning on a table so fast that it is a blur. While it spins, it is neither heads nor tails. It is a ghost of both, a shimmering blend of possibilities. This is not because we are ignorant of the result. It is because in the quantum world, the blur is the reality. In this room of light, the great Heisenberg and Schrödinger are at work. Heisenberg gives us the uncertainty principle. He tells us that the more we know about where a particle is, the less we can know about where it is going. It is as if the universe has a built-in privacy policy. You can see the texture of the fabric, or you can see the speed of the loom, but never both at once. Schrödinger, meanwhile, gives us the equation for the wave itself. He describes how these clouds of probability move and grow. But then something even stranger emerges. Imagine two of these spinning coins, these blurs of possibility, brought close together. As they spin, they begin to influence one another. Their waves overlap. Their probability clouds touch and merge. According to the new rules of Hilbert space, when two systems interact, they no longer have their own separate wave functions. They join together. They become a single composite wave, a single arrow in a much larger, more complex room. This is the birth of the non-factorizable state. Think of two drops of ink falling into a glass of water. At first, they are separate points of color, but as they swirl, they entangle. You can no longer describe the first drop without describing the second. They have lost their individuality to the relationship. The island of reason is left far behind. We are now sailing on an ocean where relations are more fundamental than things, where the here and the there are beginning to lose their meaning. Consider this as you drift deeper. If the universe is built from waves that can overlap and merge, then where does one object truly end and another begin? In the next chapter, we will follow Einstein as he realizes the consequences of this merging. We will watch him struggle with a reality that suggests two things can be light years apart and yet remain a single, indivisible wave. We will look into the spooky heart of the mystery.
As you settle deeper into your rest, imagine the scene shifting once more. The translucent walls of the quantum room fade, replaced by the quiet wood-paneled study of a house in Princeton, New Jersey. The year is 1935. Outside, a gentle rain might be falling, pattering against the glass, but inside, the air is thick with the scent of pipe tobacco and the heavy silence of profound thought. Visualize a man sitting at a desk littered with papers. He has a wild mane of white hair and eyes that seem to see far beyond the walls of the room. This is Albert Einstein. He is a man who believes in a universe of geometry, order, and logic. To him, the moon is there even when he isn't looking at it. Things are real. Things are separate. Things are local. But he has seen the mathematics of the wave function, and it troubles him deeply. He sees that if quantum mechanics is the final word, then two particles, our travelers, can remain a single entity no matter how far they drift. Einstein decides to challenge this. Along with two colleagues, Boris Podolsky and Nathan Rosen, he crafts a paper that will become one of the most famous in the history of science. It is known as the EPR paper. Drift with Einstein for a moment as he builds his argument. He starts with a simple, almost poetic premise, the criterion of reality. Imagine you are walking through a forest. You see a leaf fall. You don't need to touch the leaf to know it is falling. You can predict its path. Einstein argued that if we can predict the value of a physical quantity with certainty without disturbing the system in any way, then there must be an element of reality corresponding to that quantity. In simpler terms, he believed that things have properties like position or spin, regardless of whether we choose to measure them. He believed the universe doesn't wait for us to ask a question before it decides what the answer is. Now, recall our two entangled travelers. Einstein imagined them moving light years apart. He realized that according to quantum theory, if Alice measures her particle and finds it is spinning up, Bob's particle, far away, must immediately be spinning down. Because Alice could choose to measure her particle at any moment, and Bob's particle would instantly respond, Einstein argued that Bob's particle must have already possessed that spin all along. If Bob's particle changed its state instantly without any signal traveling from Alice, it would violate the speed limit of light. It would be what he called spukhafte Fernwirkung, spooky action at a distance. Visualize Einstein pacing his study, shaking his head. To him, this was a sign that quantum mechanics was incomplete. He believed there must be a secret code. Imagine each particle carrying a hidden set of instructions, a tiny invisible manual written at the moment of their birth. When they were created together, the manual told them, if they ask you, you be up and you be down. In this view, the connection is not spooky at all. It is just a shared history. Like two identical clocks set together and then moved to different rooms, they tick in unison, not because they are talking to each other across the walls, but because they were synchronized at the start. These are what we call hidden variables. Einstein wanted a universe where things were separate and local. He wanted to believe that Bob's particle had its own real state that Alice could not reach with her measurement. He wanted a world where the tapestry was made of individual threads, not a single indivisible sheet. But on the other side of the Atlantic, in Copenhagen, Niels Bohr was listening. Bohr did not agree. Imagine Bohr as a man comfortable with ambiguity, a man who believed that we cannot speak of a particle's properties until we have performed the measurement. To Bohr, the measurement context was everything. You cannot separate the leaf from the act of looking at it. The two giants of physics were locked in a quiet, profound battle of the mind. Einstein insisted that the world was made of separate, objective parts. Bohr insisted that the world was a holistic, relational whole, where separability was a dream we had to wake up from. For Einstein, entanglement was a flaw in the theory, a ghost in the machine, that proved we needed a better, more real explanation. But for the quantum world, entanglement was not a flaw. It was the truth. As you drift now, imagine the tension between these two ideas. On one hand, the comfort of the secret code,
the hidden manual that keeps everything local and safe. On the other hand, the vast, shimmering mystery of a universe where distance is not a barrier, and two things can remain one across the span of the stars. Einstein's spookiness was meant as a criticism, but as the decades passed, the spookiness refused to go away. Consider this. Is it more comforting to believe we are all separate islands with secret codes, or to believe we are all part of the same unbroken wave? In the next chapter, we will leave the quiet study of Einstein and move into the 1960s to a man named John Bell, who found a way to take this philosophical argument and turn it into a mathematical test. We will find out if the universe really does have a secret code, or if it is even stranger than Einstein could have imagined.
As the rain in Princeton fades from your mind, imagine the world beginning to turn faster. The wood-paneled study dissolves, replaced by the humming, high-energy atmosphere of the 1960s. We find ourselves in Switzerland, at the edge of the Alps, where the European Organization for Nuclear Research, CERN, is coming to life. But we are not standing in the middle of a massive particle accelerator. Instead, imagine a quiet office, tucked away from the noise of the machinery. There is a man here named John Bell. Visualize John Bell as a quantum rebel. He is a physicist who spent his days working on the practical, heavy machinery of the subatomic world, but his nights were spent staring into the same dark mystery that haunted Einstein. He was a man of quiet, sharp intensity, with a mind that refused to accept that the debate between Einstein and Bohr was just a matter of opinion or philosophy. For nearly 30 years, the world had lived with the EPR paradox. Most physicists had simply moved on, using the math of quantum mechanics to build transistors and lasers, ignoring the spooky ghosts in the basement. They treated quantum theory like a black box. It worked, so why worry about what was happening inside? But Bell could not look away. He wanted to know if Einstein's secret code, those hidden variables, actually existed. He wanted to know if the universe was truly made of separate, independent parts, or if it was bound together in a way we couldn't yet see. Drift with Bell now as he performs a miracle of thought. Imagine him sitting with a pencil and paper, setting a trap for the universe. He realized that if Einstein was right, if every particle carried a hidden manual that told it how to behave, then there were certain mathematical limits to how connected two distant things could appear to be. Visualize a game of chance. Imagine Alice and Bob are in different rooms, and they are each given a pair of dice that were once rolled together. If the dice have a secret connection, a hidden instruction that says, "always match," their results will be correlated. But Bell realized that there is a statistical ceiling, a maximum amount of correlation that is possible if the dice are separate, local objects. He called this ceiling an inequality. It was a simple, elegant limit. In your mind, imagine a high wall. On one side of the wall is the classical world, the world of local realism, where things have their own properties and signals can't exceed the speed of light. On the other side is the quantum world. Bell calculated that if Einstein's secret code was real, the particles between Alice and Bob could never jump over that wall. They would always stay below a certain number. But then he looked at the equations of quantum mechanics, the very equations Einstein had doubted. To his astonishment, the math predicted that under the right conditions, the particles would ignore the wall entirely. They would be more correlated than any local separate system could ever be. This was the oracle. For the first time, the mystery was no longer a matter of interpretation. It was a matter of measurement. Bell had shown that we could actually ask the universe, "Do you have a secret code, or are you truly spooky?" Imagine the weight of that realization. If we could perform this experiment, we wouldn't just be testing a theory, we would be testing the very definition of reality. We would find out if the island of reason was truly an island, or if everything was secretly connected by an underwater landscape we had never mapped. Bell published his findings in 1964 in a small journal that few people read at the time. He wasn't sure if anyone would ever be able to build the experiment. The technology required to create and measure single pairs of entangled photons across large distances didn't exist yet. His paper sat like a dormant seed, waiting for the world to catch up. As you drift, visualize Bell's inequality as a lonely lighthouse on a dark coast. It doesn't tell us how the connection works, but it tells us where the boundaries of the old world end. It tells us that either the universe is non-local, meaning things are connected across space instantly, or that things don't have definite properties until they are looked at. Think of the patience required to hold such a thought. For years, Bell's work was a quiet whisper in the background of a busy world, but the seeds were beginning to stir. In the next chapter, we will leave the quiet halls of CERN and enter the laboratories of the 1970s and 80s. We will watch as a new generation of scientists, the experimentalists, take Bell's lighthouse and use it to search the dark. We will witness the first time the universe was asked the question and the startling, unmistakable answer it gave back. We will watch as the wall Einstein built is finally, gently crossed. Imagine the abstract geometry of Bell's lighthouse beginning to solidify into something real. The high intellectual peaks of the Swiss Alps dissolve, and we find ourselves descending into a much humbler space. We are in a basement at the Institut d'Optique in Orsay, just south of Paris. The year is 1982. The air here is different. It is cool and slightly damp, carrying the faint metallic scent of electronics and the sharp, clean ozone of high-voltage equipment. The room is dim, lit only by the soft green and red glows of instrument panels. In the center of the room, stretching across a heavy, vibration-proof table, is a forest of mirrors, lenses, and crystals. This is the world of Alain Aspect. Visualize Aspect as a man of immense patience. While the rest of the world was busy with the loud, visible progress of the late 20th century, he and his team were engaged in a quiet, delicate hunt. They were trying to catch a ghost. They were trying to perform the experiment that John Bell had dreamed of 2 decades earlier. At one end of the table, imagine a source, a small chamber where calcium atoms are being coaxed into a specific state. When these atoms decay, they emit 2 photons at once. These are our travelers, our entangled twins. Drift with these photons now. They are not like the billiard balls of Newton's world. They are tiny, indivisible pulses of light, shimmering with a shared secret. They race away from the source in opposite directions, moving at the absolute speed limit of the universe. As they fly,
They head toward two polarizers. Think of these as gates that only allow light to pass if its vibration is aligned in a certain way. Now, recall Einstein's fear. He believed that the only way these photons could coordinate their behavior is if they shared a secret code from the start. But Aspect had a plan to close the door on that explanation. Imagine the polarizers shifting. While the photons are already in flight, racing at 300,000 kilometers per second, the orientation of the gates is changed. This happens so fast that no signal moving at the speed of light could possibly travel from one gate to the other to tell it what to do. If the universe was local and separate, as Einstein hoped, then Alice's measurement could not possibly affect Bob's. They would be isolated islands. They would obey Bell's inequality. They would stay below the wall. But as the detectors began to click, the rhythm told a different story. Visualize the data points appearing on a glowing screen, one by one. The correlations were too strong. The photons were matching their states with a precision that defied the boundaries of space. They were jumping over Bell's wall. They were ignoring the lighthouse and sailing into the spooky dark. Aspect and his team had done it. They had asked the universe the ultimate question, and the universe had answered with a resounding, undeniable yes. Quantum entanglement was not a mathematical glitch, it was a physical reality. Imagine the quiet in that Paris basement when the results were finalized. The island of reason had not just been flooded, it had been revealed as part of a much larger, stranger geography. The particles were light years apart in potential, yet they acted as if they were still sitting in the same palm. This result didn't just change a few equations, it shifted the ground beneath our feet. It meant that the here and the there were not the absolute categories we thought they were. It meant that distance, for all its practical importance, was not a fundamental barrier to connection. As you drift with the memory of those clicking detectors, consider what this means for the vacuum of space. If two photons can remain one even as they race toward the edges of the galaxy, then the emptiness between them is not really empty. It is filled with a structure we are only just beginning to name. In this moment, as you rest, realize that the very atoms in your body once interacted with the atoms in the stars. According to the rules of the Paris basement, you are not a separate island. You are part of a shared cosmic state. In the next chapter, we will explore the no signaling rule. We will ask, if this connection is real and immediate, why can't we use it to talk to the stars? Why does the universe give us this deep connection, yet keep its secrets so carefully guarded? We will look at the bridge that quantum mechanics built between its own spookiness and the ironclad laws of Einstein's light. Take a deep breath and let the image of the Paris basement fade. The clicking of the detectors, the hum of the cooling systems, the sharp scent of ozone. Let them all dissolve into the quiet of the night. We find ourselves now in a place of pure abstraction, a space where the logic of the universe reveals its most careful boundaries. Imagine two travelers, Alice and Bob,
standing on opposite sides of a vast, tranquil ocean. They are separated by thousands of kilometers of dark, surging water. Each holds a small, glowing lantern. In the world we have just discovered, the world of Elaine Aspect and John Bell, we know that these lanterns are entangled. When Alice shutters her lantern to reveal a green light, Bob's lantern far across the horizon instantly glows red. There is no delay. There is no crossing of the waves. The connection is immediate, defying every wall of space and every tick of the clock. Naturally, you might ask, if the connection is instant, why can't Alice use her lantern to send a message to Bob? A warning, a greeting, a secret, faster than the speed of light. This is where the universe reveals a breathtaking piece of cosmic architecture. It is called the no-signaling theorem. Visualize Alice in her lonely station. She wants to tell Bob yes. She decides that if she measures her particle and finds it spinning up, it will mean yes. If she finds it spinning down, it will mean no. She reaches out to her particle with hope. But here is the catch, the quiet iron rule of the quantum world. Alice has no control over what she finds. When she performs her measurement, the result is truly, fundamentally random. It is like flipping a coin that has no memory and no weight. One moment it is up, the next moment it is down. She cannot force the particle to be up to send her message. She is a witness to the result, not its master. Drift with this thought for a moment. Alice looks at her particle and sees up. Across the ocean, Bob's particle instantly becomes down. The connection has happened. The universe has kept its promise. But Bob, looking at his own lantern, sees only a down. To him, this result looks just as random as any other. He has no way of knowing if Alice has even performed her measurement yet. He sees a sequence of ups and downs that look like static on a television screen, white noise in the dark. It is only when Alice and Bob eventually meet, traveling by boat or by radio, moving at the slow sub-light speeds of the classical world, that they can compare their notes. Only then, when they lay their lists beside each other, do the patterns emerge. Only then do they see that every time Alice had an up, Bob had a down. The connection is real, but it is a silent one. It is a correlation, not a conversation. Imagine the universe as a grand librarian who allows you to look at two copies of the same book at opposite ends of the library. You see that they are identical, page for page, word for word, but you are forbidden from writing in the margins. You can see the shared structure, but you cannot use it to change the story elsewhere. Why would the universe work this way? Visualize Albert Einstein's light beams once more. If we could send a message faster than light, the very structure of time would begin to unravel. In some frames of reference, the message would arrive before it was sent. Cause would follow effect. The past would be at the mercy of the future. The no-signaling rule is the bridge that quantum mechanics builds to keep Einstein's world safe. It allows the spookiness of entanglement to exist,
but it places a veil over it. It ensures that while the foundations of reality are deeply, instantly connected, the information we use to build our lives must still respect the slow, majestic pace of the speed of light. It is a form of cosmic censorship. The universe allows itself to be whole, but it requires us to be local. As you drift now, consider the beauty of this balance. We live in a world where everything is quietly, profoundly linked at the root, and yet we are granted the individuality of our own here and now. We are connected, but we are not overwhelmed. We are part of a single wave, but we are allowed to be our own droplets. Imagine the information in the universe as a hidden melody. Entanglement is the rhythm that holds the song together, even if the instruments are on different stages. But to hear the melody, you still have to wait for the sound to travel through the air. In this silence, there is a profound peace. The connection is there, whether we can use it or not. It is a feature of the architecture, a silent messenger that tells us we are never truly alone, even if the stars are too far to reach in a single breath. In the next chapter, we will move from the no signaling rule into the world of contextuality. We will ask, if properties don't exist until we look at them, what does that say about the reality of the things we touch? Is the moon only there when we look at it? Or is the universe asking us a different kind of question?
Imagine the vast, tranquil ocean of the last chapter slowly beginning to mist over. The horizons of Alice and Bob's world dissolve into a soft white haze, and as you drift through this mist, you find yourself standing in the middle of a garden at dusk. The air is cool and still, smelling of damp earth and night-blooming jasmine. In the center of this garden sits a single ornate wooden box. In our everyday classical life, we assume that this box has a real state. We believe that it has a weight, a color, and a certain number of secret items inside it, regardless of whether we are there to open it or not. This is what philosophers call non-contextual realism. It is the simple, honest belief that a chair is a chair, a coin is a coin, and the moon is the moon, even when the garden is empty and the world is asleep. But now, I want you to visualize something strange. Imagine you approach the box. You decide you want to measure its weight. You lift it, and it feels heavy, like it is filled with stones. But then imagine a friend approaches the box from the other side. They don't care about the weight, they want to measure its color. When they look at it, the box suddenly appears light as a feather to them, and its surface turns a brilliant, shimmering blue. If you were to ask the box both questions at once, its weight and its color, it might give you one set of answers. But if you were to ask about its weight and its scent instead, the answer for its weight might change entirely. The box does not have a fixed set of properties waiting in a manual. Instead, the properties emerge from the context of the question you choose to ask. This is the heart of contextuality, a mystery that goes even deeper than the spookiness of entanglement. In 1967, two thinkers named Simon Kochen and Ernst Specker sat down to challenge the very foundation of how we define a thing. They weren't looking at distant particles across an ocean, they were looking at a single particle right in front of them. Visualize them working at a chalkboard, their shadows long in the afternoon light. They asked, can we assign definite, secret values to every possible property of a quantum system, such that those values don't care about the context of our measurement. Their answer was a quiet, mathematical no. They proved that in the quantum world, the result of a measurement depends on which other measurements you are performing at the same time. You cannot think of a particle as a little ball with a list of pre-written labels. The labels only appear when you ask for them, and they shift depending on what else you are curious about. Drift with this thought for a moment. It suggests that the universe is not a collection of static objects sitting on a shelf. It is more like a grand interactive dialogue. Think of a prism. When it sits in the dark, does it have a rainbow? We might say yes, but the rainbow only exists when the light strikes the glass at a specific angle. The rainbow is a relationship between the light, the glass, and the observer's eye. It is contextual. Einstein famously asked his friend Abraham Pais, "Do you really believe the moon is not there when you are not looking at it?" In the world of Kochen and Specker, the answer is a subtle, mesmerizing one. Perhaps the moon is there, but the way it is there, its precise position, its exact glow, its very moonness, is part of a shared state between the moon and the rest of the universe, including us. Imagine you are walking through a forest of shifting shadows. In the classical world, the trees stay trees and the shadows stay shadows. But in the contextual world, the tree might only become a tree when you reach out to touch the bark. This is not a lack of reality. It is a richer, more intricate kind of reality. It means that we are not just spectators watching a movie. We are participants. We are part of the context that gives the world its shape. Consider the peace in this realization. If the properties of the world are contextual, then the universe is never truly finished. It is constantly being defined and redefined by the relationships within it. Entanglement told us that things are connected across space. Contextuality tells us that things are connected across meaning. As you drift now, visualize your own life, your thoughts, your memories, the very way you feel in this moment. Are they not contextual? Do you not feel different in the light of the sun than you do in the quiet of the night? Are you not a different version of yourself depending on who is there to hear your voice? The quantum world is simply reflecting a truth we feel in our own hearts, that nothing exists in a vacuum. Everything is part of a context. Everything is defined by its neighbor. In the next chapter, we will leave the garden of shifting shadows and move into the cold, quiet mechanics of decoherence. We will ask, if the world is so shimmering and contextual, why does it look so solid? Why do the tables and chairs of our lives stay so stubbornly in place? We will look at how the environment, the very air around us, acts as a silent witness that forces the quantum world to behave like the classical one we know. Imagine the garden of shifting shadows from the last chapter slowly beginning to settle. The mist that blurred the edges of the box and the trees is lifting, burned away by a cold, clear morning light. As you drift through this transition, you find yourself back in a place that feels familiar. You are sitting in a quiet room. Perhaps it is your own bedroom or a study filled with books. Notice the objects around you. A heavy stone paperweight on a desk, a glass of water, a clock ticking steadily on the wall. In this room, the world feels solid. The paperweight doesn't change its weight depending on who looks at it. The water doesn't shimmer between being a liquid and a ghost. The clock doesn't exist in a superposition of 3 o'clock and 4 o'clock. Here, the island of reason seems to have returned with a vengeance. But if everything is built from quantum particles, from the contextual blurs and entangled waves we have been studying, why don't we see the spookiness in our morning coffee? The answer lies in a beautiful invisible process called decoherence. Visualize that paperweight on your desk. In a vacuum, perfectly isolated from the rest of the universe, it might be able to exist in a shimmering quantum state. But the paperweight is never truly alone. It is being bombarded. Every second, billions upon billions of air molecules are striking its surface. Countless photons of light are bouncing off it. Heat from the room is vibrating through its atoms. In the quantum world, every one of these tiny collisions is an interaction. And as we know, when two things interact, they become entangled. The paperweight is constantly, relentlessly entangling itself with the air, the light, and the floor. In the 1970s and 80s, thinkers like H. Dieter Z. and Wojciech Zurek realized that the environment is not just a background. It is a silent witness. Imagine you are trying to keep a secret in a crowded room. If you are alone, the secret is yours. But as soon as one person hears you, the secret is shared. If 1,000 people hear you, the secret is no longer a secret. It is public knowledge. Decoherence is the leaking of quantum secrets into the environment. When a single air molecule hits our quantum traveler, it carries away a tiny bit of information about where that particle is. When billions of molecules do it, the wave of the particle, that beautiful blur of possibilities, is scattered into the surroundings. The coherence, the togetherness of the quantum state is dissolved. Drift with this image, a drop of ink falling into a vast, rushing river. For a split second, the drop is a concentrated point of color, but the river immediately pulls it apart, stretching it, thinning it, until the ink is so spread out that you can no longer see it. The ink hasn't disappeared, it is just so entangled with the river that you can no longer pick it out. This is why we don't see superpositions in our daily lives. The environment measures everything, all the time, with such ferocity that the quantum blurs are forced to settle into definite states before we can even blink. Zurich called this quantum Darwinism. He suggested that the environment selects certain states to survive. These are the pointer states, the ones that are the most robust, the ones that can be copied thousands of times into the environment without falling apart. Position is a pointer state. This is why things have places in our world. Imagine the environment as a grand broadcasting system. Because so many photons are bouncing off the paperweight and carrying information to so many different places, everyone who looks at the desk agrees on where the paperweight is. The objectivity of our world is born from this redundant, overwhelming entanglement. The classical world is not a different world from the quantum one. It is simply the quantum world seen through the lens of a trillion witnesses. Consider the peace in this realization, the stability of your life, the floor that holds your weight, the air that fills your lungs is a gift from this silent witnessing. The universe is so deeply connected that it uses its own connectivity to create the illusion of separation. It is as if the universe is holding a billion mirrors up to itself at every moment. And in the glare of all those reflections, the shimmering ghosts of the quantum world find a place to rest. They become the solid, dependable things we touch and name. But as you drift deeper, realize that even though the spookiness is hidden, it is still there, beneath the surface. The entanglement hasn't vanished, it has just moved into the environment. We are all swimming in a sea of correlations that are simply too complex for us to see. The paperweight is still entangled with the air,
and the air is entangled with the walls, and the walls are entangled with the earth. In the next chapter, we will look at what happens when we try to push back against this decoherence. We will move into the high-tech, ultra-cold world of quantum information. We will ask, if the environment is a witness we want to escape, how do we build a box quiet enough to hold a quantum secret? We will look at the birth of the qubit and the quest to build a computer that thinks in waves.
Take a long, slow breath and let the world of the silent witness drift into the background. Imagine the room you were sitting in, the ticking clock, the air molecules, the scattering photons, all beginning to slow down. The colors of the walls soften and fade into a pale, clinical white. You are moving now into a place of extreme, engineered silence. Visualize a laboratory deep in the heart of a modern research institute. This is not the basement of Orsay or the quiet study of Einstein. This is a cathedral of glass, steel, and high-tech isolation. In the center of the room stands a massive cylindrical structure made of polished stainless steel and gold. It looks like a grand inverted chandelier, shimmering with an intricate web of wires and coaxial cables. This is a dilution refrigerator, a vault designed to reach temperatures colder than the deepest reaches of outer space. As you drift closer, imagine the temperature falling. It drops past the freezing point of water, past the point where air itself turns into a liquid, and down toward the absolute floor of the universe, absolute zero. At this depth, nearly all thermal motion ceases. The chaotic bombardment of air molecules we discussed in the last chapter has been stilled. The witnesses have been banished. In the very heart of this cold, quiet machine, resting on a small silicon chip, is our new traveler, the qubit. In the classical world of your laptop or your phone, information is a series of bits. A bit is like a light switch. It is either on or it is off. It is a 0 or it is a 1. It is a world of either or, a world where every question has a single definite answer. But a qubit, a quantum bit, is different. Imagine a sphere. Let us call it the Bloch sphere. Imagine a point at the very top of the sphere representing the number 0, and a point at the very bottom representing 1. In the classical world, you are restricted to those two poles. You are either at the top or the bottom. But the qubit is allowed to exist anywhere on the surface of that sphere. It can be a shimmering blend of both 0 and 1 at the same time. This is the state of superposition. Drift with this image. A qubit is like a musical note that is not just a C or a G, but a rich, resonant chord containing both C and G. It is a wave of information that hasn't yet been forced to choose a side. Now imagine bringing a second qubit into this ultra-cold vault. Through a delicate pulse of microwave energy, we bring them together. We perform a gate, a quantum handshake. In this moment, the two qubits become entangled. They are no longer two separate notes. They are a single, complex harmony. If you change the state of one, the other responds instantly, even here in the silence of the vault.
But unlike the accidental entanglement of the natural world, this is engineered entanglement. This is a connection we have built with intention. Why go to such lengths? Why build these massive golden refrigerators just to hold a few shimmering waves? Because entanglement is a resource, a new kind of fuel for the human mind. Imagine a computer that doesn't just check one path at a time through a maze, but instead explores every possible path simultaneously. Because the qubits are entangled, the computer can feel the structure of a problem across all its parts at once. It can see patterns that a classical machine, limited to its zeros and ones, would take billions of years to uncover. But as you watch the shimmering qubits, notice how fragile they are. Even here, at the edge of absolute zero, the silence is not perfect. A single stray photon, a tiny grain of heat, can find its way into the vault. When it strikes the qubit, it measures it. It acts as a witness. And in that instant, the entanglement is broken. The chord collapses into a singular, lonely note. The blur on the block sphere is forced to one of the poles. The secret has leaked. This is the constant battle of the quantum engineer, to keep the world away, to maintain the silence long enough for the qubits to finish their work. Consider the metaphor of a dream. While you sleep, your mind exists in a state of superposition. You can be in two places at once. You can be a different version of yourself. The logic of the either-or dissolves. But as soon as the alarm clock rings, as soon as the first light of morning touches your eyes, the dream is measured. It collapses into the singular reality of the waking day. Quantum computing is our attempt to build a machine that dreams. As you drift now in the absolute silence of the vault, visualize the potential held in these connections. We are no longer just observing the spookiness of nature. We are beginning to speak its language. We are using entanglement to encode secrets that can never be broken, and to solve riddles that have haunted us for centuries. We have moved from the island of reason to the sanctuary of the cold, and in so doing, we have turned a philosophical mystery into a technological tool. But there is still one question that lingers in the frost. If we can use entanglement to process information, can we use it to move that information across the stars? In the next chapter, we will leave the laboratory and look at the extraordinary feat of quantum teleportation. We will ask, is it possible to move a state from one place to another without moving the thing itself? Can we use the spooky bridge to step across the void? We will look at how we send a quantum secret across the earth and eventually into the heavens.
Imagine for a moment that you are standing on the edge of a great salt-cracked desert. The sky above is a deep, bruised purple, and the stars are beginning to pierce through the twilight like cold diamonds. The air is perfectly still, so quiet that you can almost hear the soft tectonic shifting of the earth beneath your feet. In the classical world, the world of our daily lives, to move from one side of this desert to the other, you must cross the space between. You must take steps. You must endure the time it takes for your body to traverse the kilometers. Every atom of you must be physically carried from where you are to where you wish to be. This is the only way we have ever known to travel. But tonight, we're looking at a different kind of journey. We're looking at a way to arrive without ever having moved. This is the mystery of quantum teleportation. Visualize two observers again, our faithful guides, Alice and Bob. They are separated now by a distance so vast it defies the imagination. Alice is here on this desert floor. Bob is far away, perhaps on a station orbiting a distant moon. Before they parted, they shared a gift, a pair of entangled photons. One stays with Alice in her desert camp. The other is carried by Bob into the heavens. This is their bridge. It is a silent, invisible connection that spans the void, a shared mathematical state that ignores the thousands of miles between them. Now, imagine that Alice has a third particle. Let us call it the traveler. This traveler is special. It holds a delicate, unique quantum secret, a specific spin, a shimmering orientation on the block sphere that has never existed in exactly this way before. Alice wants to send this secret to Bob, but as we know from the no cloning theorem, she cannot simply make a copy of it. Nature is a jealous guardian of its originals. It forbids the duplication of a quantum soul. To move the secret, Alice must do something radical. Drift with me into the heart of Alice's laboratory. Visualize her bringing the traveler close to her half of the entangled bridge. She performs what scientists call a Bell state measurement. Imagine the traveler and the entangled particle touching. Their probability clouds merge. In that instant, they become deeply, inextricably entwined. But there is a heavy price for this connection. To measure them together, Alice must destroy the traveler's original identity. In the quantum world, the act of sending is an act of sacrifice. As Alice records her results, the original traveler, the one that sat in her hand, is shattered. Its specific shimmer, its unique secret, vanishes from the desert floor. It is gone, dissolved into the static of the environment. But look across the void to Bob. The moment Alice performed her measurement, Bob's entangled particle, his half of the bridge, felt a tremor. Because it was linked to Alice's particle, it has been instantly transformed. It is not yet the traveler, but it has become a scrambled version of it. It is holding the secret, but it is holding it behind a locked door. Now, Alice picks up a classical phone. She sends a simple message to Bob. 2 bits of information moving at the slow, majestic speed of light. She tells him, "I have measured the state. Here is the key you need to unlock yours." Bob receives the message. He applies a specific transformation to his particle, a gentle nudge of a magnetic field, a soft pulse of light. And in that moment, a miracle occurs. His particle, which has been with him on the moon all along, suddenly assumes the exact identity of the traveler that was destroyed in Alice's desert floor. Every shimmer, every spin, every delicate nuance of the original is now present in Bob's hand. The state has traveled, but the matter has stayed behind. Visualize the profound nature of this leap. Nothing physical crossed the void. No atom of the traveler moved through the vacuum. Only the information, the very essence of what the traveler was, has been reconstructed on the other side of the stars. It is as if a grand architect sent the blueprints for a cathedral across the ocean, and the stones on the other side rearranged themselves to match the design perfectly, while the original cathedral crumbled into dust. In 1993,
Charles Bennett and his colleagues first described this bridge in the language of mathematics. They showed us that while we cannot clone reality, we can relocate it. And this is not just a dream. Imagine a mountain peak in Tibet, 13,000 feet above the sea. In 2017, scientists fired a green laser beam from that peak towards a satellite named Mikas, orbiting 500 kilometers above the Earth. Using this bridge of light, they successfully teleported a quantum state from the ground into space. The traveler reached the heavens without ever leaving the mountain. As you drift now, consider the beauty of this reconstruction. It suggests that what we are, our identity, our secrets, our very essence, might not be tied to the specific atoms we are made of, but to the patterns of our connections. If we can move the pattern, have we moved the thing? In the silence of the night, realize that the universe is a place of constant, shimmering reconstruction. We are being built and rebuilt at every moment by the information that flows between us. In our final chapter, we will bring our journey to a close. We will move from the bridges of light to the very end of the story, to the possibility that the entire universe, from the smallest grain of sand to the furthest galaxy, is a single, vast web of entanglement. We will ask, if everything is connected, what does it mean to be home? Take a deep, slow breath. Feel the weight of your body as it rests, supported by the quiet gravity of the earth. Imagine the room around you expanding, the walls moving back, the ceiling lifting, until you are no longer inside a building, but resting on a grassy hill beneath a vast, silent canopy of stars. As you look up, the Milky Way stretches across the sky like a river of silver dust. In the classical world we left behind, you might see these stars as distant, isolated fires, lonely points of light separated by an incomprehensible empty dark. But tonight, our eyes have been changed. Visualize, if you will, that the empty space between the stars is not empty at all. Instead, imagine a loom. It is a loom of infinite proportions, and its threads are made of light, probability, and entanglement. Every time two particles touch, every time a star is born, every time a ray of light reaches across the vacuum, a new thread is woven. For decades, we believed that space was just a stage, a pre-existing floor upon which the drama of the universe was performed. We thought that if you took away all the matter, the space would still be there, like an empty theater waiting for the next play. But modern physics is whispering a different, more pensive truth. Drift with me into the minds of the theorists who are staring at the very edge of black holes. In recent years, they have begun to suspect that space-time itself, the very here and now we inhabit, is not fundamental. Instead, it is an emergent property. Imagine a beautiful, intricate tapestry. When you stand close to it, you see the individual threads of entanglement, the spooky connections Alice and Bob have been testing. But when you step back, the threads disappear, and you see only a smooth, continuous image. The image is space. The threads are entanglement. In 2013, Leonard Susskind and Juan Maldacena proposed a bold cinematic idea. They called it equals EPR. They suggested that the Einstein-Rosen bridges, those hypothetical wormholes that connect distant points in space, are actually the same thing as the EPR entanglement between particles. Visualize a bridge made of pure correlation. Every entangled pair is a tiny microscopic thread of geometry. If you have enough of these threads woven together in a dense, intricate pattern, you get the fabric of the universe. Without entanglement, the space would simply fall apart. There would be no distance, no near, and no far. The universe would have no shape. Entanglement is the glue that holds the world together. As you drift now, realize that this connection we have been studying is not a strange exception. It is the rule. It is the invisible architecture that allows a star in the Andromeda galaxy to be part of the same reality as a grain of sand on a beach in the Pacific. Think of the no signaling rule again, the silent messenger. The universe protects our individuality by forbidding us from sending messages faster than light, but it ensures our unity by weaving us into the same quantum tapestry. We are separate in our actions, but we are one in our structure. Imagine the peace of this realization. Every atom in your body carries a history of entanglement that stretches back to the very first moment of the cosmos. You are not a solitary island drifting in a cold void. You are a knot in the loom, a unique and beautiful pattern in a web that spans the entirety of existence. The midnight scientist does not see the dark as a place of loneliness. They see it as the medium of connection. As the stars overhead begin to pulse slowly with the rhythm of your breath, consider the journey we have taken. We have seen that distance does not mean what it once meant. We have seen that the whole is always more than the sum of its parts. And we have seen that the spookiness Einstein feared is actually the very heartbeat of the world. Visualize now the entire universe not as a collection of things, but as a sea of relationships. The galaxies, the planets, the trees, and the people, all ripples on the same vast, entangled ocean. When you wake tomorrow, you will return to the world of either-or, to the world of separate chairs and solid walls. But in the quiet inner sanctuary of your mind, you will know the truth. You will know that the here is always linked to the there, and that the space between us is not a barrier, but a bridge. Drift now into the deepest rest. Feel the threads of the universe supporting you, weaving around you, holding you in a silence that is full of meaning. You are home. You have always been home. The story of entanglement is the story of us. It is the story of how we found that in the heart of the smallest particle, the entire universe is waiting to be known. Sleep now. The loom is still turning. The web is still holding. And you are part of the light.
Welcome back to the Midnight Scientists. Find a place of stillness, whether you are lying in the dark, the weight of the day slowly lifting from your shoulders, or simply sitting in a quiet room. Let yourself arrive here. Now, take a deep breath in, filling your lungs with the cool, steady air of the present moment, and exhale slowly, letting the noise of the world drift away like smoke in a gentle breeze. Tonight, we are going to do something impossible. We are not just going to observe the universe, we are going to build one. Not with atoms or steel or fire, but with something far more elegant. We are going to build a universe out of silence and math and memory. You are safe here. There is no rush. The stars can wait. For the next hour, we are merely architects of the void, standing before a blank canvas that stretches deeper than time itself. Chapter 1: The Architecture of Silence. The Blank Screen. Imagine, if you will, a perfect darkness. It is not a scary darkness, it is a velvet darkness, soft, infinite. It is the color of a computer screen before the code begins to run. It is the color of sleep before the dream begins. In the world of astrophysics, before we have galaxies spiraling in the deep or nebulas glowing with neon fire, we have this, the box. Visualize a cube, a perfect invisible box floating in the emptiness. In our minds, let's make this box enormous. It is not measured in inches or miles, but in light years. Let us say it is 100 million light years across, a volume of space so vast that the human mind cannot truly grasp it. Yet here, in our imagination, we can hold it in the palm of our hand. Inside this box, there is nothing. Not yet. It is a vacuum, a silence so profound that if you were to shout, your voice would simply unravel into the quiet. This is where the simulation begins. Before we can have the chaos of creation, we must have the peace of the void. Drift here for a moment. Feel the spaciousness of it. There is no gravity here to pull you down, no light to hurt your eyes, just the pure, clean potential of an empty universe waiting to be born. The grid. Now slowly, let us impose order upon this nothingness. Imagine fine glowing lines appearing in the dark, a grid, vertical lines rising up like pillars of light, horizontal lines stretching out to the horizon, crossing and intersecting. They form a lattice, a three-dimensional scaffolding that fills our dark box. This is the coordinate system, the map. In the mind of a supercomputer, that great humming brain of metal and silicon, space is not just emptiness, it is a series of addresses. Every point in the dark has a name. Every corner of the void has a number. Visualize this grid humming quietly. It is the nervous system of our new universe. It is waiting for input. It is waiting for the laws of physics to breathe life into its geometry. When scientists set out to simulate the cosmos, they are not playing God, they are playing composer. They are writing the sheet music, the equations of gravity, the laws of motion, the thermodynamics of gas, and asking the computer to play the symphony. But right now, the orchestra is silent. The instruments are tuned, the conductor has raised the baton, but the first note has not yet sounded. Feel the anticipation in that silence. It is the same feeling you have just before you fall asleep, that moment where the waking world fades and the dream world hovers, ready to take you. The particles. Now let us populate the dark. We are not going to scatter stars. Not yet. Stars are complex. They are messy, brilliant, violent things. We must start simpler. We must start with the dust. Imagine you are holding a handful of sand, silver, shimmering sand. Now open your hand and blow. Watch as billions of tiny specks drift out into the grid. They don't fall because there is no down. They simply float, suspending themselves in the lattice of light. In our simulation, these are not grains of sand, they are particles. But they are not atoms either. They are something much larger. Each single tiny dot in our simulation represents a massive amount of matter, perhaps the mass of 1,000 suns or even 1,000,000. We call this an n-body simulation. The n stands for the number of particles. In the early days, 50 years ago, scientists could only afford a few hundred particles, a tiny, lonely cluster in a digital dark. But tonight, in our midnight simulation, we have billions. Visualize them, a mist of silver dust filling the dark cube. They are perfectly still, frozen in time, a snapshot of a universe that hasn't started breathing yet. It is beautiful, isn't it? The simplicity of it. If you looked closely at one of these particles, you would see it is cold. It is dark matter. It doesn't glow. It doesn't reflect. It simply is. It is a placeholder for gravity. It is a promise that something is about to happen. Now we must give them instructions. A universe without rules is just chaos. A universe with rules is a story. We whisper the first law into the void. Gravity. Every particle, we whisper, shall reach out to every other particle. It is a law of attraction, a law of longing. Even across the vast, cold distances of our simulation box, no particle is truly alone. Each one feels the faint, ghostly tug of its neighbor. The particle on the far left knows about the particle on the far right. They are connected by invisible threads of force. This is the most exhausting part of the creation. The computer must calculate these connections. Billions of particles, each shaking hands with billions of others. I feel you, the particle says. Come closer. We whisper the second law, expansion. The space between you, we say, shall grow. This is the great conflict of the cosmos. Gravity wants to pull everything together into a warm, tight embrace. Expansion wants to scatter everything apart into the lonely dark. The story of our universe and the story of this sleep is the balance between these two forces, the pulling in and the letting go. Inhale, pulling the air in. Exhale, letting the air go. Gravity and expansion, the heartbeat of the deep. The first tick. The stage is set, the grid is glowing, the silver dust is suspended in the void. The laws are written in the code. It is time to start the clock. In a simulation, time does not flow like a river. It ticks. It moves in steps. Click, click, click. Each step might represent 1,000,000 years. We are going to watch eons pass in the blink of an eye. But for now, let us slow it down. Let us watch the very first step. Imagine the enter key is pressed. The silence breaks, not with a noise, but with motion. Slowly, imperceptibly, the dust begins to drift. It is not random, it is choreographed by the math. Tiny imperfections in the cloud, places where the dust was just a little thicker, begin to act like magnets. They pull their neighbors in. Watch a single cluster of particles. It looks like a wisp of smoke curling in a sunbeam. It is collapsing. Gravity is winning here. The particles spiral inward, dancing a slow, silent waltz around a common center. Elsewhere, in the empty spaces between the clouds, the void is growing. The particles are fleeing, leaving behind great hollow caverns of nothingness. The universe is sorting itself out. It is deciding where to be heavy and where to be light, where to be full and where to be empty. Imagine floating in one of these great empty voids between the filaments. It is a space so quiet that even your thoughts seem to slow down to match the rhythm of the expansion. You are drifting in the deep ocean of the computer's mind, resting in the code. This is the foundation. Every galaxy you have ever seen, every star you have ever wished upon, every planet, every person, it all starts here, in the dark, in the grid, with a handful of dust and a simple rule. Connect. The simulation is running smoothly now. The fans of the supercomputer are humming a low, steady lullaby. The data is flowing like water. We have built the skeleton of the night, but a skeleton is not a body. A web is not a world. We need more. We need warmth. We need the chaotic, beautiful, messy fire of existence. We need to turn on the light. But that is a story for the next chapter. For now, stay here in the soothing dark. Watch the silver filaments drift and sway. Let gravity hold you. Let the expansion give you space. You are the architect, and you are the dreamer. Chapter 2: The Echo of the Beginning. We are floating in the grid. Around us, the silver dust of our simulated universe is drifting, pulled by gravity, guided by the invisible lines of the code. It is a peaceful scene, a cosmic ballet of slow motion. But as we watch these filaments form, a question arises, a question that haunts the dreams of every cosmologist who has ever looked up at the night sky. Why here? Why did a clump of matter form here, in this specific coordinate, and not there, a million light years to the left? Why is the universe textured? Why isn't it just a smooth, uniform soup of nothingness? If the universe began as a single point, perfect, unified, and simple, it should have stayed smooth. It should be a flat, featureless ocean. But it isn't. It is filled with islands and archipelagos and deep trenches. It has geography. To build a true simulation, to make our digital universe look like the real one, we cannot just scatter particles at random. We need a map. We need to know where the mountains and the valleys of the cosmos came from. To find that map, we must leave our cool, dark simulation box for a moment. We must travel back, before the stars, before the dark ages, back to the very first heartbeat of existence. We must listen for the echo of the beginning, the seed. Drift with me now, backward through the timeline. Watch the galaxies unravel. Watch the filaments dissolve back into mist. Watch the mist compress, hotter and hotter, smaller and smaller. We arrive at the beginning. Imagine a seed. It is not a seed of wood or shell. It is a seed of pure energy. It is smaller than an atom, smaller than the nucleus of an atom. It is infinitely hot and infinitely dense. Inside this tiny speck, everything is trapped. Every star that will ever burn, every planet that will ever spin, every drop of water you have ever taken, it is all there, crushed together in a singularity of potential. It is holding its breath. In the language of physics, we talk about initial conditions. This is the data we must feed into our computer to start the simulation. But data is too cold a word for this. This is the DNA of reality. And here is the secret. The seed was not perfect. Deep inside that microscopic point, there were shivers, tiny, fleeting jitters called quantum fluctuations. Imagine the surface of a very hot cup of tea. Even if the table is still, the surface of the tea trembles slightly. Steam rises, molecules dance. It is never perfectly flat. The infant universe was trembling. It had tiny wrinkles, microscopic hills and valleys in the fabric of space itself. These wrinkles are the most important things in history. Without them, you would not exist. Without them, there would be no gravity to pull things together. There would be no you to listen to this story. The great breath, inflation. Then it happened. We often call it the Big Bang, but that sounds loud. It sounds violent. For our story tonight, let us think of it differently. Let us think of it as an unfolding, a blossoming, the great breath. In a fraction of a second, a slice of time so thin that math can barely describe it, the universe expanded. This is called inflation. Imagine you are holding a wrinkled sheet of fabric in your fist. It is crunched up, tight, full of tiny creases. Now, suddenly, 4 people grab the corners and pull. Snap. The sheet stretches out taut. But notice something. The wrinkles didn't disappear. They stretched. Those tiny, microscopic quantum shivers, they were stretched across the canvas of the cosmos. What was once a jitter smaller than an atom became a valley millions of miles wide. What was once a flicker of heat became a mountain of energy. Inflation took the microscopic and made it macroscopic. It froze the quantum dance into the landscape of the universe. And then it stopped. The stretching slowed, the energy cooled, and the universe began to sing. The song of the plasma. We are now 380,000 years after the beginning. It sounds like a long time, but in the life of the cosmos, it is less than a blink. The universe is no longer a point. It is a vast, hot fog. It is a soup of light and particles swirled together in a dense plasma. You could not see through it. It was like being inside the heart of a star, but you could hear it. Sound requires a medium to travel through. In space today, it is silent because space is a vacuum. But back then, the universe was not a vacuum. It was a fluid, it was dense, and it was ringing like a bell. Those stretched out wrinkles from the beginning created waves of pressure. Sound waves crashed through the hot plasma, giant cosmic ripples moving at more than half the speed of light. Hum. Can you imagine the sound? A tone deeper than the deepest cello, vibrating through the very stuff of reality. These sound waves gathered matter together. They pushed matter apart. They were the first architects. They were sculpting the fog, deciding where the galaxies would one day go. We call these baryon acoustic oscillations, a fancy name for a simple thing. The universe was breathing, in and out, compressing and rarefying. In our simulation, we need to capture this rhythm. We cannot just program the particles, we must program the echo of this song. We must teach the computer the song of the early universe. The breaking of the clouds. As the universe expanded, it cooled. The angry heat of the beginning began to fade. The plasma, which had been a chaotic storm of electrons and photons, began to settle. And then, a moment of magic. The temperature dropped just enough, to about 2,700 degrees Celsius, roughly the color of a warm light bulb, for atoms to form. Electrons found protons. They clicked into place. Suddenly, the fog cleared. Before this moment, light was trapped, bouncing around in the soup like a pinball. But now, with the particles bound into atoms, the path was clear. Flash. In an instant, light was set free. It streamed out in all directions, traveling freely through the newly transparent space. This ancient light is still traveling today. It is washing over Earth right now, passing through your roof, through your walls, through your body. We call it the cosmic microwave background, or the CMB. If you could see with microwave eyes, the night sky wouldn't be dark. It would be glowing, and it wouldn't be smooth. It would be speckled. You would see tiny patches of blue, slightly colder, and tiny patches of orange, slightly warmer. Do you know what those patches are? They are the sound waves. They are the frozen imprint of that ancient song. The orange spots are where the sound waves compressed the gas, where it was slightly denser. The blue spots are where the gas was rarefied, slightly emptier. This is the map. Feeding the machine. We return now to our quiet room, to our supercomputer, to our simulation box. We have the blank grid, we have the laws of physics, and now we have the initial conditions. We take this map, this ancient baby picture of the universe, and we feed it into the code. We tell the computer, look at the orange spots, put more particles there. Look at the blue spots, put fewer particles there. We are carefully recreating the texture of the Big Bang inside our machine. We are planting the seeds exactly where nature planted them 13.8 billion years ago. It is a delicate process. If we get the map wrong, the universe will look wrong. If we make the ripples too big, the galaxies will be giant, monstrous blobs. If we make them too small, the galaxies will be tiny wisps that never form stars. We have to tune it perfectly. We have to match the key of the cosmic song. The weight. The data is loaded. The initial conditions are set. The particles in our box are no longer randomly scattered dust. They are arranged in a subtle, beautiful pattern, a pattern that mimics the ancient ripples of the CMB. Everything is ready. The universe in the box is holding its breath again. It is poised on the edge of history. We reached for the run button, but before we press it, take a moment to feel the weight of what we have done. We have taken the chaos of the creation, the heat of the Big Bang, and the sound of the first light, and we have translated it into silence, into numbers, into memory. We have built a bridge between the fire of the beginning and the cool logic of the machine. Now we let gravity take over. Gravity doesn't care about heat or light or sound. It only cares about mass. It sees those slightly denser spots, those orange echoes, and it begins to pull. Come closer, it whispers, and the great slide towards structure begins. The fog has cleared, the sound has faded, but the echo remains. And in the dark of our simulation, that echo is about to build a world. Conclusion. Rest here for a moment. Visualize that ancient, mottled light fading into the velvet black of the present. The universe is cooling down. The noise is gone. All that is left is the potential. The particles are drifting. The grid is humming. You are safe in the silence between the stars. We have set the stage. We have tuned the orchestra, but the actors, the dark matter halos, the invisible giants that hold the galaxies, have not yet taken their places. In the next chapter, we will meet them. We will meet the ghosts that haunt the machine. We will meet the invisible weavers. Chapter 3. The Invisible Weaver. We return to the box. The simulation has been running for millions of years now. The initial burst of energy has faded. The ringing song of the beginning has quieted into a deep, heavy silence. If you were floating inside our digital universe right now, looking around with human eyes, you would be disappointed. You would see nothing. Absolute blackness. There are no stars yet to puncture the dark, no galaxies to spiral in the void, just a vast, cold ocean of emptiness. But if you could switch your eyes, if you could trade your human vision for gravity vision, the view would take your breath away. You would see that the darkness is alive. It is moving. It is swirling. It is building. Tonight, we meet the protagonist of our story, the main character who never shows their face, the architect who builds the house but never lives in it. We meet dark matter, the ghost in the room. Imagine you are in a pitch-black room. You cannot see anything, but you can feel a presence. You feel the floor tilting beneath your feet. You feel a heaviness in the air, pulling you toward the corner. You reach out, but your hand passes through nothing but air. Yet the pull is undeniable. Something massive is standing there, unseen, warping the space around you. This is the experience of the visible universe. For every gram of normal stuff, the atoms that make up you, me, the Earth, the stars, there are 5 grams of this invisible ghost. In our simulation, we represent this ghost with particles. But remember, these are not like sand or dust. They are collisionless. Visualize 2 clouds of this dark matter rushing toward each other. In the real world, if 2 clouds of rock or gas collide, they crash, they heat up, they shatter. But dark matter? Imagine 2 flocks of ghosts flying right through each other. They pass without touching. They simply glide through, their paths bending gracefully due to gravity, but never making a sound, never hitting. This is the cold dark matter model. Cold because it moves slowly enough to clump together, dark because it hides from the light. In our code, these particles are the weavers. They are threading back and forth, silently stitching the universe together. The halos. Let us watch them work. Focus on one of those orange spots from the previous chapter, one of the slightly denser regions of the early universe. Gravity is hungry here. It calls out to the surrounding dark matter. Come. Slowly, the dark particles begin to fall inward. They spiral down into the gravity well. But because they cannot collide, they don't just smash into a pile in the middle. They orbit. They swarm like bees around a hive. Millions, then billions of them buzzing around a central point, held together by their own collective weight. We call this a halo. It is not a ring like an angel's halo. It is a sphere, a great, fuzzy ball of invisible mass. In the center, it is dense and heavy. Toward the edges, it fades away like mist. These halos are the most important structures in the cosmos. Think of them as the invisible cups that will eventually hold the galaxies. Without the cup, the soup spills. Without the dark matter halo, a galaxy would fly apart. It wouldn't have enough gravity to hold on to its stars. So before we can have light, we must build the cups. The cosmic web. Zoom out now. Pull your perspective back until the simulation box looks like a small cube in the distance. What do you see? The halos are not floating randomly. They are connected. Gravity has drawn the dark matter into long, thin bridges, filaments. They stretch across the void for millions of light years. They look like the roots of a great tree or the neurons of a giant brain, glowing faintly in our gravity vision. This is the cosmic web. It is the skeleton of the universe. The voids between the filaments are growing emptier, darker. These are the deserts of space. But along the filaments, the traffic is busy. Dark matter is flowing like a river, streaming along these highways, feeding into the massive knots where the filaments intersect. At these intersections, the halos grow truly gigantic. These are the clusters, the metropolises of the dark. It is a structure of haunting beauty, intricate, delicate, massive, and it was built entirely in the dark. The trap is set. The simulation has done its first great job. The scaffolding is up. The skeleton is complete. But a skeleton is dry bones. We want a living body. We want a galaxy that shines. Floating mixed in all this dark matter is the other stuff, the minority, the baryons. That's the fancy word for gas. Hydrogen and helium, the stuff that stars are made of. Until now, the gas has just been tagging along, dragged by the gravity of the dark matter. But something is about to change. The dark matter halos have created deep gravitational valleys. Think of them as bowls in the fabric of space-time. The gas is currently floating above these bowls, but gravity is relentless. It is pulling the gas down. Fall, it whispers, and the gas obeys. But unlike dark matter, gas is not a ghost. Gas can crash, gas can splash, gas can heat up. As the gas begins to pour into these invisible dark matter cups, the era of silence is coming to an end. Friction is about to begin, and where there is friction, there is heat, and where there is heat, there will be fire. Conclusion. Drift away from the web now. Let the image of those silver filaments fade into the back of your mind. You are floating in the quiet space again. Feel the invisible support around you. Just as the dark matter holds the universe together, let the bed beneath you hold you. You do not need to do anything to be held. Gravity does the work. The weaver has finished the tapestry. The net is cast. In the next chapter, we will watch the great rivers of gas begin to flow. We will watch the universe take its first breath of fluid dynamics. We will watch the beginning of the cosmic dawn. But for now, rest in the safety of the invisible. Chapter 4: A River of Gas. We are back in the silence. The dark matter skeleton hangs in the void, a vast, invisible web stretching across the simulation box. It is majestic, it is sturdy, it is waiting. But a skeleton is not alive. It is dry, it is cold. To build a universe that breathes, to build a universe that can one day house life, we need something else. We need a medium that flows. We need the baryons. Baryon is a heavy-sounding word for something quite light. It is the scientific name for ordinary matter, the stuff you can touch, the atoms in the air you breathe, the water in the glass by your bed, the heat of the sun on your skin. All of it is baryonic matter. In the grand scheme of the cosmos, baryons are the minority. They make up only a tiny fraction of the mass, but they are the noisy minority. They are the ones that glow. They are the ones that interact. Tonight, we watch them arrive. The cosmic ocean. Imagine for a moment that space is not empty. Imagine it as an ocean. In our simulation, we switch gears now. We stop thinking about particles, like sand, and we start thinking about fluids, like water. We enter the realm of hydrodynamics. This is the physics of flow. It is the same math that describes how a river carves a canyon, how milk swirls into coffee, or how a storm cloud rolls over a mountain. In the early universe, the gas, mostly hydrogen and helium, is everywhere. It is a thin primordial mist hanging in the dark. But gravity, the relentless conductor, begins to pull. The dark matter halos, those invisible bowls we built in the last chapter, are deep and heavy. They act like drains in the cosmic bathtub. The gas begins to move. The Great Infall. Visualize a river of mist. It is streaming along the filaments of the cosmic web. It flows smoothly, guided by the gravity of the dark matter. It is a cold flow, silent and steady, pouring toward the massive knots where the galaxies will be born. It is a beautiful image, great gray rivers of hydrogen falling through the void for millions of years. But unlike dark matter, gas cannot ghost through itself. Gas has substance. Gas has friction. Imagine pouring water into a basin. When the water hits the bottom, it doesn't disappear. It splashes, it swirls, it sloshes against the sides. As the cosmic gas falls into these dark matter halos, it begins to crowd. The atoms get closer together. They bump into each other, they rub against each other. And when things rub together, they get warm. The heat of the crash. In the simulation code, the equations are changing. We are no longer just calculating position and velocity, we are calculating temperature. As the gas rushes into the halo, it hits a wall of other gas that got there first. Crash. It is not a loud crash, it is a slow, deepening pressure, a shock wave. The kinetic energy of the fall, the speed of the rushing river, is converted into heat. The gas begins to glow, not with visible light, but with X-rays. It becomes a hot, pressurized bubble filling up the dark matter halo. This is a critical moment. If the gas stays hot, it will just sit there. It will be a puffed-up cloud, too energetic to collapse, too scattered to become a star. It will remain a ghost. To make a galaxy, the gas must calm down. It must lose its energy. It must cool. The cooling flow. So the simulation waits. It watches the atoms of hydrogen dancing frantically in the heat. Occasionally, two atoms collide and release a tiny photon of light. That photon shoots away into the universe, carrying a little bit of heat with it. Bit by bit, the gas radiates its energy away. It cools, and as it cools, it loses its fight against gravity. It gets tired. It begins to sink. Imagine a hot steam cloud condensing into water droplets on a cold window. The gas in the halo condenses. It falls deeper toward the center, getting denser, getting thicker. It is settling down. But it doesn't just fall straight down. There is a rule in the universe, a stubborn law of physics called the conservation of angular momentum. It means that if something is spinning, even slightly, it wants to keep spinning, and if you shrink it down, it spins faster, like an ice skater pulling in her arms to twirl. The giant cloud of gas had a tiny, almost imperceptible rotation from the beginning, just a random little twist from the chaos of the Big Bang. But as it collapses inward, that twist becomes a spin. It begins to rotate. Gravity pulls it in. The spin pushes it out. The result is a compromise, a beautiful geometric compromise. The gas flattens. Watch it happen in your mind. The chaotic spherical cloud slowly presses itself flat. It becomes a pancake, a disk. It is rotating majestically in the dark, a great swirling whirlpool of hydrogen spinning around a dense center. This is the birth of the spiral. Most galaxies you see in pictures, the Milky Way, Andromeda, they are flat disks, and this is why. It is the natural shape of a cooling fluid spinning in gravity. It is the shape of a pizza dough spun in the air. It is the shape of Saturn's rings. It is the shape of the universe finding its balance. The friction of existence. We have arrived at a moment of profound potential. We have a dark matter halo acting as the container. Inside it, we have a spinning disk of cold, dense gas. It's like a pottery wheel waiting for the hands of the potter. The simulation is working hard now. Computing fluid dynamics is difficult. It takes a lot of processing power to figure out exactly how the gas swirls, how the eddies form, how the turbulence ripples through the disk. It's messy physics. It's the physics of weather. But looking at it now, in the quiet of our imagination, it looks peaceful, a silver plate spinning in the void. But deep inside that disk, the pressure is building again. The gas is getting crowded. It's getting clumpy. The fluid is becoming too heavy to hold itself up. The first knots are forming in the whirlpool, the first seeds of something brilliant. The river has flowed into the sea. The sea has settled into a whirlpool, and now the whirlpool is about to catch fire. Conclusion. Let your mind drift along the currents of this cosmic river. Feel the sensation of flow, of being carried gently by a force larger than yourself. You do not need to steer. You do not need to swim. The gravity of sleep is pulling you inward, toward the center, toward the calm. The gas has settled. The disk is spinning. The stage is set for the greatest magic trick the universe knows how to perform, transforming cold gas into blazing light. In the next chapter, we will strike the match. We will witness the ignition. But for now, just float. Chapter 5. The Ignition. We're hovering above the great disk. In the previous chapter, we watched the rivers of gas flow inward, settle down, and form a vast spinning plate of hydrogen. It is a masterpiece of fluid dynamics, rotating silently in the simulation box. But it is still dark. If you were to look at this galaxy now, you wouldn't see the brilliant spiral arms you are used to. You would see a shadow, a ghost galaxy. It is waiting for energy. It is waiting for a spark. Tonight, we witness the most important transformation in the cosmos, the alchemy of turning dust into light. We are going to watch the birth of the first star. The deep freeze. To understand how a star forms, we must understand a paradox. We tend to think of stars as things of fire and heat, but to make a star, you need the opposite. You need cold. Extreme, biting, absolute cold. Zoom in with me. Let us descend into one of the spiral arms of our gas disk. We are entering a molecular cloud. This is a stellar nursery. It is a dense fog of gas and dust, so thick it blocks out everything behind it. Inside, it is freezing, hundreds of degrees below zero. Why does it need to be cold? Because heat is energy. Heat makes atoms dance and push apart. If the gas is hot, it expands. It fights against gravity. But if the gas is cold, it gets sluggish. It moves slowly. It stops fighting. And that is when gravity sees its chance. The crumple. In our simulation code, the computer is constantly checking the temperature and density of every gas cell. It is looking for the tipping point. Imagine a crowd of people in a cold room huddling together for warmth. The closer they get, the tighter the huddle becomes. Gravity begins to squeeze the cold cloud. Crush. The cloud doesn't shrink evenly. It fragments. It breaks into smaller, denser clumps. These are the seeds of stars. In the simulation, we watch the numbers change. The density value climbs higher and higher and higher. The gas particles are being packed so tightly that they have nowhere left to go. They are falling freely toward the center of the clump. The squeeze becomes a crush. The crush becomes a grind. The pressure cooker. Now the paradox flips. As the atoms are squeezed together, they begin to rub against each other violently. Friction takes over. The cold cloud, crushed by its own weight, starts to heat up. But this time, the heat cannot escape. The cloud is too thick. The energy is trapped inside. The temperature rockets upward, 1,000 degrees, 10,000 degrees, 1,000,000 degrees. Deep in the heart of this collapsing knot, the pressure is becoming unimaginable. The atoms of hydrogen, simple protons, are being pushed so close together that they are starting to panic. They repel each other, pushing back with magnetic force. But gravity is stronger. Gravity is relentless. It pushes them past the point of no return. The algorithm of light. Let us pause for a moment to appreciate the code. How does a computer simulate this? We cannot model every single atom fusing. That would take a computer larger than the universe itself. Instead, the simulation uses a recipe, a star formation algorithm. It watches a region of gas. When that gas becomes dense enough, cold enough, and collapsing fast enough, the computer makes a decision. It rolls a dice. Is it time? If the probability is right, the code performs a magic trick. It deletes the gas particle, and in its place, it spawns a new kind of particle, a star particle. This particle doesn't act like a fluid anymore. It doesn't splash. It acts like a sun. Back in the nursery, the moment has arrived. The temperature in the core hits 10 million degrees. The protons can no longer resist. They smash into each other, fusing together, forging a new element, helium. In that fusion, a tiny sliver of mass is lost. It is converted into pure energy. Flash. It is a silent explosion. A shock of white light tears through the dusty cocoon. The first star has ignited. It is not a gentle candle. The first stars in the universe were monsters, massive blue giants, burning with a ferocity we can scarcely imagine. The light punches through the dark cloud, illuminating the pillars of gas from the inside out. They glow with an ethereal blue mist. The City of Lights. Now, pull back. Look at the galaxy disk again. One spark appears, then another, then 100, then 1,000,000. It looks like a city turning on its lights at dusk, viewed from an airplane window. The spiral arms are suddenly tracing themselves in fire. Blue knots of star clusters bead along the dark filaments. The galaxy is no longer a ghost. It is a pinwheel of light spinning in the void. The cosmic dawn has broken. The Dark Ages are over. For the first time in the history of our simulation, there are shadows. For the first time, there is warmth radiating out into the cold vacuum. It is a moment of triumph. The universe has woken up. Conclusion. Rest in this light for a moment. Imagine the warmth of that first star touching your face. It is the same warmth that wakes you in the morning. It is the same energy that fuels the plants and the winds of Earth. We have built the stars. But stars are not just light bulbs. They are engines. They are powerful, volatile, and doomed. They will not just sit there and shine quietly. They are going to fight back against the darkness. They are going to change the universe forever. In the next chapter, we will watch the stars take their first breath, and we will see what happens when a star dies. For now, let the galaxy spin. Let the lights flicker in the digital deep. Chapter 6. The Great Exhale. The galaxy is awake. The simulation box, once a cube of absolute darkness, is now a jewelry box. A spiral of blue and white diamonds turns slowly against the velvet black. It is a thing of order, a thing of beauty. But nature, in its infinite wisdom, does not like things to be too quiet for too long. If we let the simulation run just as it is, gravity would be too greedy. It would pull every scrap of gas into a star. The galaxy would burn through its fuel in a brilliant, feverish flash, leaving nothing behind but ash. A galaxy needs to pace itself. It needs balance. It needs to breathe. And so, tonight, we watch the galaxy take its first great breath. We watch the stars give back. The short life of giants. Zoom in again, past the spiral arms, past the clusters, to a single, massive star. It is a blue supergiant, a beast of a star, hundreds of times more massive than our own sun. It burns with a ferocious intensity. It is hungry, devouring its hydrogen fuel at a desperate pace. In the simulation, the clock is ticking. These giants do not live for billions of years like our gentle yellow sun. They live for millions, a mere blink in cosmic time. As the star ages, it grows unstable. The fusion engine in its core begins to stutter. Gravity, that relentless crusher, presses down, trying to collapse the star. The light pushes back, holding the roof up. It is a stalemate, a trembling balance between crushing weight and blinding light. And then the fuel runs out. The bloom. The light stops pushing. Gravity wins instantly. The core collapses. In the real universe, this is a violent, cataclysmic event, a supernova. But here, in the safety of our sleep, let us view it in cosmic slow motion. Imagine a flower blooming. First, a flash, brighter than 1,000,000,000 suns. For a few weeks, this single star outshines the entire galaxy. Then, the shockwave. A sphere of energy expands outward from the dying star. It is not a wall of fire. It is a wall of wind, a cosmic tsunami moving at thousands of miles per second. It crashes into the surrounding gas clouds, the very nurseries where other stars were trying to form. The pushback. This is the great exhale. In the language of astrophysics, we call this stellar feedback. It is the galaxy's way of saying enough. Watch the shock wave ripple through the gas. It pushes the mist away. It clears the room. Imagine blowing out a candle. Your breath pushes the smoke away, scattering it into the air. The supernova does the same to the nebula. It shreds the clouds. It heats them up. It pushes the gas out of the galaxy's disk and up into the halo. It stops new stars from forming. This seems destructive, doesn't it, to destroy the nursery? But it is necessary. It acts like a thermostat. If too many stars form, they explode and push the gas away, stopping the process. When the gas cools and settles back down, star formation begins again. It is a rhythm, a pulse. Star formation, explosion, silence. Star formation, explosion, silence. The galaxy is breathing, in and out, regulating itself, keeping itself alive for billions of years instead of burning out in one day. The code of chaos. Simulating this breath is one of the hardest challenges for our supercomputer. A supernova is a tiny dot compared to a galaxy, but its effect is enormous. It is like trying to simulate the weather of the entire Earth while also keeping track of a single butterfly flapping its wings in Brazil. So the simulation uses a trick. It doesn't model every single shockwave in perfect detail. Instead, when a star particle dies in the code, the computer injects a burst of thermal energy into the surrounding cells. It heats them up artificially. It tells the gas, move, expand, fly. And on the screen, we see the result. The smooth gas disk becomes bubbly. It looks like Swiss cheese or the foam on top of a cappuccino. Huge cavities open up where stars have exploded, creating bubbles of hot, thin gas. It creates texture. The galaxy is no longer a perfect, smooth painting. It is a rugged, scarred, beautiful landscape. The gift of gold. But the explosion leaves something else behind, something precious. Inside that dying star, before it collapsed, it was a factory. It was forging elements: carbon, oxygen, silicon, iron, gold. When it exploded, it didn't just push the gas away, it enriched it. Imagine a painter flinging gold dust into the wind. The shockwave carries these heavy elements out into the void. It mixes them into the clouds. This is the chemical enrichment of the universe. Before this moment, the universe was boring. It was just hydrogen and helium. You couldn't make a rock. You couldn't make water. You couldn't make a bone or a leaf or a blood cell. But now, the dust is full of possibility. Every atom in your body, the iron in your blood, the calcium in your teeth, the carbon in your genes, was forged inside one of these blue giants. You are made of this explosion. You are the echo of a supernova. The fountain. Watch the gas now. Some of it has been pushed so hard it flies right out of the galaxy. It shoots up like a fountain, arcing high above the spiral disk. It cools in the darkness of the halo. It slows down, and then, slowly, gently, it begins to rain back down. It is a recycling system. The galaxy breathes the gas out, cleans it, mixes it with stardust, and breathes it back in to make new stars. Generations of stars, each one richer, more complex than the last. The sun is a third or fourth generation star. It is made of recycled breath. Conclusion. Feel the rhythm of this cycle, the tension of the buildup, the release of the explosion, the quiet settling of the dust. It is a heartbeat. The universe is not static. It is a living, churning, breathing thing. Even destruction is part of the creation. Even the end of a star is the beginning of you. Let yourself breathe in time with the galaxy. Inhale, pulling the energy in. Exhale, letting the tension go. The galaxy is calm now. The shock waves have faded. The dust is settling. But in the center of the galaxy, something else is waking up. Something darker, something deeper, something that does not breathe out, but only breathes in. In the next chapter, we must journey into the dark heart. We must meet the monster. Chapter 7: Monsters in the Dark. We are traveling inward. Leave the glittering spiral arms behind. Leave the nurseries of the blue giants and the quiet drifts of the outer rim. We are diving toward the center of the galaxy. As we move deeper, the stars get closer together. The night sky is no longer black. It is a blaze of white light. Thousands of stars are packed into a space that would usually hold only one. It is a crowded, chaotic downtown of cosmic energy. But right in the center, at the very pivot point around which the entire galaxy turns, there is a shadow. It is a place where the math breaks, a place where space and time are twisted into a knot so tight that nothing, not even light, can untie it. Tonight, we meet the silence at the center of the storm, the supermassive black hole. The Great Anchor. In the center of almost every large galaxy in our simulation and in the real universe, there sits a monster. But let us not think of it as a monster. That implies malice. Let us think of it as an anchor. It is millions, sometimes billions of times the mass of our sun. It is the gravitational pin that holds the galaxy together. Without it, the center would not hold. In our simulation, this object is a sync particle, a tiny dot in the code with an insatiable hunger. It sits there, dark and quiet for eons. It waits. The meal. But eventually, gas wanders too close. Maybe a cloud is nudged by a passing star. Maybe two galaxies collide, sending fresh rivers of hydrogen pouring toward the core. The gas begins to spiral in. Imagine water circling a drain, faster and faster. As the gas gets closer to the event horizon, the point of no return, it is moving at nearly the speed of light. And just like in the star-forming clouds, friction takes over. The gas rubs against itself. It screams with energy. A glowing ring forms around the shadow, an accretion disk. It is the brightest object in the universe. This is the great paradox of the black hole. The black hole itself is invisible, but the meal it is eating, it shines brighter than 1 trillion stars. When a black hole is feeding like this, we call it a quasar, a lighthouse in the deep. The jet. But a black hole is a messy eater. It doesn't swallow everything. As the magnetic fields twist and tangle in the spinning disk, they create a slingshot. Whoosh! 2 massive beams of plasma are launched from the poles of the black hole. They shoot out at 99.9% of the speed of light, piercing through the galaxy and erupting into the void beyond. These are the jets. They are like swords of light stabbing through the darkness. They are thousands of light years long. In our sleep story, imagine them as fountains, great silent geysers of energy spraying out from the center, carrying heat and momentum far, far away. The gardener. Why does the simulation need this? Why do we program this violence into our peaceful code? Because without the black hole, the galaxy would die of gluttony. If the gas just kept falling in, the galaxy would grow too big. It would form too many stars. It would become a bloated, shapeless blob. The black hole acts as a gardener. It prunes the galaxy. The jets heat up the surrounding gas. They push it away. They tell the galaxy, stop, that is enough. They shut down star formation. They keep the galaxy in check. They enforce a cosmic diet. This is called quenching. It is a profound thought. The most destructive object in the universe is also the protector of its structure. Without the black hole to stop the growth, the elegant spiral arms would never survive. The beauty requires the beast. The quiet after. Eventually, the food runs out. The gas is consumed or blown away. The jet fades, the accretion disk cools and darkens. The lighthouse turns off. The black hole returns to sleep. It sits there, invisible once again, surrounded by the swirling stars. It is a dormant giant waiting for the next meal, waiting for the next merger. In our simulation, the sync particle stops growing. The numbers stabilize. The galaxy continues to spin, safe and structured, held in the balance between gravity and feedback. Conclusion. There is a comfort in this heaviness. Imagine the black hole not as a danger, but as a center of gravity, a place of absolute certainty. In a universe of drifting dust and fleeing light, here is something that does not move. Here is something that holds on. Let yourself sink toward that center, not into the dark, but into the calm stability of it. You are anchored. You are held. In the next chapter, we will leave the single galaxy behind. We will zoom out, further than we have ever gone before. We will see the pattern that connects all things. We will see the web. Chapter 8. The Cosmic Web. We are rising. We leave the black hole in the dark. We rise above the accretion disk, above the blue stars, above the spiral arms. The galaxy shrinks beneath us. It becomes a disk, then a coin, then a dot. We keep pulling back. The simulation box expands around us. We are no longer looking at a single city of stars. We are looking at the map of the world. And suddenly, the pattern reveals itself. We are looking at the cosmic web, the spongy universe. It does not look like a random scattering of sand. It looks organic. It looks alive. It looks like the interior of a sponge, or the neurons inside a brain, or the veins in a leaf. The universe is built of threads. Vast filaments of dark matter and gas stretch across the dark, millions of light years long. They are glowing faintly with the light of thousands of tiny galaxies that cluster along them like dewdrops on a spiderweb. Everything is connected. The galaxy we just built, with its spiral arms and its black hole, is just a tiny speck of light flowing along one of these great rivers. It is moving toward a node, a place where filaments cross. These nodes are the clusters. Imagine a swarm of thousands of galaxies, all dancing around each other, bound by the gravity of a massive dark matter heart. This is the metropolis. The great silence, the voids. But between the filaments, there is the other thing, the voids. Look at the empty spaces in the web, great spherical bubbles of nothingness. These are the cosmic voids. They are the loneliest places in existence. Some of them are hundreds of millions of light years across. If you were floating in the center of a void, you would see almost no stars. The sky would be perfectly black. You would be utterly alone. But in our sleep story, this is not a scary loneliness. It is a peaceful one. It is room. It is space. It is the universe taking a deep breath and holding it. The simulation shows us that most of the universe is empty. Matter is rare. Light is rare. The default state of reality is quiet, spacious, dark. There is plenty of room for you to dream here. The match. This structure, the web and the void, is the greatest triumph of our simulations. When we run our code on the supercomputers, simulations with names like the Millennium Run or Illustrious, this is what comes out, a web. And when we point our telescopes at the real sky and map the positions of millions of real galaxies, what do we see? We see the same web. The computer dreaming in its server room and the telescope staring into the deep, they see the same picture. It means we understand something fundamental. It means the recipe we whispered in Chapter 1, gravity, expansion, dark matter, was right. We have captured the shape of the cosmos in a box of silicon. The zoom. It gives you a strange feeling, doesn't it, to see the universe from this distance. From here, the violent supernovas are invisible. The screaming black holes are silent. The spinning galaxies are just stationary dots. All the chaos, all the fire, all the noise, it vanishes into the elegance of the pattern. It reminds us that perspective changes everything. Up close, life is messy and loud, but step back far enough and it becomes a beautiful, orderly design. Conclusion. Float here among the filaments. Trace the lines of light with your mind. You are looking at the nervous system of eternity. You are small, yes, but you are part of the web. You are made of the atoms forged in the nodes, flowing along the rivers of gravity. You are connected. We have built the universe. We have seen the beginning, the middle, and the structure. But there is one problem left, one nagging question. When we look too closely, the simulation starts to blur. In the next chapter, we will talk about the limits of our vision. We will talk about the pixelation of reality. Chapter 9. The Infinite Zoom. We have spent the night flying through the vast, open cathedrals of the cosmic web. We have seen the universe at its grandest scale, a lattice of light stretching across the dark. But now, let us try to do something else. Let us try to look closer. Imagine you are floating above one of those digital galaxies. It is beautiful, swirling with blue stars and dust lanes. You want to see who lives there. You want to see a planet. You want to see a mountain. You want to see a blade of grass. So you command the simulation to zoom in. The galaxy expands. You fly past the spiral arms. You approach a star cluster. You get closer and closer. And then suddenly, the beauty dissolves. The star is not a sphere of boiling plasma. It is a blocky, jagged square. The gas cloud is not a mist. It is a collection of sharp triangles. You have hit the wall. You have found the pixel. Tonight, we explore the boundary of our power. We explore the resolution of reality. The grain of the canvas. In art, if you look too closely at a painting, the illusion disappears. The smile of the Mona Lisa becomes a collection of cracked paint strokes. The impressionist landscape becomes a mess of dots. A simulation is no different. We call this resolution. It is the size of the smallest brush we can use. To simulate the entire universe with its billions of light years, we have to make a sacrifice. We cannot model every atom. We cannot even model every star. In our massive box, a single particle might represent 1,000,000 suns. If you zoom in on that particle, there is nothing inside it. It is just a number, a coordinate, a mathematical placeholder. This is the pixelated universe. It is a humbling thought. In our digital cosmos, entire solar systems, with all their planets, moons, and potential life, are smoothed over. They are invisible. They exist only as averages inside a larger block of code. The zoom-in trick. But scientists are stubborn dreamers. We want to see the details, so we use a technique called the zoom-in simulation. Imagine you have a map of the world. It shows continents and oceans, but no cities. So you cut out a tiny square of the map, say just the coast of Italy, and you draw a new map of just that square. Now you can draw the cities, you can draw the roads. We do this with the universe. We pick one interesting halo from the cosmic web, we delete everything else, and we rerun the simulation for just that halo, using all our computing power on a single spot. Suddenly, the pixels get smaller. Now we can see the gas swirling into the center. We can see the turbulence. We can see individual supernova explosions. But the trap remains. If we zoom in to see the star, we lose the galaxy. If we zoom out to see the web, we lose the star. We cannot have it all. Not yet. The subgrid world. So what happens in the spaces we can't see? What happens inside those blocky pixels where the physics is too small to simulate? This is where the scientists have to become storytellers. We use something called subgrid physics. It is a way of guessing. We tell the computer, I cannot see inside this box, but I know that gas usually turns into stars when it gets cold. So let's assume that 1% of the gas in this box turns into stars every million years. We write a rule to replace the detail. We paint over the pixel with an assumption. It sounds like cheating, doesn't it? But it is the only way. It is how we bridge the gap between the infinite complexity of nature and the finite power of our machines. The fuzzy edge. Think about your own vision for a moment. Look at your hand. You see skin, you see lines, you see fingerprints, but you do not see the cells. You do not see the bacteria living on your thumb. You do not see the molecules vibrating. Your eyes have a resolution limit too. Your brain is running a subgrid model of your own hand. It shows you the smooth surface, not the chaotic atomic dance underneath. Does that make your hand less real, or does it just make it manageable? Simulations teach us that reality is a matter of scale. What is true at the level of a galaxy is different from what is true at the level of an atom. Conclusion. Drift back from the pixelated edge. Do not worry about the things we cannot see. The universe is built of layers, and we are only looking at one layer at a time. There is a peace in acceptance. We accept that our model is grainy. We accept that our vision is blurred, because even through the blur, we can see the shape of the truth. In the next chapter, we will learn how to tune the instrument. We will learn how scientists twist the knobs of the universe until it sings in the right key. We will learn about the art of calibration. Chapter 10. The Tuning of the World. We are standing at the control panel of the universe. Imagine a mixing board in a recording studio. Rows and rows of dials, sliders, and switches. But instead of controlling volume or bass, these dials control the laws of nature. One dial says gravity strength, another says dark energy density, another says star formation efficiency. Our simulation is running, but it doesn't sound quite right yet. The galaxies are forming, but they look a little wrong. Maybe they're too puffy, maybe they're spinning too fast. Maybe they're too blue or too red. The universe is out of tune, so the scientist reaches out. With a trembling hand, they touch the dial, and they turn it. Tonight, we explore the secret art of calibration, the moment where science meets intuition. The knobs of nature. You might think that physics is fixed, that gravity is gravity, and light is light, and you would be right. The fundamental laws are set, but in a simulation there are free parameters. These are the numbers we're not quite sure about, the numbers that describe the messy stuff. For example, how much energy does a dying star actually release into the gas around it? We know it's a lot, but is it enough to blow the gas out of the galaxy, or just enough to stir it up? We don't know the exact number, so it becomes a knob. We run the simulation with the knob set to 1. The galaxy blows itself apart. Too strong. We turn it down to 0.5. Ah, the galaxy breathes. It forms a spiral. It looks like the Milky Way. Just right. The cosmic cheating? Some people call this tuning. Others, more cynically, call it cheating. Are we discovering the universe, or are we just manufacturing the answer we want? If I keep turning the knobs until the painting looks like a photograph, have I learned how to paint, or have I just traced the lines? It is a deep philosophical question, but consider this. The universe is tuned. The real constants of nature, the speed of light, the strength of the electron, the expansion rate, are set to very specific values. If they were slightly different, atoms wouldn't hold together, stars wouldn't burn, you wouldn't be here. By tuning our simulation, we are trying to find a combination that unlocks reality. We are trying to crack the code. The symphony. When the calibration is finished, something magical happens. We stop touching the dials, we step back, and we let the machine run. And suddenly, the universe begins to sing in harmony. The galaxies in the simulation match the galaxies in the sky. The number of stars matches, the amount of gas matches, the distribution of dark matter matches. It is a moment of profound validation. It means that our subgrid models, our guesses, our approximations were good guesses. We captured the essence of the process. It's like tuning a radio. Static, static, static. Music, clear, beautiful music coming from the void. The unseen variables. But we must always be careful. Maybe there is a knob we forgot to turn. Maybe there is a force we didn't include. Magnetic fields, turn them up. Cosmic rays, add them in. Dark matter temperature, adjust it slightly. The simulation is never finished. It is always a work in progress, a perpetual rehearsal. Conclusion. Feel the satisfaction of the click. The dial settles into place. The universe stabilizes. The image sharpens. There is a comfort in order, a comfort in knowing that things fit together, that the chaos can be tamed if you just find the right frequency. You are tuned to the frequency of sleep now. Your breathing is calibrated. Your mind is slowing down. But what happens when the machine gets it wrong? Chapter 11. Glitches in the glass. We have built a beautiful machine. We have tuned it. We have watched it spin. But sometimes the machine lies. Sometimes we look at our simulated universe and then we look at the real night sky and they do not agree. There is a mismatch, a glitch in the glass. For a scientist, this is the most exciting moment of all. Success is boring. Success means you already knew the answer. But failure? Failure is a whisper from the unknown. Failure says, look here, you missed something. Tonight, we examine the broken pieces. We look at the missing satellites and the cores that should be cusps. We look at the mysteries that keep the midnight scientists awake. The missing satellites. Imagine the Milky Way, our home. In our simulations, a galaxy as big as ours should be surrounded by a swarm of smaller galaxies, like bees around a hive. The code predicts hundreds of them, tiny dwarf galaxies buzzing in the dark matter halo. But when we look up with our telescopes, we don't see hundreds. We see a few dozen. Where are they? This is the missing satellites problem. Did the simulation get it wrong? Is our theory of dark matter broken? Or are they there but invisible? Maybe the little galaxies exist, but they are dark. Maybe they never managed to light their stars. Maybe they are ghost galaxies made entirely of dark matter, floating silently around us right now, unseen by human eyes. It is a haunting thought that we might be surrounded by invisible neighbors. The cusp and the core. Here's another glitch. In the simulation, the center of a dark matter halo is sharp. It is a cusp. The density shoots up to a spike right in the middle. But when we observe real dwarf galaxies, their centers look soft. They have a core. The dark matter is spread out, like a flat plateau. Why is the simulation so sharp and reality so soft? Maybe the gas did something we didn't expect. Maybe the supernova explosions were so violent that they actually pushed the dark matter away, smoothing out the center. Or maybe dark matter isn't what we think it is. Maybe it's fuzzy. Maybe it interacts with itself. The glitch is forcing us to think harder. It is forcing us to rewrite the code. The too big to fail. And then there are the galaxies that are too big to fail. The simulation predicts massive, dense subgalaxies that simply must have stars in them. They are too big to remain dark. Gravity is too strong, but we don't see them. It is a paradox, a hole in our understanding. These glitches are not errors in the computer, they are errors in our imagination. The universe is more complex, more subtle, and more strange than our equations can capture. The beauty of the flaw. Think of a Persian rug. The weavers often include a deliberate flaw, a tiny mistake in the pattern to show that only the divine is perfect. Our simulations have flaws too, but they are not deliberate. They are the fingerprints of our humanity. They remind us that we are still learning. If the simulation was perfect, the mystery would be over. We could pack up our telescopes and go home. But the glitches keep us searching. They keep us looking into the dark, asking why. Conclusion. Do not be afraid of the mistake. In your own life, the glitches, the plans that went wrong, the surprises, the detours, are often where the real story happens. The smooth path is forgettable. The broken path is where you find the flowers growing in the cracks. The universe is full of cracks, and the light gets in through them. We are almost at the end of our journey. We have built the cosmos. We have found the flaws. But there is one final, dizzying question we haven't asked yet. If we can simulate a universe, if we can build a world of light and gravity inside a computer, could this be a simulation? Could we be the pixels? In the next chapter, we will open the final door. We will step into the simulation hypothesis. Chapter 12. The Simulation Hypothesis. We have spent the night playing God. We built a box. We filled it with laws. We sprinkled it with dust. We watched it bloom into a galaxy of spiral arms and blue stars. We saw how the code, simple, logical lines of math, can create a world that looks hauntingly like our own. And now, as the night deepens, the inevitable question arrives. The question that hangs at the very edge of science and philosophy. If we can do it, if we, with our clumsy metal computers and our limited brains, can build a universe, then has someone else already done it to us? Tonight, we step through the looking glass. We ask the question, are we the dreamers, or are we the dream? The staircase of reality. Think about how far we have come. 50 years ago, our video games were two white rectangles batting a square ball back and forth. Pong. Today, we have virtual worlds so rich, so detailed that people get lost in them. We have suns that set in real time. We have leaves that rustle in the wind. We have digital characters that look you in the eye. Imagine what we will have in another 50 years, or 1,000, or 1,000,000. If a civilization survives long enough and their computers keep getting better, eventually they won't just simulate games, they will simulate history. They will simulate minds. This is the argument. It suggests that if it is possible to simulate consciousness, then advanced civilizations will run billions of these simulations, ancestor simulations, curiosity simulations. And if there are billions of simulated worlds and only one real base reality world, then statistically, where are you? The odds say you are in the code. Does the idea scare you? It shouldn't. Look at the evidence we found tonight. Remember the pixel? We learned that if you zoom in too far, the simulation blurs. Quantum mechanics tells us that our real universe is pixelated too. There is a smallest possible distance, the Planck length. You cannot zoom in further. It is the resolution limit of our reality. Remember the speed limit? In our code, information can only travel so fast. In our universe, light has a speed limit. Nothing can go faster. It is the maximum processing speed of the cosmos. Remember the Big Bang? The moment the simulation started? It looks a lot like someone pressed a button. Maybe the glitches we talked about, the missing satellites, the weird expansion rates, are just optimization tricks, shortcuts to save memory in the great server farm in the sky. The meaning of the dream. But here's the most important thought. If this is a simulation, does it matter? If you kiss someone you love, does your heart beat any slower because it's a simulated heart? If you stub your toe, does it hurt any less? If you feel awe when you look at the stars, is that awe fake? No, the feeling is real. The experience is real. Whether reality is made of atoms or algorithms, it is still real to you. Think of a dream. When you are in it, you feel fear, joy, love. It is a world generated entirely by your brain. It is a simulation, but while you are in it, it is your life. Perhaps the universe is just a shared dream, a very stable, very detailed, very long dream. And if there is a programmer, a creator, what are they like? They are not a cruel tyrant. Look at the rules they wrote. They wrote a universe that loves light. They wrote a universe that builds complexity from chaos. They wrote a universe that allows for eyes to see it and minds to wonder about it. They wrote a universe where eventually the dust wakes up and starts telling stories. Maybe the purpose of the simulation isn't to test us or to judge us. Maybe the purpose is simply to be, to explore all the possibilities of existence, to see what happens when you mix gravity and time and love. Conclusion. So as you lie here, floating in the possibility of the code, feel safe. If you are a simulation, you are a masterpiece. You are the result of billions of years of calculation. You are the part of the program that gets to feel the blankets and the pillow and the peace of the night. The computer is reliable. The power is on. The simulation is stable. You can close your eyes. The world will still be here when you wake up. The save file is secure. In the final chapter, we will let the simulation run on its own. We will walk away from the console. We will enter the eternal rehearsal. Chapter 13. The Eternal Rehearsal. The screen is glowing softly in the dark room. On it, the universe we built is humming. The galaxy is rotating with majestic slowness. The spiral arms are drifting. The black hole is sleeping. The gas is breathing. It is perfect. But our work is done. We have built the world. We have tuned the laws. We have explored the glitches and the ghosts. It is time to let it go. Imagine the scientist standing up from the chair. They stretch, their silhouette framed by the light of the digital cosmos. They do not turn the computer off. You never turn the universe off. They simply step away. The loop. They walk out of the room, closing the door gently behind them. Inside the machine, the universe continues. It doesn't need us watching it to exist. It runs on its own logic now. Tick, the stars orbit. Tick, the planets spin. Tick, a comet drifts through the dark. It is an eternal rehearsal, a performance for an empty room. Science is a loop. We observe the real world, we build a simulation to understand it, and then we look back at the real world with new eyes, round and round. But tonight, the loop is open. We are stepping off the wheel. The fade. Visualize the simulation box one last time. It is drifting away from you, smaller, smaller, a glowing cube in the infinite dark. It becomes a star. It becomes a pixel. It becomes a memory. The silence of the void is wrapping around you like a heavy blanket. The grid lines are fading. The equations are dissolving. There is no more math. There is no more code. There is only the deep, rhythmic breathing of the night. Final sleep. You are part of the universe. Whether it is made of atoms or data, you belong to it. You are made of the same stuff as the stars. You follow the same laws as the galaxies. You are a small, quiet simulation of the cosmos, resting in the dark. Gravity holds you. Expansion gives you room. Time waits for you. Drift now. The scientists are sleeping, the computers are humming, the stars are burning, and you are drifting. Safe, quiet, home. Good night, traveler. Good night, architect. Good night.
Welcome back to the Midnight Scientists. Wherever you are in the world, whether you are nestled beneath a pile of blankets, curled gently on a favorite chair, or simply floating in that soft, spacious pause between the day's obligations and the deep rest you deserve, I'm grateful you are here. Before we begin our slow drift into the realms of science, let me invite you to just settle. Feel the weight of your body, the quiet presence of your breath. Let the distant echoes of the day soften and dissolve. There is nowhere you need to be and nothing you need to do, except simply be present with the sound of my voice. Tonight, we will journey inward, not through the landscape of memory or dreams, but through the astonishing, silent architecture of your own self. If you enjoy these peaceful explorations of the cosmic and the microscopic, where wonder meets stillness, a simple like on the video and a quiet subscription to the channel is the kindest gesture. It helps us find other minds seeking this calming blend of science and serenity, and for that, I offer my deepest thanks. Chapter 1: The Quiet Promise of Five Senses. Now, as you begin your descent into calm, consider a very old idea, a comfortingly tidy, ancient notion, an idea that has traveled across 2 millennia to whisper its certainty into modern textbooks. It is the idea of the five senses. Imagine yourself standing in the gentle, hazy sunlight of ancient Greece, perhaps in the Lyceum, a philosophical sanctuary where the great mind of Aristotle once walked. Around 2,300 years ago, give or take a philosophical scroll, this singular, colossal thinker looked upon the world and sought to categorize human experience. He observed the flicker of light entering the eyes, sight. He observed the vibration of air against the eardrum, hearing. He noted the chemical detection of molecules in the air, smell, and on the tongue. And finally, he categorized the pressure and texture felt upon the skin, touch. 5. A perfect, pleasing number. A number that aligns so beautifully with the 5 fingers on a hand or the 5 points of a star. It was neat, it was complete, it was wonderfully, logically Greek. And because Aristotle was Aristotle, a mind of towering genius, his classification stuck. Drift with me now and visualize this idea traveling like a smooth, polished stone rolling through history. It tumbles from ancient scrolls into the heavy, leather-bound texts of the medieval era. It finds a welcome home in the illuminated manuscripts of the Renaissance. It crosses oceans and centuries, finally nesting itself deep inside the primary school books of your own childhood. The list was easy to memorize, easy to teach, and deeply satisfying in its perceived symmetry. 5 doors to experience the universe. No more, no less. But like many beautiful, tidy ideas inherited from antiquity, it turns out to be only the opening chapter of a much, much longer book. The simple truth is that the human body, your body, as you lie here, is a far more complex and nuanced instrument than any philosopher could have fully mapped with only observation and logic. Aristotle, for all his brilliance, did not have access to the soft glow of fMRI brain scans. He could not chart the tangled, whispering pathways of the vagus nerve. He did not know that tiny, shimmering crystals floating in fluid deep within your inner ear could orchestrate your stability against the ceaseless pull of gravity.
He did not know the precise mechanism by which you can close your eyes and still, with perfect accuracy, touch your fingertip to your nose. These two are sensations. They are real, measurable, deeply important signals that flow continuously through the dark rivers of your nervous system. Yet they find no home in the tidy, classical list of 5. So the question lingers, why did that number hold on for so long? Perhaps it is due to what scientists call historical inertia. Once an idea gains enough momentum, it becomes self-sustaining, repeated in classrooms and embedded in culture until it feels less like a concept and more like a simple, undeniable fact. Culturally, we crave simplicity. We prefer a small, manageable catalog of experiences. 5 senses are far easier to discuss, illustrate, and absorb than, say, the 17, 20, or even 30 distinct sensory systems that modern neuroscientists now debate. The sheer complexity of defining a sense is part of the challenge. Is a sense defined by a unique kind of receptor, by a distinct neural pathway, or must it rise to the level of conscious awareness? Scientists still debate the technicalities, but the consensus is profoundly clear. The traditional 5 are merely the headliners, the loud, vibrant soloists in a vast, hidden orchestra. Beneath the surface of your conscious attention, the quiet, tireless ensemble is always playing. Consider for a moment balance. You are not aware of it most of the time. You simply stand, or sit, or walk. But without a dedicated, unique system operating deep inside your head, the vestibular system, you would be a wobbly, confused marionette. This is not touch, nor is it sight. It is a standalone, gravity-tuned system silently working in the background, a gyroscope keeping your world from spinning out of control. Or consider pain. It is so often lumped in with touch, but the two are profoundly different. Touch tells you that something is there. Pain tells you that something is wrong. Pain possesses its own highly specialized nerve endings, known as nociceptors, or, politely, the body's internal alarm system. They are tuned to detect damage, crushing pressure, scalding heat, corrosive chemicals. They dispatch urgent, unmistakable messages up the spinal cord to the brain, prioritizing survival over comfort. Without this essential sense, you would never know to pull your hand from a hot stove or rest a sprained ankle. Pain is a ferocious, difficult teacher, but it is an essential one. And then there is temperature. Feeling the difference between an icy breeze and a warm stone is not merely a variation of touch, it is the detection of energy itself. You possess dedicated thermoreceptors in your skin and deep within your organs that sense changes in thermal energy, both on the surface and within your core. That sudden, exhilarating jolt of cold water, or the deep, radiating warmth of a fireplace, these are not part of the classic 5, yet they are undeniably, measurably a sense. Even in the darkest room, with your eyes closed, you never have to guess where your body parts are. You simply know. This profound awareness, which we call proprioception, tells your brain about the tension in your muscles, the angle of your joints, and the continuous location of your limbs in 3-dimensional space. It is a full-body, continuous GPS that is so reliable you rarely give it a second thought. It is the silent, invisible choreographer of all your movements, from the simplest stretch to the most complex dance. And finally, consider the deep, internal dialogue, the sense of what is happening inside your private hidden realm. This is interoception. It is the awareness that signals hunger, the tension of a full bladder, the flutter of the heart during a sudden scare,
or the slow, rhythmic expansion of your lungs. These sensations do not register on the skin or on the tongue. They are gathered by a vast, intricate network of internal sensors, silently reporting on your deepest physiological state. They are crucial for your survival, for maintaining your well-being, and for shaping your emotional world. When you begin to combine these fundamental, dedicated systems, proprioception, vestibular sense, nociception, pain, thermoception, temperature, and interoception, with the classical 5, the picture of human sensation expands dramatically. The 5 senses are like the bright, bold headlines on a newspaper. The hidden senses are the rich, vital stories unfolding on the deeper pages. The full sensory picture is expansive, textured, and quietly extraordinary. It is a subtle humility that comes with this realization. So much of your experience, so much of your effortless navigation of the world relies upon systems you never consciously acknowledge. The body, in its wisdom, handles the intricate details so the conscious mind can focus on the big picture. But for tonight, we will invite your conscious mind to gently linger on these details. We will slow down and listen to the subtle pulses, the silent balances, the hidden stretches, and the essential internal signals that make you wonderfully, intricately you. So, as you rest, imagine standing in a dark room. Your eyes are softly closed. Yet, without hesitation, you lift your hand, and with serene accuracy, your fingertip meets the tip of your nose. It is a feat of invisible, internal choreography. Proprioception is about to reveal its secrets. Drift with me now, and let us peer through the veil of the obvious into the inner map of the body. The tiny, dedicated sensors in your muscles and joints are ready to begin their nightly report. They are preparing a continuous, real-time map of your position. But what happens when that map is suddenly wiped blank? How does the mind navigate a body it can no longer feel? We will find out as we descend further. Chapter 2: The Invisible Navigator. Drift deeper now if you are able, and hold that image we closed with, the soft darkness, the eyes closed, and the quiet certainty of your fingertip finding your nose. It is such a simple, perfect act. It is a moment of quiet, invisible choreography, a profound testament to the body's innate, unquestioning self-knowledge. You do not search, you do not grope, you just know where your hand is and where your nose is, and your entire system brings the two together with a grace that defies conscious effort. This seamless, moment-to-moment self-awareness is the domain of proprioception. The name itself whispers its purpose. It comes from the Latin roots, proprius, meaning one's own, and perceptio, meaning perception. Proprioception is, quite literally, the perception of one's own self, but not in an abstract philosophical way. It is the deep, cellular knowledge that your foot is beneath you, your head is tilted slightly to the left, and the muscles in your shoulder are holding your weight at a precise angle. It is your brain's internal GPS system, a continuous, full-body weather report for your structure, always updated, always active, and almost always unnoticed. Unlike sight, which drinks in light from the external world, or hearing, which captures the air's vibrations, proprioception is an entirely internal sense. It is your body's relentless way of keeping track of itself, a silent, dedicated bookkeeper recording every shift, stretch, and strain. The very reason you have likely never stopped to think about this sense is because it works so flawlessly, so reliably, that it has rendered itself gloriously forgettable. It is the backstage crew that never misses a cue, ensuring the star performer, you, can move with effortless confidence. To understand this quiet miracle, we must journey inward, deep within the protective sheaths of your muscles, joints, and tendons. Here, nestled among the fibers, are the specialized microscopic sensors that power this internal map. They are the twin guardians of movement, the muscle spindles and the Golgi tendon organs. Imagine the muscle spindles as miniature, finely tuned scrolls wrapped around the individual muscle fibers. Their singular purpose is to monitor length. As you perform a stretch, say reaching languidly for a pillow, the spindle stretches too. It instantly fires off signals up your spinal cord, broadcasting a message to the brain. Alert, we are lengthening over here. We are getting longer. This constant communication allows your nervous system to know with exquisite precision the exact length and speed of change in every muscle, ensuring your movements are fluid and your muscles are not overextended. If a muscle is stretched too quickly, the spindle triggers an immediate, automatic reflex contraction, the swift, protective tightening that helps prevent injury. This is the same, almost electrical jolt that causes your knee to kick when a doctor taps the right spot. It is the body's instant safety net. Now, meet the Golgi tendon organs, the quiet cousins. These sensors are situated right where the muscle fibers meet the tough, silvery tendon, the anchor point to the bone. Their specialty is not length, but tension. They are the internal strain gauges, measuring precisely how much force is being generated during a contraction. When you lift a heavy mug or push against a stubbornly closed door, the Golgi tendon organs are weighing in, reporting the exact load. If the tension becomes dangerously high, these organs send a powerful signal that inhibits the muscle's activity, forcing it to briefly relax. It is the body's built-in structural integrity check, preventing a tear or an overuse injury before the damage can even begin. Now, meet the Golgi tendon organs, the quiet cousins. These sensors are situated right where the muscle fibers meet the tough, silvery tendon, the anchor point to the bone. Their specialty is not length, but tension. They are the internal strain gauges, measuring precisely how much force is being generated during a contraction. When you lift a heavy mug or push against a stubbornly closed door, the Golgi tendon organs are weighing in, reporting the exact load. If the tension becomes dangerously high, these organs send a powerful signal that inhibits the muscle's activity, forcing it to briefly relax. It is the body's built-in structural integrity check, preventing a tear or an overuse injury before the damage can even begin. Together, the spindles and the Golgi organs operate in a sophisticated, continuous dialogue, a ballet of tension and release. One monitors how far the muscle goes, the other monitors how hard the muscle pulls. This rich, real-time data stream is fed primarily to a region of your brain called the cerebellum, the silent maestro of coordination. The cerebellum integrates this proprioceptive input with signals from your inner ear and your vision, constantly fine-tuning your posture and coordinating your movements. This is why you can walk down uneven stairs, adjust your posture while sitting, or type complex words without glancing at the keyboard. It is a system of perpetual micro-adjustment. Think of the simple act of walking in the dark. You are not consciously commanding each muscle, you are simply moving. Your proprioception is the silent guide, navigating the terrain beneath you by sending continuous updates about the angle of your ankle, the flex of your knee, and the pressure beneath your foot. Without this sense, even the most mundane movement would require your full, exhausting, conscious attention. And this leads us to one of the most compelling and sobering stories in neuroscience, the account of Ian Waterman. In his early 20s, Ian contracted a rare viral infection that tragically targeted and destroyed the large sensory nerve fibers in his body, specifically those responsible for proprioception and much of his sense of touch from the neck down. His motor nerves remained intact, his muscles were still strong. He retained the ability to move, but he had lost the knowledge of movement. Visualize the moment Ian awoke. He was not paralyzed in the traditional sense, yet he felt utterly disconnected from his own body. He described the sensation not as pain, but as an internal absence, a terrifying vacuum where his self-knowledge once resided. It was as if his body had become an unfamiliar instrument, a disconnected object floating just beyond his grasp. When he tried to move an arm, he could send the motor command, but no confirming signal, no proprioceptive receipt ever returned. His brain had become a driver in a pitch-black car with no dashboard lights. He pressed the gas, but had no feedback to know if he was moving or where he was going. Ian could not sit upright, could not stand, and could not move his limbs unless he looked directly at them. To function, he had to undertake the painstaking process of remapping his entire existence. He learned to substitute the speed of light, his vision, for the slowness of internal sensation. Walking became a conscious, visually guided chore. He had to look at his feet, think about the movement, and meticulously command each step, treating his own legs as external objects. If the lights were suddenly turned off, he would immediately collapse because the invisible scaffolding of his proprioception was gone, and his visual substitute vanished with the darkness. His case is a living, breathing testament to the fragility of our effortless embodiment. It underscores how deeply the feeling of being you, the certainty of your own physical presence, relies on this tireless, subterranean stream of sensory data. Through sheer, grueling willpower and immense concentration, Ian Waterman learned to live again. He rebuilt his movement, not on feeling, but on sight and intention, demonstrating the astonishing adaptability of the human brain to forge new, difficult pathways when the easy ones fail. His struggle is a quiet reminder to the rest of us. The simple act of standing on 2 feet, of pouring a glass of water without spilling, of simply adjusting your posture beneath the covers is, in its essence, a miracle of neurological coordination. The good news is that for most of us, proprioception is not a fading light, but a sense we can actively refine. Training this sense is common in the world of specialized movement. Think of the serene focus of a Tai Chi practitioner, moving with slow, deliberate precision, or the astonishing accuracy of a gymnast performing a complex flip in midair, knowing exactly when to tuck and when to unfurl their body to ensure a perfect landing. These feats rely on proprioception dialed to an expert, almost superhuman level. Even the simple practice of yoga or stretching is, in part, a proprioceptive workout. When you settle into a deep, sustained pose, you are not merely elongating your muscles. You are gently challenging your muscle spindles and Golgi tendon organs. You are teaching your nervous system to trust the stretch, to recalibrate the threshold for alarm, and to become more comfortable and more aware of its full range of motion. It is a process of internal negotiation, softly asking your body to feel more, to trust deeper, and to become more acutely aware of its own geometry. As you lie here now, perhaps you can perform a small internal experiment. Wiggle your toes very gently and notice the sensation. Feel the subtle tension in your calf muscles as you do so. Without moving, consciously bring your attention to the angle of your head on the pillow. Are you absolutely certain of your position? That quiet, unshakable certainty is the whispered voice of proprioception. It is the continuous, loving effort of your body to ensure that you always know where you are and what you are doing, even in the stillness of the deepest night. It is a core pillar of your selfhood, connecting the physical dimensions of your form to the conscious experience of your mind. Without it, the self fractures. With it, every gentle movement is a symphony. But the body's internal reporting system is not limited to position in space. There is another, even deeper sense that governs the hidden world of your internal state, the rhythm of your heart, the fullness of your lungs, the churn of your hidden organs. This is the sense that tells you not where you are in the room, but how you are faring within the secret machinery of life itself. It is the sense of interoception, and it holds the keys to your deepest feelings and your subtle physical truths. As you begin to feel the weight of your own body, anchored and known by proprioception, let your mind turn to the most delicate sensation of all, the awareness of your own heartbeat. This deep internal rhythm is the basis of self-knowledge. But how clearly can you hear its music? And what other secrets does this inner landscape hold? We will listen closer in the next chapter. Chapter 3: The Deep Dialogue of the Internal Self. Close your eyes now, if they are open, and sink deeper into the stillness. Proprioception has anchored you in space. Now we turn our awareness to the inner landscape, the boundless, intricate world contained beneath the surface of your skin. Here, there is a quiet language always being spoken, one that precedes words, visuals, or even conscious thought. It is the steady murmur of your heartbeat, the subtle tightening in your stomach before you realize you are hungry, the slow, involuntary expansion of your lungs as you take a deep, contented breath. These are not mere thoughts or reactions. They are sensations, urgent and subtle messages flowing from the body's core to the mind's command center. This silent stream of bodily awareness is governed by a profound and remarkable hidden sense: interoception. If proprioception is your internal GPS for your limbs, interoception is your internal dashboard for your organs. It is your ability to perceive the physiological state of your entire body, how things are going inside. Are you warm? Are you cold? Is your bladder full? Is your blood sugar dipping? Is your heart racing? Interoception gathers this continuous, real-time data about the condition of your tissues, fluids, and internal organs, sending updates to your brain without ever needing your permission or your conscious participation. You have experienced this sense countless times, yet rarely pause to name it. That dry tickle in your throat that demands a sip of water. The thrilling, unsettling sensation of butterflies in your stomach before a big presentation. The pervasive feeling of fatigue that settles over you after a long, draining day. These are all undeniable, felt messages from within, facilitated by this dedicated internal monitoring system. At the heart of interoception lies a beautifully complex web of sensory neurons that monitor internal conditions throughout the body. These receptors reside not just in your skin, but deep inside your heart, your lungs, the muscular walls of your gut, and your bladder. They are the tireless scouts of your inner domain. The information they gather is routed through an elaborate highway of nerves, most famously the magnificent vagus nerve, the Latin word for wandering. The vagus nerve is the longest cranial nerve, a majestic, branching bundle of fibers that originates in the brainstem and wanders all the way down, connecting the brain to almost every major internal organ. It is the primary postal service for the brain-body axis, picking up messages about inflammation, fullness, and microbial activity from your gut and delivering them straight to the brain. Once these deep internal signals reach the brain, they are primarily processed in a remarkable structure tucked away in the temporal lobe, the insular cortex, or simply the insula. Imagine the insula as the brain's specialized integration center, a quiet, softly glowing core where the raw physical data of interoception is translated into a felt, subjective experience. It's the part of you that takes a racing heart and a churning stomach and says, "Ah, yes, this feels like anxiety," or "This deep, satisfied warmth feels like contentment." It builds an integrated, continuous picture of your internal landscape, forming the deep bedrock of emotional self-awareness. What makes interoception so fascinating is that it does not often shout. Most of the time, it whispers. The signals are constant, but they rarely rise to the level of vivid, full-blown conscious awareness unless there is a significant change, extreme hunger, sudden pain, or the urgent need for hydration. For the most part, interoception is a background hum, a quiet operating system keeping the brain informed without causing a fuss. Yet this quiet hum is central to one of the body's most critical functions, homeostasis. Homeostasis is the physiological state of internal balance, the delicate stability that keeps your blood sugar, temperature, fluid levels, and heart rate within the narrow, life-sustaining range. Interoception is the early warning system that detects any drift from this sweet spot. When your blood sugar begins to dip, the body nudges the brain with subtle hunger signals. When you become too warm, the system triggers the automatic cascade of sweating and vascular dilation. Without this sense, you would be like a highly sophisticated spacecraft with no fuel gauges or temperature monitors, still flying, but moments away from catastrophic system failure. The mind-body loop. One of the most profound roles of interoception is its function as the bridge between the body and the mind. Emotions, it turns out, are deeply, inextricably intertwined with these internal signals. The racing heart during fear, the sensation of tightness in the chest during sadness, the fluttering gut during excitement, these are not mere literary metaphors. They are genuine, physiological sensations that your brain detects via interoception and then labels as an emotional state. Some researchers even propose that emotions begin as interoceptive experiences. Your brain detects a sudden physiological shift in your body, rushes to interpret it, and then assigns it a psychological category. This rapid pulse and breathlessness must be excitement, or this sinking feeling in my abdomen must be sadness. This brain-body loop is constant and bidirectional. Your body informs your mind, and your mind can, in turn, influence your body. Thinking about a difficult memory can cause your shoulders to tense or your stomach to clench. Actively relaxing your breathing can send calming signals through the vagus nerve to your heart, slowing its rate and inducing a state of physiological calm. It is an elegant, adaptive feedback system, and the more keenly attuned your interoceptive skills, the more precisely you can navigate the subtle shifts in your mood, energy, and overall well-being. However, not everyone is equally attuned to this inner dialogue. Some individuals are highly interoceptive. They can instantly detect subtle changes in their heartbeat, register the first hint of dehydration, or sense emotional shifts just as they begin to surface. They are highly sensitive listeners to their own internal broadcast. Others are less tuned in. Their internal signals may need to be much louder or more persistent before they capture conscious attention. This can make it difficult to recognize when they are truly tired, genuinely hungry, or on the verge of emotional overwhelm, as the body's subtle whispers are often missed. The clinical spectrum reveals even greater complexity. Individuals struggling with anxiety disorders may experience heightened interoception that is also distorted. A normal fluctuation in heart rate, a completely harmless signal, is amplified by the brain, misinterpreted as a sign of imminent danger or a medical emergency, sending the anxiety spiral into overdrive. Conversely, some people with eating disorders may exhibit disrupted interoception, leading to a profound difficulty in accurately recognizing or responding to internal signals of hunger or fullness. Understanding interoception, therefore, becomes a powerful tool for self-regulation and mental health. The gateway of the breath. Of all the doors into interoception, the breath is perhaps the most powerful and accessible gateway. Unlike most internal processes, the beating of your heart, the churning of your gut, the movement of your blood, breathing possesses a unique duality. It is both automatic and controllable. Your body will continue to breathe without you giving it a single thought, yet you can take conscious control of its pace and depth at any given moment. This dual nature makes the breath the perfect anchor for internal awareness. When you shift your attention to the breath, following the cool air entering the nostrils, tracing the gentle rise and fall of the abdomen, noticing the subtle pause before the exhale, you are consciously amplifying your interoceptive sensitivity. This is why nearly every meditative or contemplative tradition throughout history features breathwork. It is not a mystical technique, but a physiological override. By slowing and deepening your breath, you activate the parasympathetic nervous system, the rest and digest branch, which sends calming, soothing messages back down the vagus nerve to the internal organs. This process not only reduces the physiological signs of stress, but heightens your awareness of them, providing a sense of grounding and internal stability. It is the closest thing the body has to a manual override button for its nervous system rhythm. As you lie here, simply notice the sensation of breathing. Do not try to change it. Just observe the effortless flow. Feel the subtle shift in your posture, the faint cooling on your upper lip with each exhale, the quiet work of the diaphragm. This focused, gentle attention is the heart of interoceptive practice. Interoception is the foundational sense that gives you the lived feeling of being in a body, not just inhabiting it, but profoundly experiencing it. It translates chemical gradients, fluid pressures, and neural signals into a subjective truth that guides your survival, fuels your emotions, and defines your sense of well-being. It may not be as dramatic as the blinding light of sight or the complex tapestry of sound, but without the deep, quiet knowledge of interoception, the self would be adrift, untethered from its own biological reality. You may not hear it often, but this internal world is always speaking. And when you learn to listen, even just a little, the whispers can tell you everything you need to know. You are still, you are breathing, you are aware of your inner rhythm. But how does this quiet, internal awareness interact with the relentless pull of the physical world? In the next chapter, we will turn our attention to the silent, crystal-powered structures deep within your skull, the engineers of your equilibrium, that work tirelessly to ensure that even in the deepest rest, you do not fall. Chapter 4: The Crystal Garden of Equilibrium. You are still. Your proprioception holds the map of your resting body. Your interoception monitors the quiet rhythm of your inner organs. But even in this deepest stillness, your body is engaged in a silent, continuous struggle against the universal constant, gravity. You are not tipping over. Your head is held steady. If you were to gently shift your weight, your body would instantly compensate, making dozens of tiny, unnoticed corrections. This astonishing feat of continuous, three-dimensional balance is orchestrated by one of the most mechanically elegant hidden senses of all, a marvel of bioengineering tucked deep inside the hardest bone in your skull, the vestibular system. Imagine your inner ears, those two tiny, coiled structures. We often credit them only with the sense of hearing, the capacity to translate air vibrations into sound, but their role in survival extends far beyond listening. They house the engineers of your equilibrium, the quiet geniuses responsible for keeping you upright, oriented, and stabilized against the ceaseless pull of the earth. The vestibular system is your body's built-in gyroscope. It is a microscopic, fluid-filled complex dedicated to detecting two critical factors: head movement and head orientation relative to gravity. This complex is composed of two main types of structure, each designed to monitor a different kind of movement: the semicircular canals and the otolith organs. Don't let the names create complexity. Visualize the elegance of their design. First, the semicircular canals. Imagine three minuscule, curved tubes on each side of your head, arranged at right angles to one another, much like the axes of a gyroscope. One canal monitors movement in the up and down direction, like nodding yes. One monitors side-to-side movement, like shaking no. And the third monitors tilting, like touching your ear to your shoulder. These canals are filled with a specialized fluid called endolymph. When you turn or rotate your head, the fluid, due to inertia, momentarily lags behind the movement of the canal walls. This relative shift in fluid gently brushes against a group of tiny, delicate sensors, microscopic hair cells lining the walls of the canals. This bending of the hair cells is instantly converted into an electrical signal, which is then sent through the vestibular nerve to your brainstem and cerebellum. This signal doesn't just tell your brain that you moved, it tells it precisely how you moved, the direction, the speed, and the rotation of your head. It is a real-time, high-definition rotational sensor, powered by the simplest principles of liquid physics and biological transduction. Next, we move to the otolith organs, the utricle and the saccule, which are concerned with linear motion and gravity. These two small structures are sensitive not to rotation, but to acceleration, moving in a straight line like a car taking off or slowing down, and static tilt, the unchanging posture of your head relative to the ground. Inside the otolith organs lies a remarkable substance, a dense, jelly-like membrane embedded with countless tiny, shimmering crystals made of calcium carbonate. These are the otoconia, or ear stones. Visualize a garden of minute, shimmering crystals suspended in a delicate gel. When you tilt your head, say from the vertical position to horizontal on your pillow, gravity tugs on these dense crystals. The shifting weight of the otoconia bends the underlying sensory hair cells, and the brain receives an immediate update on your head's absolute position. When you accelerate forward or backward, the crystals also lag behind, similar to the fluid in the canals, sending a signal about that linear motion. Between the rotational input of the canals and the linear/gravity input of the otoliths, your brain receives a continuous, comprehensive, three-dimensional orientation report. It integrates this data with proprioception, where your body is, and vision, where the horizon is, to create your unwavering sense of where you are in the world. The mystery of dizziness and motion sickness. The elegance of this system only truly reveals itself when it is disrupted. This disruption manifests as dizziness or motion sickness, sensations born from a fundamental sensory mismatch. Think of the childhood game of spinning in circles. When you stop, the world continues to whirl. This is not imagination. It is your vestibular fluid still sloshing in the semicircular canals. Your eyes report a static, stopped world, but your inner ears continue to send high-volume signals to the brain that you are violently in motion. Your brain receives these conflicting messages and, unable to reconcile the visual stability with the inner motion, interprets the chaos as disorientation, or what we call dizziness. It is a temporary mutiny between your senses. This sensory conflict is also the root cause of motion sickness. Picture yourself reading a book in the backseat of a car. Your eyes are locked on the stationary page. Your visual system reports stillness, but your vestibular system feels every turn, bump, and acceleration, reporting continuous motion. The brain receives this intense disagreement and, in an ancient evolutionary interpretation, concludes, "Something is wrong. My senses are lying to me. This could be poison." The body's evolutionary response to consuming a neurotoxin is, naturally, to clear the decks, hence the feeling of nausea. Your body is overprotective, assuming any major sensory disagreement is a threat, and trying to purge the perceived poison. This is why simply looking out the car window at the distant, stable horizon helps. It aligns your visual input with the motion felt by your inner ear. The senses agree, yes, we are moving, and the brain relaxes the alarm. In more persistent cases, this elegant system can be thrown into disarray by physical issues. Vertigo, a more severe and persistent sensation of spinning, often occurs when the tiny otoconia crystals from the otolith organs become dislodged and float into one of the semicircular canals, where they do not belong. This condition, known as benign paroxysmal positional vertigo, BPV, makes specific head movements, like rolling over in bed or tilting your head back, trigger sudden, intense spinning, because the misplaced crystals are inappropriately bending the hair cells, sending false signals of movement. Thankfully, physical therapists often treat this with simple, elegant repositioning maneuvers, such as the Epley maneuver, which use gravity to gently coax the crystals back into their rightful chambers. It's like gently shaking a snow globe until the flakes settle back onto the ground. Adaptations and limits. On a day-to-day basis, your vestibular system is working with quiet, invisible dedication. It is the reason you can walk across uneven cobblestones, stand on one leg to tie your shoe, or even simply maintain an upright head posture against the constant downward pressure. The boundaries of this system are tested by specialized activities. Figure skaters and acrobats train relentlessly to suppress the reflexive dizziness that spinning causes. In their case, the brain learns to prioritize visual and proprioceptive input over the confusing, sloshing signals from the inner ear. And then there are the challenges of the final frontier, space. Astronauts in zero gravity face an unprecedented vestibular crisis. Without the constant, reliable tug of gravity, the otolith organs essentially lose their primary anchor. They can no longer tell the brain which way is up or down. This often leads to severe space motion sickness during the first few days of a mission. The brain, confused by the floating crystals and the absence of a gravitational baseline, struggles to process the conflicting signals. Fortunately, the human brain is remarkably neuroplastic. After a period of intense sensory confusion, it adapts, learning to rely more heavily on vision and proprioception to navigate the weightless environment, eventually re-establishing a new, gravity-free sense of orientation. Your sense of balance, therefore, is not a simple state. It is an active, continuous process, a quiet, three-way dance between the fluid mechanics of your inner ear, the subtle tension in your muscles, and the processing power of your brain. Next time you tilt your head to listen more intently or simply step off a curb without a second thought, pause for a moment to acknowledge the tiny engineers in your skull. The sloshing fluid, the tumbling crystals, and the constant, silent transmission of data are working in perfect, tiny harmony to keep you grounded, stable, and beautifully oriented in the great, ceaseless theater of your life. But now, let us turn to the sense that defines the limits of safety and the boundaries of wellness, the sense that protects you, even when it demands your attention with an unmistakable intensity. We will turn to the necessary protective signal known as pain. Your body is balanced, your internal map is stable, but what happens when that map highlights a critical, urgent flaw? Pain is not the enemy, it is the essential guardian. But why is the sensation of pain so variable, so flexible, and so easily influenced by the mind? We will explore the specialized sensors of damage in the next chapter. Chapter 5: The Essential Guardian, the Sense of Pain. Pain. The word itself carries a weight of aversion, of urgency. Of all the senses we possess, pain is the least welcome guest, the one we spend the most effort trying to avoid or eliminate. It is rarely appreciated in the moment, and yet, paradoxically, it is one of the most vital, foundational, and highly specialized senses in the human body. To understand pain is to recognize that it is not simply an unfortunate feeling, but a full-fledged sensory modality, a guardian, a teacher, and an essential messenger. Drift with me now, and let us approach this difficult sense not as an enemy, but as a complex neurological marvel. To define pain as a sense is to acknowledge that it has its own dedicated system of detection, transmission, and interpretation. You feel pain because certain sensory receptors in your body are tuned specifically to detect damage or the imminent threat of damage. These specialized detectors are called nociceptors, from the Latin nocere, meaning to hurt. Visualize these nociceptors as microscopic, highly selective security alarms scattered across every millimeter of your skin, nested within your muscles, joints, tendons, and lining many of your internal organs. Unlike the gentle touch receptors we discussed earlier, nociceptors are deliberately fussy. They ignore mild pressure, gentle warmth, or subtle movement. They only react when the stimulus is extreme enough to cause tissue injury. Nociceptors come in different varieties, each specializing in a unique flavor of trouble. Some are tuned to mechanical damage, responding only to intense crushing, cutting, or pinching pressure. Others react to thermal extremes, screaming at temperatures that are searingly hot or painfully cold. A third group is sensitive to chemical signals, the inflammatory compounds, acids, and transmitters released by damaged cells after an injury or infection. When a nociceptor is activated, Say, when you touch a hot stove, it generates an electrical impulse. This impulse travels rapidly along dedicated nerve fibers, the fast, sharp A delta fibers for immediate acute pain, and the slower, throbbing C fibers for dull, lingering pain through the peripheral nerves, up the spinal cord, and into the brain. There, in complex regions like the somatosensory cortex, the insula, and the anterior cingulate cortex, the signal is interpreted and processed, transforming a simple electrical discharge into the subjective, inescapable experience we call ouch. The flexibility of the alarm. What makes pain scientifically fascinating and sometimes frustrating is its remarkable plasticity. Pain is not a fixed measurement. It is not simply proportional to the tissue damage. Rather, it is an interpretation constructed by the brain, heavily modulated by context, mood, memory, and expectation. Think of the classic example of the soldier in combat who sustains a severe wound but feels no pain until hours later when the danger has passed. In that moment of intense threat, the brain, prioritizing survival above all else, releases powerful natural opioids, effectively turning the volume knob of pain down to zero. The nociceptors are firing, but the central nervous system is choosing to filter the signal. Later, in the safety of a field hospital, the cognitive framework shifts, the danger subsides, and the pain signal is finally allowed to flood through. Conversely, consider a tiny paper cut. Objectively, the tissue damage is minuscule, yet the pain can feel offensively dramatic. This disparity is partly due to nerve density. Your fingertips, lips, and face are packed with sensory receptors and nociceptors because they are critical for exploration, communication, and feeding. A high concentration of alarms in a small area ensures a disproportionately large sensory broadcast. This means pain is profoundly contextual. If you sustain an injury while feeling safe and supported, the experience is often less intense than if the same injury occurs while you are anxious, stressed, or fatigued. Your mood, your history, and your predictions about the injury's outcome all shape the final subjective experience. The brain is not merely receiving data, it is telling a story about that data, and that story is infinitely flexible. Acute versus chronic, the two faces of pain. Scientists categorize pain into two broad families, each serving a drastically different purpose. Acute pain. This is the pain of immediate injury, the pulled muscle, the brief sting of a burn, the sudden throbbing of a hammer blow to the thumb. It has a clear, identifiable cause, is usually proportional to the damage, and resolves when the tissue heals. Acute pain is protective, vital, and functional. It enforces rest, encourages caution, and compels you to treat the injury, thereby promoting healing. Chronic pain. This is a much more complex and difficult phenomenon. It persists long after the tissue damage has healed, often defined as lasting more than 3 to 6 months. Or it may arise with no clear physical cause at all. Chronic pain is not a symptom, it is a condition unto itself. In these cases, the nervous system has become maladaptive. The volume knob has been effectively stuck in the high alert position. The nociceptors and the spinal cord pathways may have become hypersensitive, continuously transmitting pain signals even when there is nothing left to protect. Chronic pain often involves deeper changes in the brain's structure, reshaping the connections responsible for processing emotion, memory, and self-awareness, coloring every aspect of a person's life. The absence of the alarm. To understand the necessity of pain, we must consider its absence. Imagine a life without the alarm system, a life where touch exists but pain is impossible. This is the reality for individuals with congenital insensitivity to pain, CIP, a rare genetic disorder. On the surface, it sounds like a liberation. No headaches, no toothaches, no agony from a minor fall. But in reality, it is profoundly dangerous. Children born with CIP often accumulate horrific injuries because they lack the essential feedback loop that compels caution. They may suffer severe burns without noticing the heat, repeatedly fracture limbs from normal play, or allow infections to rage unchecked because there is no pain signal to drive them to seek help. Their lifespan is often tragically shortened. Pain, for all its fierce intensity, is what keeps us intact. It is the body's ultimate expression of self-care. Its absence proves that survival hinges on the unpleasant yet essential warning that damage is occurring. The phantom and the emotional echo. Pain also reveals the profound truth that the ultimate location of the sensation is the brain, not the injured tissue. The phenomenon of phantom limb pain illustrates this with eerie clarity. An amputee may experience intense, often burning or cramping pain emanating from a foot or hand that is no longer physically present. The limb is gone, yet the pain is devastatingly real. This happens because the brain's internal body map, the homunculus we will explore later, has not erased the missing limb. Neurons that once processed input from the limb are now firing spontaneously or are being invaded by neighboring cortical regions, leading the brain to generate the perception of pain from the missing body part. It is a sensory illusion, a broken feedback loop where the brain's expectation clashes with reality. Furthermore, the sense of pain is not restricted to physical damage. Your brain treats emotional pain with surprising literalness. Studies using fMRI scans reveal that the same brain regions activated by a scalding burn, the insula and the cingulate cortex, also light up when a person experiences social rejection or profound grief. The phrase, "a broken heart," is therefore not just a poetic flourish. It is a description of a genuine, shared neurological pathway. The brain registers a threat to social connection or self-identity with the same urgency it reserves for a physical wound. As you rest now, acknowledge the subtle presence of this essential guardian. Any lingering stiffness in your neck, a dull ache in a joint, or the gentle, distant memory of an old injury, these are residual messages from a system that is continuously scanning for your safety. Pain is a difficult, fierce form of interoception. It is the loud, urgent alarm designed not to punish, but to force attention and demand rest. It is the sensory underpinning of caution, healing, and self-preservation. Though we seek comfort, it is the pain pathways that ultimately keep the entire structure functional, durable, and wonderfully, fiercely alive. But now, let us move from the fierce intensity of the alarm to the quiet, pervasive awareness of the environment that surrounds and penetrates you, the subtle, essential detection of thermal energy. The alarm has sounded, and the body has noted the threat. Now, how does the body regulate itself against the silent, invisible flow of energy? The sense of temperature is more than just hot and cold. It is the detection of energy itself, and it is governed by microscopic molecular gates. We will explore the thermal deception in the next chapter. Chapter 6. The Energetic Veil, Thermoception. As you rest, shielded by blankets and warmed by the quiet engine of your own metabolism, consider the silent, continuous communication happening between your body and the environment. This dialogue is orchestrated by the hidden sense of thermoception, your extraordinary ability to feel and regulate temperature. Thermoception is far more fundamental than simply telling you to put on a coat or open a window. It is the core mechanism that allows your body to detect energy, the subtle, pervasive flow of heat and cold that determines the stability of all living systems. Without it, you could not maintain the delicate internal balance required for life, and you would be perilously unaware of threats from frostbite or heat stroke. Drift with me now, and let us explore the molecular elegance of this thermal sense, a system based on tiny, guarded doorways within your cell membranes. The detection of temperature begins in specialized sensory nerve endings within your skin and, profoundly, deep within your body core. These receptors are not passive thermometers. They are sophisticated molecular sensors, primarily belonging to a family of proteins called transient receptor potential channels, or TRP for short. Visualize these TRP channels as microscopic, specialized gates embedded in the surface of your nerve cells. Each gate is tuned to a specific thermal range. Some channels, like TRPV1, are activated only by intense heat, responding to temperatures above 42 degrees Celsius. This is the scalding threshold, the temperature at which the heat becomes painful. Other channels, like TRPM8, are activated by cold, opening when temperatures drop below about 26 degrees Celsius. This is the refreshing jolt of cold water or the sensation of cool air. When the environmental temperature meets the specific threshold of a TRP gate, the gate swings open, allowing a rush of ions to enter the nerve cell. This creates an electrical signal, an urgent message that travels to your brain, translating the environmental energy directly into the subjective feeling of warmth or chill. The deception of flavor. What is truly fascinating is that these thermal gates are chemically cross-wired. They don't only respond to actual temperature, they can be fooled by certain molecules. Consider the cooling sensation of menthol in mint or chewing gum. Menthol does not actually cool your body, it is merely a chemical that binds to the TRP8 cold receptor. The cold gate swings open, sends its signal to the brain, and you experience the undeniable feeling of coolness even though no actual thermal change has occurred. It is a convincing, refreshing deception. The opposite occurs with capsaicin, the compound that gives chili peppers their fiery heat. Capsaicin binds to the TRPV1 heat-sensitive channel, the same one that screams at a scalding burn. The brain receives a high alert signal, interpreting it as if your mouth were literally on fire. Your body responds accordingly. You sweat, your nose runs, and you experience the uncomfortable flush of intense, perceived heat. This is your thermoception system responding to a perfectly legal culinary thermal illusion. The core thermostat, the hypothalamus. While the skin reports on the surface temperature of the world, your most vital thermal monitoring is done deep within your core. Here, a small, mighty structure in your brain, the hypothalamus, acts as the master thermostat of your body. The hypothalamus continuously monitors the temperature of the blood flowing through it, comparing this core temperature against a precise set point, typically around 37 degrees Celsius. This is the ideal operating temperature for the vast network of proteins and enzymes that govern your biological functions. When your core temperature begins to drift, even by a fraction of a degree, the hypothalamus initiates automatic, non-conscious responses to bring things back into balance. If you are too hot, for example, during vigorous exercise, The hypothalamus triggers the dilation of blood vessels near the skin, vasodilation, and activates sweat production. This allows heat to radiate away from the body, cooling you down. If you are too cold, e.g., stepping out on a brisk night, the hypothalamus triggers the constriction of blood vessels near the skin, vasoconstriction, to minimize heat loss, and initiates shivering, rapid, involuntary muscle contractions designed to generate internal heat. You may not be consciously tracking the exact temperature of your blood, but your interoceptive system, guided by the hypothalamus, is constantly managing this life and death thermal equilibrium. The paradox of fever. This thermal control center becomes particularly dramatic during a fever, which reveals the brilliance of the body's defensive strategy. When your immune system detects an invading pathogen, a virus or bacteria, it releases chemical messengers called pyrogens. These pyrogens travel to the hypothalamus and effectively raise the temperature set point. Imagine your internal thermostat is suddenly bumped from 37 to 39 degrees Celsius. Even though your blood temperature hasn't changed yet, your body believes it is now 2 degrees Celsius too cold. This sensory mismatch is what triggers the feeling of chills and shivering. You wrap yourself in blankets, your muscles contract violently, and you seek external heat. The body is frantically working to reach the new, artificially high set point, which is an environment less hospitable to the invading microbes. A fever is not an accident. It is a deliberate, energy-intensive defense mechanism orchestrated by the thermoceptive system. Once the body has fought off the infection, the pyrogens clear and the hypothalamus resets the set point back to 37 degrees Celsius. Now the current 39 degrees Celsius feels dangerously hot. This is when the fever breaks. The body initiates massive sweating and vasodilation to rapidly shed the excess heat, leaving you drenched and finally cooling down. Thermal comfort and emotional connection. Thermoception also weaves itself into our emotional and psychological experience. We often equate physical warmth with social warmth, with comfort, safety, and affection. Psychologists have found that simply holding a warm drink can temporarily make people feel more generous, trusting, and empathetic toward others. The sensory experience of warmth acts as a primal, comforting shortcut in the brain, linking physical temperature to emotional climate. Conversely, intense cold can be associated with emotional distance or isolation. We speak of receiving a cold shoulder or feeling frozen out, language that reflects the deep, intuitive connection between our thermal experience and our social reality. As you drift now, notice the comforting warmth around you. This is not just a passive state. It is an active signal that your system is in balance, that your internal thermostats are operating smoothly, and that your microscopic thermal gates are maintaining their peace. Every breath you take, every tiny shift in blood flow beneath your skin is part of this silent, continuous thermal management. The sense of temperature is a gentle, pervasive reminder that you are a living, responsive organism, constantly negotiating the subtle, energetic boundary between your inner world and the outer environment. It is the wisdom that ensures you are safe, stable, and perfectly positioned for rest. In the next chapter, we will return to the realm of movement, but explore how the brain's map of the body, its physical self-image, can become profoundly confused, creating a vivid, felt reality that is entirely an illusion. Your body's map is usually accurate, but what happens when the physical territory vanishes? The brain is stubborn. It clings to its internal representation of the self, sometimes generating sensations from a limb that no longer exists. We will explore the eerie persistence of the body image in the next chapter. Chapter 7: The Illusion of Flesh, Phantom Limbs and Body Maps. As you lie in the quiet certainty of your own body, take a moment to confirm your edges. You know where your hand rests. You feel the presence of your feet. This feeling of body ownership, the unwavering sense that this is mine and I am here, is so fundamental that we never question it. It is the core architectural pillar of the self. But what if that pillar suddenly vanished? What if the physical territory was erased, yet the feeling of it remained, vivid and often agonizingly real? Drift with me now into one of the strangest, most poignant neurological phenomena, phantom limb syndrome. This is the profound, confusing experience where an individual who has lost a limb, an arm, a leg, a hand, continues to feel sensations, sometimes excruciating pain, emanating from the missing body part. It is a surprisingly common experience. Estimates suggest that up to 90% of people who undergo amputation will experience some form of phantom sensation. These sensations are not vague whispers. They can be incredibly detailed. The feeling of a wedding ring still on the missing finger, the urge to scratch an itch on a lost foot, or the intense, burning pain of a clenched fist where a hand no longer exists. To understand this illusion, we must revisit the concept of the brain's internal blueprint of the body. Neuroscientists call this the body schema or the body matrix. Imagine your brain contains a meticulously detailed three-dimensional map of your physical form. Every nerve ending, every muscle, every joint is represented by a cluster of dedicated neurons within the sensory and motor areas of the cortex. This map is not etched in stone. It is flexible, constantly updated by the continuous feedback loops of touch, proprioception, and vision. When a limb is amputated, the physical source of the input, the nerve endings, the muscle spindles, the skin receptors, is gone. The brain suddenly receives no feedback from a large region of its map. The dedicated cortical territory for that missing hand or foot does not simply vanish or go dark. It becomes starved of its expected sensory input. This absence creates a kind of neurological vacuum. The brain, abhorring a gap, does what it always does. It improvises. The neurons that once monitored the missing limb remain active, sometimes firing spontaneously, or, more commonly, they begin to be invaded or taken over by the sensory input from neighboring body parts on the cortical map. For instance, the cortical area representing the face is often located immediately adjacent to the area representing the hand. When the hand's input is lost, touching the patient's face might sometimes be interpreted by the brain as a sensation or pain coming from the missing hand. The brain is misinterpreting the input due to the reorganization of its map.
The phantom limb, therefore, is not a memory or an emotional projection. It is a neurological artifact, the persistence of the brain's internal model long after the physical reality has changed. It is the stubbornness of the map, overwhelming the evidence of the territory. The problem of the frozen phantom. One of the most agonizing aspects of phantom limb pain is the feeling that the missing limb is held in a painful, unnatural position, often cramped, twisted, or clenched tightly into a fist. This sensation stems from a fundamental sensory mismatch. When you decide to move your arm, your brain sends a motor command down the motor nerves. When the arm is present, the proprioceptors and touch sensors send back an immediate sensory confirmation. Command received, movement executed, fist unclenched.
This completes the feedback loop. In the case of the phantom limb, the brain sends the command to unclench the imaginary fist, but because the limb is gone, no sensory confirmation returns. The loop is broken. The brain concludes by default that the command failed, and the phantom limb remains painfully stuck in its cramped position. It is a terrifying sensory illusion built on the failure of feedback. The mirror solution. The understanding of this broken loop led to one of the most innovative and revealing treatments for phantom limb pain, mirror therapy. Developed by neuroscientist V.S. Ramachandran, the technique is deceptively simple yet brilliantly effective. The patient places their existing healthy limb inside a specialized box with a mirror, arranged so that the mirror reflection makes it appear as though the missing limb is present. When the patient moves their intact limb, they see the reflection of the missing limb moving in perfect synchrony. The brain receives powerful, clear visual confirmation that the command to move has been successfully executed. The visual signal, being the loudest and most persuasive sense, overrides the missing proprioceptive feedback. The brain is momentarily tricked. It sees the phantom hand unclench, stretch, and relax. And astonishingly, for many patients, this sensory reconciliation leads to an immediate, profound relief from years of agonizing phantom pain. The brain, having been provided with a coherent visual narrative, updates its internal map and releases the neurological tension. This technique is a powerful demonstration of multisensory integration and the malleability of the self. It shows that your sense of body ownership is not an immutable fact, but a flexible model that can be instantly warped, broken, or repaired by changing the blend of sensory input. Expanding the boundary of self. The phantom limb illustrates the deep commitment of the brain to its own map, but sensory illusions show how easily the boundaries of the self can be manipulated even in a healthy individual.
Recall the rubber hand illusion we mentioned earlier. A person's real hand is hidden, and a fake rubber hand is placed in view. When both hands are stroked simultaneously, the brain, seeking consistency between what it sees, vision, and what it feels, touch, integrates the rubber hand into its body schema. People feel the rubber hand is their own, demonstrating that the self can extend and incorporate inanimate objects based on synchronized sensory input. More dramatically, the reverse can also happen. In a rare condition called somaparaphernia, usually following brain damage, patients may not only deny their disability, but also deny ownership of a perfectly healthy, functioning limb. They may insist that the arm lying beside them belongs to the doctor, a sister, or a roommate. They are intellectually aware the arm is attached, but the feeling of ownership, the anchor of the sense of self, has vanished due to a glitch in the brain's map. These extraordinary conditions, from phantom limbs to rubber hands to disowned arms, are not just clinical oddities. They are profound philosophical windows into the architecture of consciousness. They teach us that the feeling of being embodied is not a static reality, but a continuous, active construction, an ongoing agreement between dozens of sensory inputs. Your brain is not a passive recipient of signals. It is a master editor and storyteller, constantly weaving fragments of sensation, memory, and prediction into the cohesive, localized experience of you. Your body as you lie here is not just a container for your consciousness. It is the narrative scaffolding upon your sense of self is built, constantly confirming and reconfirming its presence, its position, and its ownership. The phantom reminds us that even when the body changes, the brain's dedication to its own internal story of you remains fiercely, beautifully persistent. But the body also has a sense that guides the rate and pace of action, a quiet governor of energy output, telling you not where you are, but how much effort you are expending. The body is mapping itself, even in absence. Now let us consider the hidden gauge that determines whether you push harder or stop to rest. The sense of effort is not just about muscle fatigue. It is a negotiation between mind and body, influenced by belief, context, and motivation. We will measure the wisdom of effort in the next chapter. Chapter 8, The Governor of Energy, the Sense of Effort. You are resting, but even in this deep stillness, your body maintains a complex internal economy. It manages resources, tracks energy expenditure, and continuously makes decisions about when to press on and when to conserve. This process is governed by a fascinating and often overlooked hidden sense, the sense of effort, or the perception of exertion.
Unlike pain, which screams for attention, or touch, which is immediate and localized, the sense of effort operates like a quiet governor on your motor systems. It is the internal gauge that measures how hard you are working, how sustainable your current activity is, and ultimately what your capacity for further action might be. It is the silent negotiation between your intention and your physiology, and it governs every single action, from carrying a heavy grocery bag to sustaining a long thought. Drift with me now, and let us explore how this subtle sense is constructed, revealing that effort is not just a physical truth, but a neurological interpretation. The experience of effort is not rooted in a single receptor, but is a profound blend of signals integrated across multiple hidden senses and cognitive systems. It is both sensation and perception, raw data combined with a complex, subjective interpretation. Raw physiological data. This comes from the body's hard facts, the stretch and tension messages from proprioception, muscle spindles, and Golgi tendon organs, the rise in heart rate and breathing, monitored by interoception, and the buildup of certain metabolites in the muscles. These signals are the objective cost of the action. The motor command signal, corollary discharge. As the brain sends a command to the muscles to contract, it generates an internal copy of that command, known as a corollary discharge. This internal signal is perhaps the strongest component of the sense of effort. The louder the motor command the brain has to send to perform a task, e.g. lifting a very heavy weight, the greater the effort the brain perceives. In essence, you feel the effort not just from the muscles, but from the command itself. Context and interpretation. This is the cognitive layer. The brain weighs the raw data and the motor command against factors like fatigue, motivation, emotional state, and previous experience. This interpretation is what ultimately determines your subjective feeling of difficulty. The rating of perceived exertion, RPE. In the world of sports science, this sense is quantified using the rating of perceived exertion, RPE, often measured on a scale from 6, no exertion, to 20, maximal exertion. This metric, deceptively simple, emphasizes a powerful truth. Effort is fundamentally subjective. If you are running a marathon, two runners side by side may have identical heart rates, identical oxygen consumption, and identical levels of muscle fatigue. Objectively, their bodies are doing the same work. Yet one runner may rate their effort as a 15, hard, while the other rates it as an 18, very hard. This difference highlights the brain's power to modulate the signal. Effort is the brain's safety buffer, a mechanism designed to encourage the conservation of energy and prevent catastrophic failure. But this buffer is highly flexible and subject to mental influence. Imagine two scenarios for lifting the same heavy stone.
Scenario A. You are told the stone is a priceless relic, and lifting it successfully means saving your family. Scenario B. You are told the stone is worthless, and you are simply moving it for no reason. In scenario A, the task will feel easier despite the identical physical workload. The brain, motivated by the high reward and emotional context, effectively turns down the perceived effort signal. It recalibrates the cost-benefit analysis, allowing you to push closer to your absolute physical limit. This is the mental fuel of the sense of effort, demonstrating that what we believe about a task is as important as the metabolic cost of performing it. The pacing mechanism. The sense of effort is your primary tool for pacing over time. It allows you to regulate your behavior so that you don't exhaust your resources too early. Consider a long, slow climb up a tall hill. Your effort sense is continuously monitoring your rising heart rate and muscle strain. It feeds this information to your planning circuits, allowing you to decide, should I maintain this pace or slow down to ensure I reach the summit? This is a continuous, moment-by-moment dialogue between your body's current state and your goal-oriented mind. If this sense is disrupted, pacing becomes impossible. People with certain neurological conditions may find their sense of effort is either dramatically amplified, making simple movements feel agonizingly difficult, or attenuated, leading them to overexert themselves perilously because the body provides no warning. These clinical cases underscore how vital this governor is for the stability and sustainability of life. Effort in the mind. The feeling of exertion is not limited to physical motion. It is a powerful descriptor for mental and cognitive load as well.
Think about the feeling of intense concentration after hours of problem solving, or the exhaustion that settles in after a long, emotionally demanding conversation. Your body hasn't moved, but you describe yourself as being tired. This is because mental fatigue and physical effort share overlapping neural pathways, particularly in regions that manage attention, working memory, and glucose consumption. The brain, like any organ, consumes significant energy, and when the demand is high, the sense of effort kicks in. It tells you that resources are depleting, encouraging you to rest and conserve, even if the exertion was purely cognitive. This subtle, pervasive sense is what connects the physical self to the psychological self. The way you feel about your own exertion influences your choices, your mood, and your self-perception. Training the negotiator. Just as athletes train their muscles and proprioception, they also train their tolerance for perceived effort. This is not about making the body stronger. It is about teaching the brain to reinterpret the discomfort.
Through consistent, progressive training, the central nervous system slowly raises the threshold for alarm. The brain learns that the high heart rate and the burning muscle sensation are not signals of danger, but signals of adaptation and growth. The feeling of an 18 effort today may become a 15 effort next month, even though the objective work is the same. The brain's story about the sensation has changed. This is the power of mental framing, a key element in endurance, rehabilitation, and achieving difficult goals. By consciously focusing on the purpose of the effort, or by simply telling yourself, just 5 more minutes, I can tolerate this, you are engaging your higher cognitive functions to negotiate with the ancient conservative safety buffer of the sense of effort. As you rest now, acknowledge the quiet wisdom of this internal governor. It is the subtle voice that ensures you do not waste energy on the superfluous, but save it for the essential. It is the negotiator that balances your will to achieve with your need to survive, constantly guiding your pace through the long, quiet journey of life. It is this sense that allows you to feel the comfortable weight of your own fatigue right now and to surrender to the deep, restorative rest you seek. But the body's wisdom is not always obvious. Sometimes the brain's construction of reality is revealed only when the body is in motion, and that motion is coordinated with impossible precision. The body is a symphony of separate signals, yet our experience is seamless. This effortless coordination, blending sight, touch, and balance, is a quiet miracle. But what happens when the instruments of this orchestra play different tunes, and how does the brain resolve the conflict? We will explore this harmonious integration in the next chapter. Chapter 9: The Seamless Weave, Multi-Sensory Integration. You have explored the individual dancers in your internal sensory orchestra, the body map of proprioception, the internal state of interoception, the thermal gates of thermoception, and the stability of the vestibular system. Each sense is a marvel unto itself, a dedicated channel of information, but they rarely perform solo. Your experience of the world, the seamless, fluid reality you inhabit, is not a series of separate sensor readings, but a masterpiece of collaboration. This quiet, continuous blending of information from all channels is known as multi-sensory integration. It is the neurological magic that takes fragmented signals and stitches them together into a unified, beautifully coherent whole without needing your conscious oversight. Drift with me now, and let us witness this seamless weave, a process that ensures the simple act of standing, reaching, or speaking feels effortlessly real. Consider the quiet, continuous challenge of simply standing still. It is a profound act of integration. Your visual sense reports that the room is stationary. Your inner ears, through the vestibular system, monitor for the slightest head sway or tilt. Your proprioceptors in your ankles and knees track muscle tension and joint angle.
Simultaneously, the pressure receptors, touch, in the soles of your feet confirm the surface texture and the distribution of your weight. These 4 streams of data, vision, balance, body position, and touch, arrive at the brain's integration centers, particularly in the parietal cortex, at slightly different speeds. The brain must constantly filter, compare, and reconcile these inputs. It is making judgments in milliseconds. Is the slight swaying I feel from my inner ear real movement, or is the ground shifting? If my eyes say the world is moving, but my feet say the floor is stable, which signal do I trust? Most of the time, the brain finds a consensus, and the result is your stable, comfortable, upright posture. You feel grounded. The conflict and the illusion. The elegance of this process becomes strikingly clear when the senses disagree. This is the root of many disorienting, temporary illusions. Imagine stepping off a large, slow-moving escalator. For a moment, you may feel as though the stationary floor is rushing up to meet you, or that you are still drifting forward. Your visual sense and vestibular sense are telling the truth. The escalator was moving. But your brain has built a powerful, temporary predictive model based on that motion. When the motion suddenly stops, the model takes a moment to decay, creating a brief, illusory sensation of continued movement. This sensory confusion is magnified in the phenomenon of sensory mismatch, which is at the heart of motion sickness. The brain cannot tolerate persistent conflict. When the eyes and the inner ear present contradictory evidence, the brain often defaults to a survival mechanism, leading to nausea. But in less threatening scenarios, the brain will actively override a sense to maintain coherence. A famous example is the ventriloquist effect. When you watch a puppet speaking, you hear the words coming from the nearby ventriloquist, but you perceive the sound as originating from the moving mouth of the puppet. Your brain actively relocates the auditory signal to match the visual cue. Vision is so powerful, so dominant, that it actively edits the data from the less trusted sense, hearing, to create a single, unified reality. The eyes tell the ears where the sound should be. The synesthetic weave. The close-knit relationships between the senses are made strikingly visible in the rare neurological condition known as synesthesia. This is a cross-wiring where the stimulation of one sensory or cognitive pathway leads to an involuntary experience in a second pathway.
For some synesthetes, hearing a sound might automatically trigger the perception of a color, chromesthesia. Others may taste shapes or see letters and numbers as specific colors, grapheme color synesthesia. In all brains, the sensory pathways run close to one another, often sharing subtle connections. In the synesthetic brain, these connections are hyperactive, shining the light on the fact that your senses are never truly separate. They are different expressions of the same continuous neural fabric. In the non-synesthetic brain, this connection may simply manifest as an intuitive link, the feeling that a high-pitched sound is lighter or a low-pitched sound is heavier. The adaptability of the system. Perhaps the most astonishing aspect of multisensory integration is its capacity for plasticity and adaptation when one sense is lost. The brain does not simply mourn the lost input, it repurposes the unused real estate. In individuals who are blind, the regions of the cortex typically devoted to visual processing, the visual cortex, do not go silent. Instead, they can become recruited and rewired to process information from the remaining senses, especially touch and hearing. Studies show that when a blind person reads Braille, the visual cortex can actually light up. The brain is literally using the area once dedicated to seeing light to process the intricate texture of the Braille dots. Touch, in this context, becomes a form of seeing. This neuroplasticity has inspired the development of sensory substitution devices, or SSDs. One remarkable example is the BrainPort,
a device that allows blind individuals to see through their tongues. A small camera captures the visual world, and the light patterns are converted into corresponding patterns of electrical stimulation delivered to an array of electrodes placed on the tongue. The resulting sensation is not taste, but a kind of buzzing, tickling pattern. At first, the user only feels the tickle, but with hours of integration and practice, the brain successfully maps the tactile pattern back onto the visual space. Users eventually report that they are no longer feeling their tongue being stimulated. They are experiencing a sense of space and form in the world around them. They are, in a very literal sense, seeing the world through touch. This is the ultimate proof of sensory integration. The senses are defined not by the receptor they use, but by the information they transmit. The brain is a pragmatist. If the data is reliable, it will incorporate it into the cohesive tapestry of reality, even if it comes through an entirely novel pathway. The symphony of self. Every quiet moment of your existence is a testimony to this integration. The pleasure of a warm drink is not just the warmth, thermoception, and the taste, chemoception, but the comforting weight, proprioception and touch, and the satisfying sound of the sip, hearing, all blur together into the single cozy experience.
This seamless weave is what makes the world feel stable, reliable, and unified. Your senses are not separate doors. They are windows in a circular room, each one looking out onto the same landscape, and their reports are constantly cross-referenced and edited to ensure a continuous, coherent story of the world. As you drift now, feel the harmony of this process, the balance, the touch, the internal rhythm, the quiet knowledge of where you are, all are working in unison. You are a multi-sensory symphony, always playing, always adapting, and always translating the chaos of the universe into the calm, predictable structure of your own reality. This harmonious structure is so essential that the brain dedicates specialized, exaggerated space to its key players, creating a profoundly distorted internal self-portrait. The brain's map of your body is not proportional to reality. Instead, it is a grotesque, beautifully distorted caricature with massive hands and lips and a tiny torso. In the next chapter, we will meet this strange internal self-portrait, the homunculus, and see how the brain prioritizes its most sensitive zones. Chapter X, The Grotesque Portrait, Meeting the Homunculus. You have traveled through the invisible pathways and internal rhythms of your body, sensing the subtle whispers of your hidden world. Now, let us venture into the very core of your sensory self-representation to meet a creature both profoundly strange and scientifically beautiful, the somatosensory homunculus. Imagine a tiny, grotesquely distorted person living inside your brain. This figure is not proportional to the size of your physical body. Instead, it possesses comically oversized hands, enormous swollen lips, and a colossal tongue, while the rest of its body, the back, the thighs, the torso, is shrunken and barely noticeable. This bizarre, lumpy caricature is the homunculus, and it is the most honest self-portrait your brain possesses. The homunculus is not a literal creature, but a map, a visualization of how much dedicated neurological real estate different parts of your body occupy within your somatosensory cortex. This strip of neural tissue is located in the parietal lobe, just behind the central fissure that divides the brain, and it is the region responsible for processing touch, temperature, pain, and proprioception signals. Drift with me now and visualize this map. The space allocated to any given body part is not determined by its physical size, but by its sensitivity and its functional importance, the shared density of sensory nerve endings it contains. Sensory royalty. Why the exaggerated features? Because your hands, especially the fingertips, are the sensory royalty of your body. They are the primary tools of exploration, manipulation, and communication. A fingertip can feel the faint vibration of a buzzing phone, distinguish the texture of silk from sandpaper, or precisely adjust the grip
on a delicate object. To handle this immense influx of fine-grained data, the brain dedicates a vast, disproportionately large area of cortex to them. Similarly, the lips and tongue are immense on the homunculus because of their essential role in speech, taste, and emotional expression. They require exquisite sensitivity for articulation, feeding, and social bonding. They are sensory gateways, and the brain allocates them the necessary processing power to manage their complex functions. Conversely, large areas of the body, such as the skin of the back or the thighs, have lower nerve density. They are important for posture and support, but are less critical for fine discrimination. Thus, they are represented by much smaller areas on the homunculus. This internal self-portrait is a powerful reminder that the brain does not care about physical symmetry. It cares intensely about functional utility. The motor homunculus. The sensory map is paired with a neighboring, equally distorted figure, the motor homunculus. This map, located just forward of the central fissure in the motor cortex, represents how much brain power is dedicated to controlling movement in different body parts. Unsurprisingly, the motor homunculus also possesses massive hands, fingers, lips, and tongue. This reflects the incredible fine motor control required for precision tasks, playing an instrument, writing, using tools, or producing the complex, rapid movements of speech. Together, the sensory and motor homunculi show us that much of your mental real estate is devoted to the tasks of touching, feeling, and moving with precision. Neuroplasticity, the shifting self. The homunculus is a powerful visualization, but it holds an even deeper secret. It is not fixed. It is made of living, adaptable neural tissue. The map can be continuously redrawn and reorganized through a process known as neuroplasticity. The phrase "use it or lose it" applies, but in a more dynamic way: use it and grow it. Skill acquisition. When you learn a new high-precision skill, the corresponding area on the homunculus will physically expand. For example, studies have shown that professional violinists develop an enlarged cortical representation for the fingers of their left hand, the hand used for precise string placement. A tactile artist or a professional braille reader will show increased sensitivity and cortical area dedicated to their fingertips. The brain rewards investment by dedicating more computational space to the well-practiced function.
You have explored the hidden senses of the human body. Now let us expand our view to the natural world. How does a robin navigate across oceans without a map? How does a snake see in absolute darkness? We will explore the exotic sensory world of animals and what their hidden talents reveal about our own limits in the next chapter. Chapter 11, Beyond the Five, the Exotic Senses of the Animal World. We have focused intensely on the hidden internal genius of the human body, uncovering the subtle senses that keep you balanced, aware, and embodied. But as you settle deeper into the quiet, let us lift our gaze and expand our sensory imagination to the vast, shimmering world beyond our skin, a world perceived in ways we can only begin to grasp. Drift with me now, and let us explore the exotic sensory landscape of the animal kingdom. This realm operates not on 5 nor 10, but on dozens of unique channels, revealing that our human reality is but one narrow slice of the universe's full sensory spectrum. Evolution is the ultimate inventor, and if a novel sense aids survival, nature will find a way to build it. The compass within, magnetoreception. Imagine a life without maps, without sun or stars, yet possessing the unwavering certainty of direction. This is the reality for creatures tuned into the planet's fundamental force, magnetoreception, the ability to sense the Earth's magnetic field. Think of the robin we mentioned, or the tireless sea turtle navigating thousands of miles across featureless ocean. These creatures carry an internal biological compass. While the exact mechanism remains a topic of intense scientific research,
two leading theories suggest astonishing sensory technology. Magnetite crystals. Microscopic crystals of magnetite, a naturally magnetic mineral, are believed to be located in specialized cells in the beaks of some birds and the brains of others. These crystals subtly shift in response to the magnetic field lines, triggering nerves that convey directional information. Quantum compass. Another more mind-bending theory involves quantum physics. Some species of migratory birds may possess light-sensitive proteins called cryptochromes in their eyes. When these proteins absorb blue light, they become chemically activated, and the subsequent chemical reaction is so delicate that it is influenced by the Earth's magnetic field. This could allow the bird to literally see the magnetic field, perhaps as a slight pattern or gradient overlaid on their visual field, like a subtle shimmering curtain indicating north and south. For these animals, the planet's magnetic grid is a permanent, reliable map, allowing them to maintain their bearings even in the murkiest water or the densest cloud cover. The magnetic field, invisible and unfilled by us, is a palpable truth for them.
Seeing heat, infrared thermoreception. Now shift your focus to the quiet, dark floor of a forest, where a pit viper lies coiled, waiting. Its vision is limited, but its world is illuminated by the invisible light of heat. The pit viper, which includes rattlesnakes and copperheads, possesses specialized structures called pit organs, tiny indentations located between its eyes and nostrils. These pits contain membrane sheets packed with highly sensitive TRP channels, similar to our own, but tuned to detect faint infrared radiation, the heat signature, emitted by warm-blooded prey, like a mouse or a rat. In the absolute darkness of night, to the pit viper, its prey doesn't just make a sound, it shines like a small moving thermal lamp. The snake can build a complete, detailed, three-dimensional thermal image of its environment, striking with deadly accuracy purely on the radiant heat of its target. This is not vision as we know it, but a separate, dedicated sense for detecting the molecular vibration of energy itself. It is the biological equivalent of a high-tech night vision camera, confirming that our sense of temperature is a crude whisper compared to the viper's thermal roar. Feeling electricity, electroreception. Descend now into the murky, lightless depths of the ocean, where the waters blur sound and sight. Here, creatures like sharks and rays navigate using a sense that detects the fundamental force of life itself, electroreception. All muscle contraction, every nerve impulse, every cellular ion exchange in a living creature generates a tiny, faint bioelectric field. Sharks and rays are equipped to sense these fields using specialized sensory pores, called the ampullae of Lorenzini. These pores are small canals filled with a conductive jelly that open to the surface of the skin, mostly around the head and snout. They act as biological voltmeters, detecting even incredibly subtle voltage changes in the surrounding water, sometimes as faint as a few billionths of a volt. This sense allows a shark to hunt in the dark, locate a flatfish buried silently beneath the sand simply by sensing the faint electrical field generated by its gills moving, navigate, use the electric currents generated by ocean tides moving through the Earth's magnetic field to orient themselves over vast distances. For the shark, the environment is not silent or dark. It is filled with a dynamic, living electric hum, a continuous map of hidden life and geophysical forces. The pressure radar, lateral line system. Many fish, amphibians, and aquatic creatures possess another highly specialized sense, the lateral line system. This is a pressure sensing network that runs along the sides of the body, often visible as a faint, distinct line. The lateral line is composed of fluid-filled canals beneath the skin containing sensory hair cells, similar to those in our inner ear. These cells detect subtle changes in water flow and pressure. It allows a fish to
sense vibrations, detect the movement of other fish in a school, allowing for synchronized swimming, Avoid obstacles. Navigate obstacles in turbid water by sensing the pressure waves bouncing off them. Detect predators. Feel the approaching pressure wave of a larger, faster animal before it is seen. It is a continuous underwater tactile radar, giving the fish a comprehensive, real-time map of the hydrodynamic texture of its immediate environment. Our sensory keyhole. What these exotic animal senses reveal is profoundly humbling. The sensory reality available to us, defined by our 5 main senses, plus proprioception, interoception, balance, and thermal awareness, is incredibly rich, yet it remains fundamentally limited. Our human senses operate like a keyhole through which we view a vast, unbounded universe. We perceive the world within the narrow band of the visible light spectrum, hear only a limited range of sound frequencies, and feel only a fraction of the pressure and thermal gradients that exist. The robin, the snake, and the shark peer through entirely different keyholes, experiencing entirely different, equally valid aspects of reality. The planet is a chorus of magnetic fields, thermal gradients, and electric hums that we simply do not have the biological hardware to access. This realization transforms our appreciation of our own hidden senses. Our proprioception may not guide us across the magnetic ocean, but it perfectly guides us across an uneven floor. Our interoception may not detect bioelectric fields, but it perfectly monitors the subtle chemistry of our heart and gut. Our senses, both obvious and hidden, are perfectly optimized for the demands of being a human being: tool use, complex communication, bipedal locomotion, and social navigation. As you conclude this journey through the sensory world, let the knowledge of these exotic animal senses deepen your awe for the invisible world within you. The difference between you and the robin is not a measure of superiority, but a beautiful testament to evolutionary specialization. Every living creature, from the microscopic bacterium to the soaring hawk, carries a unique, perfectly tuned way of knowing the world. And now we turn to the final, fascinating question. Can the human mind, through intention and focus, learn to deliberately tune in to its own subtle internal broadcasts? Can we train our hidden senses? The body is a marvel, but can the mind influence its sensors? We will explore the science of attention and the practice of mindfulness, revealing how deliberate focus can amplify the quiet voice of interoception and change the physical structure of the brain itself. Chapter 12: The Quiet Amplifier: Mindfulness and the Training of Interoception. You have navigated the hidden architecture of your body, sensing the subtle whispers and the silent alarms. We have established that the human experience is built upon far more than the classic 5 senses. But the final, profound question is this: if these senses are mostly unconscious, can we, through intention and focus, learn to actively tune them? Can the mind deliberately amplify the subtle broadcasts of the body? Drift with me now into the fascinating intersection of ancient wisdom and modern neuroscience, where the practice of mindfulness is revealing itself to be a powerful, measurable way to sharpen our internal senses, particularly interoception. At its core, mindfulness is the practice of bringing your full attention to the present moment, observing sensations, thoughts, and emotions without judgment. This simple act of quiet attention, performed consistently, is not just a spiritual endeavor. It is a direct, measurable form of sensory training. Remodeling the sensory brain. When you sit quietly and focus on the felt experience of your body, the weight, the stillness, the breath, you are sending a clear, repetitive signal to your interoceptive system. Attention is now focused here. Report with greater detail. Scientifically, this practice has a profound physical effect on the brain. Neuroimaging studies using techniques like fMRI have shown that long-term meditators often exhibit functional and structural changes in key areas of the sensory network. Specifically,
there is evidence of increased gray matter density and enhanced activity in the insular cortex and the anterior cingulate cortex. Recall that the insular cortex is the brain's primary integration center for interoceptive data, the region that translates raw physiological signals, like heart rate or stomach tension, into a subjective, felt experience, like anxiety or calm. By regularly directing attention to these internal signals, mindfulness effectively remodels the insula, making it a more efficient and sensitive receiver of the body's internal broadcasts. It's like upgrading your body's radio tower, resulting in a signal that is clearer, stronger, and less prone to static. The heartbeat detection test. One of the most objective measures of interoceptive sensitivity is the heartbeat detection task. In this experiment, participants are asked to silently count their own heartbeats for a set period without touching their pulse or using any external device. Their count is then compared to the actual recorded heartbeats. Individuals who regularly practice mindfulness or meditation consistently demonstrate higher accuracy in this task. Their brains are more finely attuned to the subtle pressure changes, blood flow dynamics, and neurosignals that accompany each beat. This isn't just a party trick. It signifies a more robust connection between the internal rhythm of the body and the cognitive awareness of the mind.
This heightened awareness is directly linked to improved emotional regulation. When you can sense stress or anxiety rising in your body, e.g., a subtle quickening of the pulse, a shallowing of the breath, at an earlier stage, you gain a crucial delay time. You move from reacting to the emotion to responding to the sensation. This ability to create space between the signal and the reaction is the foundation of emotional intelligence and resilience. Gateways into internal awareness. Mindfulness offers specific techniques that utilize the hidden senses as anchors. The body scan. This practice involves systematically moving attention through the body, from the tips of the toes to the crown of the head. You are not trying to relax or change the body, but simply to notice the sensations as they are, the mild pressure where the body meets the surface, the faint tingling in the extremities, the subtle muscle tension. This practice directly challenges and refines the integration of proprioception, thermoception, and light touch, turning the body's ambient sensory hum into a subject of deliberate focus. Breath following. As discussed in Chapter 3, the breath is the unique dual control function of the body. Focusing on the breath, the cool air entering, the warm air leaving, the rise and fall of the diaphragm, is the most accessible gateway to interoception. It allows you to deliberately engage the vagus nerve pathway, sending calming feedback to the autonomic nervous system. By consciously tracking the breath's rhythm, you create a tangible link between your mental state and your physiological rhythm. The poetic truth. The essence of this training is not about gaining new information, but about reintegrating what the body already knows. In our fast-paced, outwardly focused lives, we often rely on external metrics, the clock, the scale, the schedule, while systematically overriding internal ones, fatigue, hunger, tension. Mindfulness is the radical act of reprioritizing the internal wisdom. For individuals who have experienced trauma, chronic pain, or high anxiety, the body's internal signals can become distorted, dulled, or overwhelming. The heart racing might be interpreted as danger, not just exertion. By cultivating mindful awareness, the brain can be retrained to process these signals with greater equanimity and accuracy. The system learns that a quickened heart is a sensation that can be observed, rather than an emergency that demands panic. It is a quiet, gentle revolution. By slowing down and listening inward, you are using the incredible neuroplasticity of your brain to reestablish trust in your own physical presence. You shift from being a passenger in your body to being the attentive steward of your biological systems. As you settle deeper into your rest, understand that this journey through the hidden senses has been a profound act of mindfulness. You have used the power of attention to illuminate the vast, silent, and miraculously complex world that resides within you. The greatest science story is the one unfolding inside your own skin. In the final chapter, we will gather all these threads: proprioception, interoception, balance, and integration, to reflect on the deepest mystery of all: how these hidden senses construct your seamless, unshakable feeling of embodiment.
the quiet knowing of being you. You are here, you are present. All the hidden senses are working in harmony. But what is this you that is sensed? We will consider the final, beautiful mystery of embodiment, the fusion of sensation and selfhood, as we drift toward complete rest. Chapter 13, The Final Frontier, Embodiment and the Unshakable Self. You have traveled through the silent, profound wisdom of the hidden senses. Proprioception mapped your space. Interoception whispered your rhythm. Balance steadied your orientation. Pain guarded your boundaries. Together, these systems, along with the classic five, weave the complete, complex tapestry of human experience. But as our journey nears its close, we arrive at the final, most beautiful mystery: embodiment. What is this feeling, this unshakable, effortless certainty that you are you, contained right here, inside this specific body? How do all the scattered signals, the micro adjustments, the subtle shifts in thermal energy, and the quiet internal pulses fuse into a single, seamless, continuous sense of selfhood? Drift with me now, and let us gently conclude that the feeling of being embodied is not a static fact. It is a grand, dynamic construction built entirely from the relentless flow of sensory data. The self as a sensory field. Your brain does not perceive the body as a collection of separate parts. It maintains an integrated, three-dimensional body matrix that defines the boundaries and the contents of the self. This matrix requires continuous, non-stop confirmation from the hidden senses to remain stable. Proprioception confirms your location in space. I am sitting here, my leg is crossed. Interoception confirms your internal state. I am breathing steadily, my heart is calm. Multisensory integration ensures that the visual image of your body aligns perfectly with the feeling of your body. When all these systems agree, the result is the quiet, perfect feeling of being home in your own skin. This feeling of ownership, however, is astonishingly malleable, as we saw with the rubber hand illusion and phantom limb syndrome. The brain prioritizes consistency. If vision, touch, and proprioception can be tricked into a temporary, cohesive consensus, the brain will instantly and completely adopt the illusion.
The fact that the self can be temporarily extended to include a piece of rubber, or that the body map can stubbornly cling to a limb that is gone, reveals a vital truth. Selfhood is a working hypothesis. It is the brain's most efficient, moment-to-moment guess about where the organism begins and ends, based on the loudest, most coherent sensory data available. Tool embodiment, extending the self. The boundary of the embodied self is not limited to the skin. It is functionally stretchable. Consider the simple act of using a familiar tool, perhaps a writing pen, a tennis racket, or a long walking stick. When you use the tool, your brain rapidly extends its proprioceptive map to incorporate it. You stop feeling the pressure in your palm from holding the handle and start feeling the tip of the stick contacting the ground or the end of the racket striking the ball. Functionally, the tool has become a temporary, high-definition extension of your arm. This phenomenon, known as tool embodiment, demonstrates that your body schema is designed to be elastic. It includes anything that allows for functional interaction with the environment. Your sense of self is a practical, adaptive definition, expanding and contracting as your focus and tools change. The philosophical anchor of interoception. Among all the senses, interoception provides perhaps the deepest anchor for the sense of self. It is the continuous, non-voluntary report from the deep internal reality of the body, the heart, the lungs, the gut. Philosophically, René Descartes famously separated mind and body with his declaration, "I think, therefore I am." But modern neuroscience, heavily informed by the quiet work of interoception, suggests a revision. I feel the quiet, continuous rhythm of my body, therefore I am.
Studies have shown that individuals with strong interoceptive accuracy, those who are deeply attuned to their heartbeat and breath, tend to report a more stable, less dissociative sense of self. They feel more grounded in their emotional and physical responses. When the internal rhythm is clear, the self feels real. When the signal is fuzzed by stress, trauma, or illness, the feeling of self can become detached or unreal, leading to feelings of depersonalization, the unsettling sense of observing your life from afar. The quiet, insistent truth of your heartbeat is arguably the most fundamental way your biology affirms your existence. It is the continuous drumbeat beneath consciousness. The dance of consciousness. The most profound realization from our journey is that these hidden senses are the necessary scaffolding of consciousness. They provide the where and the how for the who you are. They explain the feeling of flow, those rare, immersive moments during deep concentration, creativity, or intense physical activity, where the inner narrator falls silent. In these moments, the boundary between the body and the world softens, and the action becomes effortless. The hidden senses, proprioception, balance, and effort, are running the entire show, performing with such perfect integrated coordination that the conscious mind no longer needs to intervene. The self is dissolved into the process, guided entirely by the body's internal ancient wisdom. This is the state of perfect embodiment, a place of quiet action and seamless knowing, where the body's hidden wisdom fully takes the reins. As you conclude this sensory exploration, let go of any effort to monitor your body. Let the knowledge you have gained dissolve into the quiet certainty of your rest. You do not need to command your senses. They are perfectly designed to manage themselves. You are an organism of magnificent, coordinated complexity. The hidden senses are your body's way of whispering the fundamental truth of your existence. You are here, not in coordinates, but in warmth, in weight, in balance, in breath, in the deep, quiet, unshakable knowing of being alive. May that quiet knowing be your anchor now. Feel the weight of your body, supported by the ground beneath you. Feel the slow, gentle rhythm of your breath, an effortless exchange between your internal world and the world outside. All the tiny, tireless engineers, the shimmering crystals, the specialized molecular gates, and the ancient nerve pathways are now settling into their deepest night watch, ensuring your safety, your stability, and your peaceful rest. You are safe. You are held. You are wonderfully complex. The full symphony of the hidden senses is now playing at its softest volume, guiding you gently towards sleep. All systems are go. All reports are filed. May your descent into dreams be as profound and seamless as the hidden processes that govern your waking life. Sleep well, and know that the miracle of your being is held by the quiet wisdom within.
Hello there, and welcome to the Midnight Scientists. I am glad you have found your way here, to this quiet sanctuary carved out of the noise of the day. If you're listening to this, the sun has likely dipped below the horizon, leaving in its wake the soft indigo bruise of twilight, or perhaps the deep, absolute obsidian of the middle of the night. This is a space designed for you to slow down, to unspool the tight coils of the day, to let the heavy machinery of the waking world grind to a halt, replaced only by the hum of curiosity and the rhythm of your own breath. Before we begin our journey tonight, I want you to take a moment to orient yourself, not in time, for time behaves differently here in the dark, but in space. Where are you in this vast, spinning world? Perhaps you are tucked beneath heavy, quilted blankets in a snowy corner of the north, where the wind howls against the glass but cannot reach you. Perhaps you are lying beneath the slow, rhythmic turning of a ceiling fan in the humid warmth of the southern hemisphere, the air heavy with the scent of rain. Or maybe you are in a city that never quite sleeps, listening to the distant, muffled traffic that sounds like the ocean washing against the shores of concrete and steel. Chapter 1. The Threshold of the Unseen. Wherever you are, visualize yourself as a single point of light on the dark globe of the earth. You are part of a vast, invisible web of dreamers, a community of the night, all seeking the same stillness, the same respite. You are safe here. You are anchored. If you haven't already, settle yourself. Adjust the pillows beneath your head until they feel like clouds supporting the weight of your thoughts. Pull the covers up to your chin. Let your limbs grow heavy, sinking deeper into the mattress, as if gravity itself is wrapping you in a gentle embrace. Unclench your jaw. Let your shoulders drop away from your ears. Let the small muscles around your eyes soften, smoothing out the worry lines of the day. You are not expected to do anything now. There's no checklist, no urgency. You are not even expected to remember what you hear tonight. This story is a vessel, drifting down a slow river. You may stay on board and watch the scenery pass, or you may close your eyes and drift away into the current of sleep at any moment. Both are welcome here. Tonight, we are going to explore a mystery that has captivated the human mind as long as we have been human. It is a topic that has puzzled philosophers in marble halls, challenged scientists in sterile laboratories, and inspired poets staring up at the moon. We are going to talk about dreams. And yes, there is a gentle irony in speaking of dreams in hopes of lulling you into them, but I hope that rather than keeping you awake, this exploration will serve as a bridge, a soft, sturdy walkway leading you from the conscious world into the subconscious one. We are about to float gently through the science of why we dream, how the brain spins intricate stories in the dark, and what those nightly voyages might mean for our waking lives. So take a deep, slow breath. Inhale the quiet of the room and exhale the static of the day. Let us begin. To understand dreaming, we must first appreciate the vessel in which it happens, the sleeping mind. When we close our eyes, it often feels as though we are turning off a switch. We imagine the brain powering down, like a computer screen fading to black, sitting dormant and silent until the alarm rings in the morning. But the reality is far more beautiful and far more active. When you drift off, your brain does not switch off. Instead, it shifts gears. It moves from the sharp, analytical focus of the daylight hours into a softer, more fluid state of being. It enters a maintenance mode that is anything but passive. It is a time of repair, of sorting, and of creation. What technically is a dream? The question sounds simple, doesn't it? Like asking why the sky is blue or how a tide rises. But as with all things in the realm of the mind, the word technically begins to wobble the moment we look at it closely. Dreams are notoriously slippery. You know what one feels like. You know the texture of a dream. It is strange, vivid, and fleeting. It is profound in the moment, yet often dissolves like mist the second you open your eyes. Defining a dream with scientific precision is like trying to bottle fog. It is like trying to catch a cloud in a net. But let us try to trace its edges. In the most basic physiological sense, a dream is a sequence. It is a series of images, emotions, thoughts, and sensations that occur involuntarily in the mind during certain stages of sleep. It is a hallucination that we accept as reality. It is a story we tell ourselves when there is no one else listening. Psychologically, a dream is a unique form of consciousness. It is a state where you are undeniably there. You see, you feel, you react, and yet your physical body is absent from the equation. You are an observer and a participant in a world built entirely from the bricks of your own memory and imagination. Neurologically, a dream is a symphony, or perhaps a storm. It is a cascade of electrical activity firing across the darkened landscape of your cortex. It involves the limbic system, the ancient emotional core of your brain, and the visual cortex, the part of you that sees. These regions light up and communicate in a language of sparks and signals, all while the prefrontal cortex, the logical, skeptical CEO of your brain, takes a step back. This is why in a dream you do not question the impossible. Imagine for a moment that you are floating through a grocery store, but the aisles are not of linoleum and metal shelves. They are floating on clouds of toast. You are searching for your childhood pet, a dog you haven't seen in 20 years. And when you find him, he looks at you with wise, kind eyes and speaks to you in fluent Italian. In the waking world, your brain would reject this immediately. It would say, "This is impossible. Dogs do not speak. Clouds cannot hold the weight of a store." But in the dream, the logic centers are asleep. The skepticism is offline. And so you accept it. You nod at the dog. You understand the Italian. You float on the cloud. It feels completely, undeniably reasonable. This suspension of disbelief is one of the hallmarks of the dreaming mind. It is a protected space where the rules of physics, time, and identity are suspended, allowing the brain to explore scenarios that could never exist in the light of day. But not all dreams are the same. Just as the ocean has different depths, from the sunlit shallows to the crushing dark of the trenches, the world of sleep has different zones. Scientists have done their best to categorize the types of dreams we experience, though the borders between them are often as fuzzy as the edge of a shadow. There are the vivid dreams. These are the ones we tend to remember most clearly. They are the cinematic blockbusters of the night. They possess a high-definition clarity, filled with saturated colors, intricate textures, and a strong sense of narrative. In a vivid dream, you can feel the wind on your skin. You can smell the salt of the ocean or the dust of an old library. You have a distinct sense of being there. These are the dreams that leave a residue on your mood when you wake up, a lingering feeling of joy or longing or unease. Then there are the abstract dreams. These are softer, more fragmented. They are like looking at a painting through a pane of frosted glass. They might not follow a story. Instead, they are collections of impressions. You might dream of a shape or a color or a feeling. You might wake up with the vague sensation that you were trying to solve a puzzle or that you were late for something, but the details remain forever out of reach. Abstract dreams are less like movies and more like whispers. They are the brain organizing information in a way that doesn't require a script. And then we have the recurring dreams. These are the familiar visitors, the old friends or perhaps the old ghosts that come to knock on the door of your mind time and time again. They revisit the same theme, the same landscape, or the same scenario. Perhaps you are back in school, walking down a hallway that stretches on forever, realizing you have forgotten the combination to your locker. Perhaps you are running, your legs moving through air that feels thick as molasses, trying to catch a train that is always just leaving the station. Or perhaps you discover with a jolt of embarrassment that you have forgotten to wear clothes in a crowded room. These loops are fascinating to scientists and psychologists alike. The brain, it seems, likes to revisit certain patterns. It is like a musician practicing a difficult bar of music, playing it over and over, trying to resolve the tension, trying to get it right. Recurring dreams are often tied to unresolved stress or ongoing themes in our lives, but they are also a testament to the persistence of the subconscious. It does not give up easily. And finally, we must touch upon the most mysterious type of all, lucid dreams. These are the rare jewels of the night. In a lucid dream, a spark of awareness ignites within the sleeping mind. You are in the dream, perhaps flying over a golden city or speaking to a long-lost friend, and suddenly a realization washes over you. You think, wait, this isn't real. I am dreaming. In that moment, you become the director of the movie. You are no longer just a leaf blown by the wind of the narrative. You are the wind itself. You can choose to turn left instead of right. You can choose to fly higher. You can conjure a door where there was only a wall. Scientists believe that lucid dreaming involves a unique neurological state, a hybrid consciousness where the waking brain and the dreaming brain briefly touch hands. Parts of the prefrontal cortex, that logical guardian, wake up just enough to give you agency, while the rest of the brain remains deep in the vivid hallucinations of sleep. It is a delicate balance, walking the tightrope between two worlds. But before we can dive deeper into the meaning of these dreams, into the theories of Freud and Jung and the modern neuroscientists who map the firing of neurons, we must understand the rhythm of the night itself. We must understand that sleep is not a flat, monotonous line. It is a cycle. It is a tide that flows in and out, carrying you through different stages of consciousness, each with its own purpose, each with its own flavor. Imagine the sleep cycle as a slow descent down a grand, spiraling staircase. When you first close your eyes, you are merely standing at the top of the stairs. You are in the transition. The sounds of the room, the hum of the refrigerator, the passing car are still accessible to you, but they are beginning to fade. This is the shallow water. As you descend, the water grows deeper, darker, and cooler. Your heart rate slows, your temperature drops. The electrical waves of your brain lengthen and smooth out, like the rolling swell of a calm sea. You move from light sleep into deep sleep, the restorative slumber where the body heals itself. And then, after exploring the depths, you begin to rise again. You surface toward a different kind of consciousness. You enter the state known as REM, rapid eye movement. This is the realm of the dream, but we are getting ahead of ourselves. For now, just visualize that staircase. Visualize the slow, rhythmic descent, step by step, breath by breath, leaving the light of the surface behind, moving comfortably into the velvet embrace of the inner world. The night is long, and we have time. There is no rush to reach the bottom. There is no rush to understand it all at once. We are simply here, at the threshold, ready to open the door and see what lies inside. Chapter 2. The Rhythm of the Tides. You might imagine that sleep is a stillness. When we look at a sleeping person, that is certainly what we see. The chest rising and falling in a slow, hypnotic cadence, the hands uncurled and resting, the face smoothed of expression. It looks like a pause. It looks like the machine has been unplugged, the lights turned off, the engine allowed to cool. But beneath that surface of calm, there is a symphony playing. Sleep is not a monolith. It is not a single, unchanging state of darkness that you enter at night and leave in the morning. It is a journey. It is a dynamic, shifting landscape that you traverse over and over again throughout the night. It is a cycle, rhythmic as the tides, predictable as the phases of the moon. Your brain does not simply shut down. it dances. It moves through a carefully choreographed routine, a ballet of neurochemistry and electricity that repeats roughly 90 minutes, like a traveler descending into a canyon and climbing back out to the ridge. You cycle through depths and shallows, through quiet restoration and vivid hallucination. Let us walk through this cycle together. Let us trace the path you take every night, even if you are never awake to see the map. It begins, as all journeys do, with a departure, non-REM stage 1. This is the shoreline. You have just pushed your boat off the sand. You are drifting away from the waking world, but you can still see the land. This is that lovely, hazy borderland where your thoughts begin to lose their shape. The rigid logic of the day softens. You might hear a car drive by outside, but it sounds distant, unimportant. You might have a thought about tomorrow's to-do list, but it dissolves before you can finish it. This stage is brief, usually lasting only a few minutes. It is the lightest form of sleep, a fragile state where you can be easily called back. If someone were to whisper your name now, you would wake up and might even claim you weren't sleeping at all. It is here, in this shallow water, that you might experience a sudden, startling sensation. You are drifting, and then a jolt, a twitch of the leg, a sensation of falling as if you have missed a step on a staircase. This is called a hypnic jerk. It is a common, harmless little glitch in the system. Some scientists believe it is an evolutionary echo, a reflex from our ancient ancestors who slept in trees, a quick check by the brain to ensure we weren't falling from our perch. Others think it is simply the muscles relaxing too quickly, a misfire of energy as the body powers down. Whatever the cause, it is merely a ripple on the surface. You twitch, you settle, and you drift deeper. Non-REM stage 2. Now the shore is gone. You are in open water. The sounds of the outside world are severed. You are no longer listening for the door to open or the wind to blow. You have turned inward. Your heart rate slows its rhythm. Your body temperature drops, cooling the engine. And inside your brain, something fascinating is happening. If we were to look at an EEG monitor, watching the electrical waves of your mind, we would see slow, steady rolling waves interrupted by sudden, sharp bursts of activity. These are called sleep spindles and K-complexes. They sound technical, but think of them as sparks in the dark. They are brain's gatekeepers. These little bursts of electrical activity are believed to be the brain's way of protecting your sleep. They are noise-canceling signals. When a sound occurs in the room, a creak of the floorboards, a distant siren, these spindles fire up to suppress the brain's response to it. They are saying, "Hush, it is not important. Stay asleep. Stay deep." It is also here in this quiet, protected space that the brain begins to sift through memories. It starts to move information from the temporary loading dock of short-term memory into the long-term archives. It is the beginning of the night's work. You spend about half of your night in this stage. It is the steady, reliable cruising altitude of sleep. But the journey is not over. The bottom of the canyon still awaits. Non-REM Stage 3. Welcome to the abyss. This is also known as slow wave sleep or deep sleep. On the brain monitor, the frantic scribbles of waking thought are gone. The quick sparks of Stage 2 have faded. Now the lines rise and fall in huge, slow, majestic undulations called delta waves. Imagine the ocean in the middle of the Pacific, not the choppy waves of a storm, but the massive, slow swell of the water moving across thousands of miles. That is the rhythm of your brain in deep sleep. This is the most restorative stage of all. It is here that the body does its heavy lifting. It is not dreaming, it is repairing. Growth hormones are released, muscles are knitted back together, the immune system is recharged. The brain actually flushes itself of toxins that build up during the day, a literal cleansing of the mind. If you are woken up from this stage, you will feel lost. You will be groggy, confused, moving through a thick fog. Your brain is so deep in the cellar of consciousness that it takes a long time to climb back up the stairs. This deep sleep is a sanctuary. It is a place of absolute oblivion, a void where you cease to exist for a while so that you can exist better tomorrow. But you do not stay in the dark forever. After dwelling in the depths for a time, the tide begins to turn, the brain waves speed up, the journey reverses. You rise from the deep, up through the lighter stages, moving toward the surface. But instead of waking up, you enter a new door, a door marked with a strange, paradoxical energy. REM sleep, rapid eye movement. This is the star of the show. This is where the magic happens. It is called paradoxical sleep because to a scientist looking at your brain scans, you look awake. The visual cortex is lighting up with fireworks. The emotional centers, the amygdala and the limbic system, are burning bright. The brain is consuming energy, firing signals, processing information with an intensity that rivals and sometimes exceeds the waking state. And yet you are deeply asleep. It is here that the body does something remarkable. As the mind wakes up into the dream world, the brain stem sends a signal down the spinal cord. It is a command of absolute stillness. It creates a temporary paralysis called REM atonia. Your major voluntary muscles, your arms, your legs, are switched off. They become limp and heavy. This is a brilliant safety mechanism. In your mind, you might be running a marathon, or fighting a dragon, or conducting an orchestra. If your body were to act out these movements, you would hurt yourself. You would thrash and kick. So nature has designed a lock. The mind is given the key to infinite movement, infinite flight, infinite speed, while the body remains safely anchored to the mattress, a heavy stone in a riverbed. The only muscles that are spared are the ones that control your breathing and, of course, your eyes. Beneath your closed lids, your eyes dart back and forth, tracking invisible objects, watching scenes that exist only for you. You are watching the internal cinema. You are dreaming. This is the cycle. Stage 1, Stage 2, deep sleep, REM. It takes about 90 minutes to complete one full loop, and then it begins again. But the night is not a perfect repetition, it evolves. In the first half of the night, your body prioritizes deep sleep. It knows that physical repair is the most urgent need, so you spend long stretches in the delta waves, fixing the vessel. The dreams are short, if they happen at all. But as the night wears on, as the body cools and repairs, the balance shifts. The deep sleep grows shorter, the REM periods grow longer. By the early hours of the morning, in that quiet time before dawn, when the birds are just thinking about singing, you are spending long stretches in the dream world. Your brain is no longer fixing the body, it is now working on the mind. It is processing emotions, running simulations, weaving stories. It is a beautiful, elegant system, a nightly maintenance routine that runs without you ever having to press a button. Think of it as a nightly dive. You dive down into the deep, dark water to heal your bones and muscles, and then you swim up to the shimmering surface to heal your heart and mind. Down and up, a rhythm that has been with you since the day you were born. So as you lie there now, feeling the heaviness of your own limbs, know that you are not just off, you are preparing to enter this cycle. You are waiting for the tide to take you out. You are waiting for the gatekeepers to dim the lights. You are waiting for the waves to slow down until they become the long rolling swells of the deep ocean. And eventually, you will find yourself in that strange, paralyzed, electrified state of REM. But what happens there? When the body is locked and the brain is free, where do we go? And why does the brain choose this time when we are most vulnerable to tell us stories? To understand that, we must look at the machinery of the dream itself. We must look at the parts of the brain that wake up when the sun goes down. Chapter 3: The Theater of the Mind. Now that we have descended the staircase of sleep and settled into the rhythm of the tides, let us step inside the room where the dreaming actually happens. It is a strange place, this internal theater. If you were to stand outside it, looking at the sleeping body, you would see only stillness. The eyelids flutter like the wings of a moth, but the face is serene, the breath is steady, the hands are curled in rest. But if we could dissolve the skull and look upon the landscape of the brain during REM sleep, we would not see darkness. We would see a city at night. We would see a sprawling metropolis of neurons, vast and intricate, coming alive with a light show of spectacular complexity. It is one of the great paradoxes of human existence. When the body is most paralyzed, the mind is most liberated. When the muscles are turned off, the imagination is turned up to its highest setting. Let us take a tour of this glowing city. Let us walk through the architecture of your brain as it constructs a dream. The first thing you might notice is the energy. During deep sleep, the brain was quiet, humming with those slow rolling delta waves. But now, in the dream state, the energy spikes. The neurons are firing in rapid staccato bursts. The consumption of glucose, the brain's fuel, soars. In some regions, your brain is burning energy now, lying motionless in the dark, as it does when you are awake and solving a complex mathematical problem. But the lights are not on everywhere. The city is lit selectively. Walk with me to the center of the city, to the deep, ancient structures that sit at the top of the brainstem. Here we find the limbic system. This is the emotional core of the human being. It is the seat of our passions, our fears, our desires, and our instincts. And during a dream, this area is blazing. Specifically, a small almond-shaped structure called the amygdala is highly active. In the waking world, the amygdala is your sentry. It is the part of you that scans for danger. It is the part that makes your heart race when a car swerves too close, or makes you feel a swell of warmth when you see someone you love. It is the engine of intensity. In the dream world, the amygdala is unchained. This helps explain why dreams are rarely neutral. Have you ever noticed that you rarely dream of simply sitting in a beige room doing nothing? No, dreams are charged. They are saturated with feeling. You feel an overwhelming sense of urgency as you run through a forest. You feel a crushing sorrow as you wave goodbye to a ship leaving a harbor. You feel a soaring, golden euphoria as you realize you can fly. The amygdala does not know that these things are not real. It does not care that the forest is a hallucination or that the ship is made of memory. It responds to the signal with total sincerity. It floods your system with the chemistry of emotion. So, when you wake up with your heart pounding or with tears drying on your cheeks, it is because, to your amygdala, the experience was true. The story was fake, but the feeling was real. But as we look around this lit-up city, we notice a dark spot. A very important building has gone dark. Move your attention to the front of the brain, right behind the forehead. This is the prefrontal cortex. In the daylight, this is the CEO of your life. This is the part of the brain responsible for logic, for planning, for impulse control, and for reality testing. It is the rational editor that stands between you and the world, whispering, "That doesn't make sense," or "You shouldn't do that," or "That is impossible." It is the voice of reason. But during REM sleep, the prefrontal cortex is chemically inhibited. The lights are turned off. The editor has hung up his coat and gone home for the night. The CEO is on vacation. This is perhaps the most critical feature of the dreaming brain. Without the logical oversight of the prefrontal cortex, the brain is left without a filter. This is why dream logic is so beautifully, wonderfully absurd. It is why you can be in your childhood bedroom one moment, walk through the door, and suddenly be standing in the middle of a desert in Egypt. And in the dream, you don't stop and say, "Wait a minute, this is geographically impossible." You simply accept it. You think, "Ah, yes, the desert, of course." It is why people can morph into other people. You might be talking to your boss, but suddenly they have the face of your grandmother, and yet you still know it is your boss. The part of your brain that would normally flag these errors, the part that checks for continuity and realism, is asleep. So you accept the impossible. You accept that you can breathe underwater. You accept that gravity is optional. You accept that you are late for an exam for a class you haven't taken in 20 years. The dreaming brain is a theater where the critic has been barred from entering. The play goes on, wild and unscripted, and the audience, you, watches with total suspension of disbelief. But if the critic is gone, who is writing the script, and who is painting the scenery? Let us move to the back of the brain, to the occipital lobe. This is the home of the visual cortex. When your eyes are open, this region processes the light that floods in through your retinas. It tells you that the grass is green, that the sky is blue, that the room has depth and shadow. But right now, your eyes are closed. You are in a pitch-black room. There is no light entering the system. And yet, the visual cortex is firing wildly. It is generating images from the inside out. It is pulling data not from the world, but from your memory and projecting it on the screen of your mind. And it is a powerful projector. Dream visuals can be incredibly rich. Think of the texture of a dream, the shine of wet pavement under a street lamp, the impossible iridescent color of a bird's wing, the face of a stranger that your mind has invented from scratch. This internal seeing is so convincing that to the brain it is indistinguishable from actual sight. You are hallucinating a reality that consumes your entire field of vision. And connecting all of these, the emotion of the amygdala, the blindness of the prefrontal cortex, the visuals of the occipital lobe, is the hippocampus. The hippocampus is the librarian. It is the structure responsible for memory. During the day, it has been busy collecting new books, new faces, new facts, and now at night it is opening those books and cross-referencing them with the old archives. It takes a fragment of yesterday, a conversation you had with a cashier, and stitches it together with a memory from 10 years ago, the smell of your grandmother's kitchen. It takes the stress of a deadline you are facing tomorrow and blends it with the image of a tidal wave you saw in a movie once. The hippocampus is the weaver. It pulls the threads of your life, the recent and the ancient, the trivial and the profound, and weaves them into a tapestry. It creates a narrative collage. This is why dreams feel like a remix of your life. They are familiar yet distorted. They are you, but a version of you seen through a kaleidoscope. So, here is the state of the union in the dreaming mind. The logic center is dark, the emotion center is blazing, the visual center is painting furiously, and the memory center is shuffling the deck. It is the perfect recipe for a wild, emotional, vivid, and nonsensical journey. But why? Why does the brain do this? Why spend so much energy running this internal cinema when it could just rest? Why terrify us with nightmares or confuse us with riddles? Is it just random noise? Is it just the static of the brain sweeping the floors, a few neurons firing accidentally as they clean up the mess of the day? Or is there a purpose? Some scientists believe that this state, this high-energy, low-logic simulation, is a training ground. Think about it. In a dream, you are often practicing survival. You are running, you are searching, you are navigating social conflicts. You are feeling fear, but you are safe in bed. You are feeling grief, but you have lost nothing. Perhaps the dream is a flight simulator. It is a virtual reality program designed by evolution to let you practice being human, to let you practice reacting to danger, to loss, to surprise, without the real-world consequences. Or perhaps it is emotional digestion. Just as your stomach breaks down food to extract the nutrients, perhaps your dreaming brain breaks down the emotional experiences of the day. It strips away the sharp edges of a painful memory, turning a trauma into a story, filing it away so that when you wake up, the burden is a little lighter. We will explore these theories deeply as we drift further down the river. But for now, just marvel at the machine itself. Marvel at the fact that right now, as you listen to my voice, your brain is preparing to do this for you. It is preparing to shut down the logic. It is preparing to ignite the imagination. It is preparing to take you on a journey that no one else will ever see, a private screening in the theater of the skull. It is a gift of biology, a nightly reminder that you are more than just a logical creature. You are a creature of story. You are a creature of feeling. And soon, the curtain will rise. The lights in the logic center will fade to black. The projector will whir to life, and the show will begin. Chapter 4: The Ancient Whisper. We have looked at the machinery. We have traced the wires and observed the sparks of the biological engine. We know how the brain dreams, how the neurons fire and the chemicals flow. But knowing how a violin is made does not explain the music. Knowing that the amygdala lights up does not explain why you dreamt of a house you haven't lived in for 20 years, or why the wind in that dream whispered a secret you couldn't quite hear. For as long as there have been human beings, there has been the question, why? Long before we had fMRI machines to peer into the skull, long before we understood electricity or neurotransmitters, our ancestors looked into the dark mirror of the night and saw something profound staring back. Imagine, if you will, a time before electric light. The sun sets and the world is plunged into a darkness far deeper and more absolute than anything we experience in our modern cities. There is no hum of traffic, no glow of street lamps. There is only the fire, crackling and spitting in the hearth, and then silence. In this ancient world, sleep was not just a pause, it was a departure. It was a journey into another realm entirely. To the people of ancient Egypt, the dream world was as real as the waking one, perhaps even more real. They believed that when a person slept, they were not merely resting, they were traveling. The soul was untethered, free to wander the spaces between the earth and the heavens. They saw dreams as messages. If you were an Egyptian living along the banks of the Nile 3,000 years ago and you had a vivid dream, you would not dismiss it as just a dream. You would treat it as a letter delivered by a divine courier. They had priests, known as the masters of the secret things, whose sole job was to read these letters. They wrote dream books, elaborate manuals of symbols and meanings written on papyrus scrolls. If you dreamt of a deep well, it meant one thing. If you dreamt of drinking warm beer or weaving cloth or seeing a crocodile, it meant another. To them, the dream was a window. Sometimes it looked into the future, offering a warning or a prophecy. Sometimes it looked into the will of the gods. But it was always significant. It was always a conversation with the invisible. Move forward in time, across the Mediterranean Sea to the marble temples of ancient Greece. Here, dreams were not just messages, they were medicine. The Greeks built great sanctuaries to Asclepius, the god of healing. These were not hospitals in the way we think of them, sterile and bright. They were places of ritual and quiet, nestled in groves of cypress trees, filled with the scent of herbs and the sound of running water. Pilgrims who were sick or troubled would come to these temples to practice incubation. They would purify themselves, offer prayers, and then lie down to sleep in a sacred dormitory called the abaton. They slept among non-venomous snakes that slithered quietly across the stone floors, the symbol of the god. They slept with the hope that Asclepius would visit them in the night. They believed that the cure would come in the dream itself. Perhaps the god would perform a surgery on them while they slept. Perhaps he would whisper a recipe for a poultice or a change in diet. Or perhaps the dream itself was the healing and realignment of the soul that would manifest in the body. Imagine the faith of that act, to travel for miles, to lie down in the dark among strangers and snakes, and to trust that the most powerful medicine in the world would come to you when your eyes were closed. To the ancients, the source of the dream was external. It came from somewhere. It came from the gods, from the spirits, from the ancestors. It was a visitation. But as the centuries turned, the pendulum swung. The Enlightenment arrived. The Industrial Revolution roared to life with its steam engines and factories. The world became obsessed with reason, with logic, with the tangible and the measurable. In this new world of clockwork and science, dreams lost their magic. They were demoted. They were dismissed as nonsense. Scientists of the 19th century waved them away as nothing more than the result of indigestion, a bit of spicy cheese or a heavy meal causing the brain to misfire. They were seen as the mental equivalent of a burp, random noise, meaningless static. The dream world went quiet. It was ignored, left to gather dust in the attic of scientific inquiry. And then, at the turn of the 20th century, a man in Vienna lit a candle in the dark. Sigmund Freud. In 1899, he published a book called The Interpretation of Dreams, and with it, he shifted the gaze of humanity. He took the source of the dream from the sky and placed it firmly back inside the human mind. Freud argued that dreams were not messages from the gods, they were messages from us. He famously called dreams the royal road to a knowledge of the unconscious activities of the mind. Imagine your mind as a house. The ground floor is your waking life. It is where you entertain guests, where you cook dinner, where you make polite conversation. It is tidy, logical, and respectable. But Freud suggested that this house has a basement, a deep, sprawling cellar that is locked to the public. And in this basement, we keep the things we do not want to see. We keep our primal desires, our secret jealousies, our forbidden rages, and our oldest, deepest wounds. According to Freud, the door to this basement is guarded. During the day, the guard is vigilant. He keeps the monsters downstairs. But at night, when we sleep, the guard gets tired. He dozes off. And while he sleeps, the residents of the basement slip past him. But they are clever. They know that if they show their true faces, the dreamer will wake up in horror. So they wear masks. They dress up in costumes. A forbidden desire might dress up as a train entering a tunnel. A suppressed anger might dress up as a thunderstorm. A fear of failure might lose their teeth. Freud called this wish fulfillment. He believed that every dream, no matter how strange or scary, was ultimately an attempt by the subconscious to satisfy a hidden urge. He taught us to look at the dream as a puzzle, a code to be cracked. He taught us that the dream is not about the train, it is about what the train represents. Whether or not you agree with Freud's specific interpretations, and many modern scientists do not, his impact was seismic. He validated the inner life. He told the world that the stories we tell ourselves at night matter, that they are made of the same stuff as our deepest selves. But the story of interpretation does not end with Freud. It expands with his student, his friend, and eventually his rival, Carl Jung. If Freud saw the dream as a basement full of secrets, Jung saw it as a vast, ancient forest. Jung agreed that dreams came from the unconscious, but he didn't think it was just a personal dumping ground for repressed desires. He believed in something far larger, far more mystical. He called it the collective unconscious.
Jung believed that beneath our individual memories, beneath your childhood, your job, your specific fears, there is a deeper layer of mind that is shared by all human beings, a reservoir of wisdom and imagery that we inherit just by being born human. Think of it like the internet. Your personal computer has its own files, its own photos, its own documents. That is your personal unconscious. But your computer is also connected to a vast worldwide web of information that exists outside of you, yet is accessible to you. That is the collective unconscious. This, Jung argued, is why people from completely different cultures who have never met and never spoken often dream of the same things: the shadow, the wise old man, the great mother, the hero, the flood, the tower. He called these archetypes. They are the universal blueprints of the human story. When you dream, Jung said, you are not just processing your own day. You're tapping into this ancient well. You are speaking the language of the species. For Jung, a dream was not trying to hide something, as Freud thought. It was trying to reveal something. It was trying to restore balance. If you were too rigid and logical in your waking life, your dreams might be wild and chaotic to compensate. If you were feeling small and powerless, you might dream of being a king or a giant. The dream was a message from the self to the self, a nightly attempt to make you whole. So where does this leave us as we lie here in the dark of the 21st century? We have the ancient Egyptians whispering that dreams are gods. We have the Greeks whispering that dreams are healers. We have Freud whispering that dreams are secrets. We have Jung whispering that dreams are myths. And standing beside them, we have the modern neuroscientist, holding a brain scan whispering that dreams are electrical impulses and memory consolidation. Who is right? Perhaps they all are. Perhaps the dream is a prism. If you hold it up to the light of religion, it looks like a message. If you hold it up to the light of psychology, it looks like a symptom. If you hold it up to the light of biology, it looks like a function. But for the dreamer, for you, lying there in the quiet, the theory matters less than the feeling. The feeling of walking through a house that is both yours and not yours. The feeling of seeing a face you thought you had forgotten. The feeling of waking up with a solution to a problem you didn't know you had. History shows us that we have always taken our dreams seriously. We have always felt, instinctively, that when the lights go out, something important begins. We have always felt that the night is not empty, it is full. And as you drift closer to your own dreams tonight, remember that you are part of this lineage. You are part of the long, unbroken chain of dreamers stretching back to the caves. When you close your eyes, you are stepping into the same river that the pharaohs bathed in. You are wandering the same forests as the philosophers. You are entering the same basement, the same temple, the same vast starry expanse of the human mind. You are going to a place where the ancestors are waiting. And who knows, perhaps tonight the message they have for you is simply this: rest. You are safe. The story continues. Chapter 5. The Silent Alchemist. We have spoken of the brain as a machine, a city, and a temple, but there is another role it plays, one that is perhaps the most tender and essential of all. As we drift deeper into the night, let us consider the weight of the day you have just left behind. Even on the best of days, being human is a heavy task. We move through a world of sharp edges and sudden turns. We navigate complex social currents. We worry about the future. We regret the past. We carry conversations that went wrong, disappointments that stung, and anxieties that hum in the background like a low-voltage wire. By the time we reach the edge of the bed, our minds are often cluttered. We are carrying a backpack full of emotional stones. If we carried these stones forever, adding new ones every day, we would eventually be crushed by the weight. We would become brittle, reactive, and overwhelmed. But we don't. We wake up the next morning, and somehow the burden feels lighter. The sharp sting of an insult feels duller. The panic of a mistake feels manageable. The grief feels a little more like a memory and a little less like a wound. How does this happen? It happens because while you sleep, your brain becomes an alchemist. There is a beautiful theory in modern neuroscience, championed by researchers like Matthew Walker, that suggests dreaming is a form of overnight therapy. It is emotional first aid. Let us return to that glowing city inside your skull. We know that during REM sleep, the dream state, the emotional centers of the brain are highly active. The amygdala is burning bright, pulling up the files of your recent emotional experiences. But there is a crucial difference between the waking brain and the dreaming brain, a difference that comes down to a single chemical, norepinephrine. This is a stress chemical. It is the molecule of anxiety, of fight or flight. When you are awake and something frightens or upsets you, norepinephrine floods your system. It is what makes your hands shake, your heart race, and your memory sear the event into your mind with painful clarity. But during REM sleep, for the only time in the entire 24-hour cycle, the release of norepinephrine is completely shut off. The brain creates a chemical sanctuary, a safe room. In this unique, stress-free environment, the brain dares to open the dangerous files. It takes out the memories of the day, the argument, the worry, the fear, and it replays them. But because the stress chemical is absent, you can experience these memories without the visceral physical reaction. You can review the footage without the panic. Think of it like taking the sting out of a wasp. The memory remains. You remember the wasp, you remember it landing on you, but the poison is removed. This is why we dream of stressful things. Have you ever wondered why, when you are stressed, your dreams seem to echo that stress? You might dream of losing your passport, or failing a test, or being lost in a strange city. It is tempting to think that your brain is punishing you. Why, you might ask, can't I just dream of a tropical beach? Why must I relive the anxiety? But your brain is not punishing you. It is processing. It is taking the raw, jagged experience of the day and running it through the wash cycle. It is turning it over and over in the safe, chemical bath of sleep, smoothing down the sharp edges. Imagine a rough stone thrown into a river. The stone is your worry. The river is your dream. At first, the stone is jagged. It cuts your hand if you hold it. But all night long, the water rushes over it. The current tumbles it, rolls it, washes against it. The dream story might be chaotic. The water might be turbulent, but the work is being done. By morning, the stone is still there. The memory hasn't vanished, but it is smooth. It is round. You can hold it in your hand without bleeding. This is the gift of the night. It explains the old wisdom of the phrase, "sleep on it."
How many times have you gone to bed angry, confused, or heartbroken, feeling that the world was ending? And yet, when the sun comes up, the feeling has shifted. The anger has cooled into annoyance. The heartbreak has softened into sadness. The confusion has settled into acceptance. You didn't fix the problem. You didn't change the world. You simply slept. And in that sleep, the silent alchemist transmuted your pain into wisdom. But the brain does not just process the negative, it is also a master of connection. While you sleep, the brain is not just stripping away emotion, it is also building bridges. It is taking the new experiences of the day and weaving them into the tapestry of your entire life. It asks, where does this fit? It takes the conversation you had with a stranger today and connects it to a book you read 5 years ago. It takes the feeling of the wind on your face this afternoon and connects it to a childhood memory of the beach. This is why dreams are so bizarre. In the waking world, we categorize things neatly. Work goes in the work box, family goes in the family box, the past stays in the past. But in the dream world, the boxes are overturned, the contents are spilled out onto the floor, and the brain starts to play. It creates a collage. It puts your boss in your childhood kitchen. It puts your dog in the driver's seat of your car. It blends the face of your partner with the face of a celebrity. It looks like chaos. It looks like nonsense. But scientists believe this associative mashup is actually a form of brilliance. It is the brain searching for patterns. It is testing weak connections to see if they hold weight. By mixing things up in these strange, surreal combinations, the brain often discovers solutions that the logical waking mind would miss. This is the source of creative dreaming. History is filled with stories of artists, scientists, and inventors who went to bed with a problem and woke up with an answer. Dmitri Mendeleev was struggling to organize the elements of the universe. He worked for days, exhausted, until he finally collapsed into sleep. And there, in the theater of his mind, he saw a table where all the elements fell into place as if by magic. He woke up and wrote down the periodic table. Paul McCartney woke up one morning with a melody playing in his head, a tune so complete and perfect he thought he must have heard it on the radio. It turned out to be the song "Yesterday." Mary Shelley dreamt of a pale student of unhallowed arts kneeling beside the thing he had put together, a vision that became Frankenstein. Why does this happen? Because in the dream, the no voice is turned off. The inner critic that says, "That's silly," or "That won't work," is asleep. Your brain is free to think sideways. It is free to make leaps of logic that are impossible in the daylight. It wanders off the path and finds the hidden treasure in the woods. So if you are stuck on a problem in your waking life, a creative block, a difficult decision, a relationship issue, do not force it. Do not sit at your desk until your eyes burn, staring at the screen. Step away, turn off the lights, lie down. Trust the alchemist. Hand the problem over to the night shift. Say to your brain, "Here, I cannot solve this. You take it for a while." And then let go. As you lie here now, feel the comfort of that surrender. You do not have to be the one in charge anymore. You do not have to hold the weight of your emotions or the complexity of your problems. You are entering the sanctuary. The chemicals are shifting. The stress is draining away, leaving your body like water draining from a tub. The guard is stepping aside. The alchemist is lighting the fire. Whatever you are carrying tonight, whatever worry, whatever fear, whatever question, visualize yourself placing it in a basket by the door of your sleep. You do not need to bring it inside with you. The dream will come out and pick it up. It will wash it. It will polish it. It will hold it up to the light of the stars and see what it is really made of. And while that work is happening, you will be floating. You will be flying over oceans of toast, or walking through forests of blue trees, or simply drifting in the warm, dark void of rest. You are being healed, even if you do not feel it. You are being put back together, piece by piece, softer and stronger than before. So let the day go. It is done. It has been recorded. It has been handed over. Now there is only the river, the slow, steady current that carries you away from the shore of the known and into the mist of the possible. Let us drift further down this river. Let us see what other tasks the brain is performing in the secret workshops of the night. For the alchemist is not the only worker in the city. There is also the librarian, and there is the builder, and they have much to do before the sun rises. Chapter 6. The Silent Librarian. We have spoken of the alchemist who transmutes your emotions, soothing the burns of the day, but there is another figure who walks the halls of your mind while you sleep, a figure of quiet precision, infinite patience, and careful hands. Let us call this figure the librarian. Consider for a moment the sheer volume of information that flooded into your brain today. From the moment you opened your eyes this morning, you were inundated. You saw thousands of faces, some real, some on screens. You read headlines, street signs, text messages. You heard snippets of songs, the hum of traffic, the tone of a friend's voice. You learned a new fact, perhaps, or remembered an old appointment. You felt the texture of your coffee cup, the temperature of the wind, the ache in your lower back. If your brain kept every single scrap of this data, every license plate you glanced at, every color of every shirt you passed on the street, it would be overwhelmed. It would become a hoarder's house, stacked floor to ceiling with useless clutter. You would be unable to find the important things, the name of your partner, the solution to a problem, the memory of a perfect sunset, because they would be buried under the noise of the irrelevant. And so every night the librarian goes to work. This process is scientifically known as memory consolidation, but that term feels too cold for such a beautiful act. It is really a process of curation. The center of this activity is the hippocampus. We met the hippocampus earlier, the weaver of dreams, but its day job is to act as a temporary inbox. It is a small, curved structure shaped like a seahorse, nestled deep in the center of the brain. During the day, it catches everything. It holds the new memories in a fragile, temporary state.
But the hippocampus has limited storage. It's like a USB stick that fills up quickly. If it isn't emptied, it cannot learn anything new tomorrow. So when you enter the deep, slow wave sleep of the night, a dialogue begins. The hippocampus wakes up and starts to whisper to the cortex, the outer wrinkled layer of the brain, which acts as the hard drive, the permanent vault. Imagine a vast, dimly lit library with high, vaulted ceilings. It is night. The public has gone home. The silence is thick and velvety. The librarian moves through the aisles. They are carrying a basket filled with the day's intake, a jumbled pile of books, loose papers, and photographs. They pick up a memory. Let's say it is the conversation you had with a friend today. The librarian looks at it. Is this important? Does this carry emotional weight? Is this a lesson? Is this a connection? If the answer is yes, the memory is strengthened. It is taken out of the fragile basket of the hippocampus and placed securely on the sturdy oak shelves of the cortex. It is filed away in the section for friendship or joy or advice.
This transfer is physical. Scientists have observed that the electrical firing patterns that occurred when you learned something during the day are replayed at high speed while you sleep. Your brain literally rehearses the memory, etching the groove deeper, turning a faint trail in the grass into a paved road. This is why, if you are learning to play the piano or studying a new language, sleep is not just a break from practice, it is practice. You might struggle with a piece of music all afternoon, your fingers fumbling over the keys. You go to sleep frustrated, but while you rest, the librarian is there, running the scales, polishing the movements. You wake up the next morning, sit at the piano, and suddenly your fingers know the way. The memory has been moved to the vault. It has become part of you. But the librarian has another job, one that is just as important as saving memories: forgetting. The librarian picks up another scrap from the basket. It is the memory of the pattern on the bus seat you sat on this morning, or the random string of numbers on a receipt you threw away. Is this important? No, the brain whispers. We do not need this. And so the memory is discarded. The connection is severed. The synaptic pathway is allowed to fade. This process is sometimes called synaptic pruning or downscaling. Imagine a beautiful, overgrown garden. If you let everything grow wild, the weeds would choke the roses. The vines would block the sun. To keep the garden healthy, you must prune. You must cut back the weak branches so the strong ones can flourish. Sleep is the pruning of the mind's garden. It creates space. It clears the desktop. It wipes the slate clean so that when you wake up tomorrow, you have room to learn again. You have the mental bandwidth to be curious, to be attentive, to be present. Without this nightly cleaning, your brain would be noisy. It would be buzzing with static. You would feel foggy, overwhelmed, unable to focus. We have all felt this after a night of poor sleep, the feeling that the brain is full of cotton wool, that thoughts are wading through treacle. That is the feeling of a library that hasn't been tidied. But when you sleep well, you wake up with that crisp, clear feeling. The shelves are organized, the floors are swept, the sun is streaming through the windows of the mind. There is a profound comfort in this. It means you do not have to hold on so tight. You do not have to worry about remembering every detail, every lesson, every moment. You can trust the machinery of your mind. You can trust the librarian. As you lie here now, let that trust wash over you. Visualize the thoughts of the day as leaves floating on the surface of a pond. You do not need to collect them. You do not need to organize them. Let them sink. Let them drift. Somewhere deep inside, the work is being done. The keepers of the archive are moving silently in the dark. They are saving what matters. They are letting go of what doesn't. They are writing the story of your life into the permanent ink of memory, all while you do nothing but breathe. The library is safe. The doors are locked. The silence is holding you. And as the librarian finishes her work on the memories of the past, the brain begins to turn its attention to something else, something older, something primal. It begins to look toward the future. It begins to run simulations. Because the night is not just for remembering where you have been, it is also for preparing you for where you might go. Chapter 7. The Midnight Simulator. The librarian has filed away your memories. The alchemist has soothed your emotions. The city of your mind is humming with the quiet, organized rhythm. But as the night deepens and the brain slips into the most vivid cycles of REM sleep, a new function begins to whir to life. The scene shifts. The internal projector changes reels. We are no longer just looking back at what has happened. We are looking forward to what might happen. Welcome to the simulator. There is a fascinating theory in evolutionary biology known as the threat simulation theory. It suggests that dreaming is not just about processing the past, but about rehearsing for the future. It proposes that the dream world is a virtual reality training ground designed by millions of years of evolution to keep you safe. Imagine for a moment our ancient ancestors. They lived in a world of constant, immediate danger. A rustle in the grass could be a lion. A shadow in the water could be a crocodile. A storm could mean freezing to death. To survive, they needed sharp instincts. They needed reflexes faster than thought. But you cannot practice running from a lion in real life. The stakes are too high. You get one chance. If you fail, the game is over. So nature devised a brilliant solution. It gave us a safe space to practice. It gave us the nightmare. I know, nightmare is a heavy word. We tend to dislike them. We wake up, heart pounding, sweating, wishing we could erase the images from our minds. But consider the nightmare not as a torment, but as a drill. In the safety of sleep, paralyzed by the REM lock so you can't hurt yourself, your brain conjures a threat. It creates a predator. It creates a fall from a great height. It creates a situation where you are lost or trapped or being chased. And then it watches. What will you do? Will you run? Will you fight? Will you freeze? It tests your neural pathways. It fires the circuits of fear and reaction, strengthening them, oiling the gears of your survival instincts. It is a flight simulator for the human animal. When you wake up from a dream where you were running from a shadow, your heart is racing because your body believes you just survived. You just put in a solid hour of survival training. You are, theoretically, sharper, faster, and more ready for the waking world than you were when you went to bed. But we aren't running from lions anymore. We live in cities of glass and steel. Our predators are different now. And so, the simulator has updated its software. Instead of saber-toothed tigers, we dream of social threats. We dream of showing up to work naked. We dream of failing an exam. We dream of shouting but no sound coming out. These are the modern equivalents of being eaten. To a social primate like a human, being embarrassed, being ostracized, or failing in front of the tribe is a form of death. It is a threat to our standing, our safety. So the brain rehearses these scenarios too. It puts you in the worst-case scenario. You forgot your speech, everyone is staring, and it forces you to navigate the emotions. It forces you to sit with the vulnerability. It is uncomfortable, yes, but it is purposeful. It is your brain asking, if the worst happens, can you handle it? And usually, the answer is yes. You wake up, the relief washes over you. It was just a dream, you say. But deep down, you have faced the fear. You have walked through the fire and come out unburned. But the simulator has another job, one that is just as important as saving memories: skill. Have you ever heard of the Tetris effect? In the early days of video games, researchers noticed something strange. People who played Tetris for hours a day would report seeing falling blocks in their dreams. As they drifted off to sleep, their minds would continue to rotate the shapes, fitting them into lines. This wasn't just an obsession, it was learning. Studies have shown that if you are trying to learn a new physical skill, like skiing or juggling or dancing, your brain will rehearse those movements while you sleep. Imagine a skier. During the day, they are on the mountain, their muscles straining, their mind focused on balance and speed. They fall, they get up, they try again. At night, the body lies still, but in the motor cortex of the brain, the neurons are firing in the exact same sequence: left turn, shift weight, right turn, balance. The brain is running the simulation over and over, refining the neural pathway, smoothing out the glitches. It is practicing without the risk of breaking a leg. And the results are real. People who sleep after learning a skill often perform better the next day than people who stay awake. The dream has made them better. The dream has coached them. There is something incredibly moving about this. It means that even when you feel like you are doing nothing, when you are just lying there, oblivious to the world, your brain is fighting for you. It is trying to make you stronger. It is trying to make you smarter, faster, more resilient. It is working tirelessly in the dark to ensure that when you open your eyes to the morning sun, you are the best possible version of yourself. So if you find yourself in a strange dream tonight, if you are running through a labyrinth, or debating with a giant, or trying to catch a bus that flies, do not be afraid. You are simply in the simulator. You are in the training dojo of the mind. You are safe. You are tethered to your bed. Let the scenario play out. Let the brain run its drills. Visualize yourself as a pilot in a simulator, calm and collected. The storm outside the cockpit window looks real. The turbulence feels real. But you know the ground is solid beneath you. You are merely preparing for the flight of your life. And as the simulation ends and the adrenaline fades, the brain shifts gears once more. It moves from the high-stakes drama of survival to something softer, something stranger. It moves into the realm of the lucid. For sometimes, in the middle of the simulation, the pilot wakes up and realizes, wait, I am flying the plane. And that is where the true magic begins. Chapter 8. The Waking Dreamer. We have explored the automatic nature of dreams, how they wash over us like waves, pulling us into their currents without our consent. Usually, we are passengers in these vessels, drifting wherever the river takes us. We accept the strange logic. We accept the changing scenery. We are simply along for the ride. But sometimes, rarely, and wonderfully, the passenger wakes up and takes the wheel. This is the phenomenon of lucid dreaming. Imagine you are in a dream right now. You are walking through a meadow of tall silver grass. The sky above you is a shade of purple that doesn't exist in the waking world. You see a house in the distance, but as you walk toward it, the house transforms into a giant ticking clock. In a normal dream, you would simply nod and say, "Ah, yes, the clock house." But in a lucid dream, something shifts. A tiny spark of critical thought ignites in the darkness. You stop, you look at the clock, you look at the purple sky, and a question forms in your mind. Is this real? And then the realization washes over you like a cool breeze. No, I am dreaming. In that moment, the world of the dream does not collapse. It remains. The grass is still silver, the sky is still purple, but your relationship to it has changed completely. You are no longer trapped in the script. You are the director. This state is a neurological hybrid. It is a rare moment where the prefrontal cortex, that logical CEO we spoke of, who usually takes the night off, clocks back in for a brief moment. It doesn't wake up fully. It wakes up just enough to give you self-awareness, while the rest of the brain continues to hallucinate. It is a delicate balance, like walking a tightrope between the sleeping and waking worlds. For those who experience this, the sensation is often of euphoric freedom. If you know you are dreaming, you know you are safe. The monster chasing you becomes harmless. You can simply turn around and ask it why it is running. The cliff edge is no longer a threat. It is a launching pad. Flight is the most common desire of the lucid dreamer, and why wouldn't it be? To push off the ground and feel the sensation of gravity dissolving, to soar over the rooftops of your own imagination, seeing the city of your mind spread out below you like a glittering map. There are even techniques that dreamers use to trigger this state, little tests called reality checks. They might try to read a sentence in a book. In a dream, text is notoriously unstable. It shifts and scrambles when you look away. Or they might look at their hands. In a dream, hands often look strange, too many fingers, or made of wax. These are the keys that unlock the door. But whether you try to control your dreams or simply let them happen, the existence of lucid dreaming tells us something profound about the human mind. It tells us that consciousness is not an on-off switch. It is a dimmer. It is a spectrum. We can be awake, we can be asleep, and we can be something in between, a conscious traveler in an unconscious world, exploring the hidden rooms of our own being with a flashlight in hand. So if you find yourself tonight in a place that feels just a little too strange, if the gravity feels light or the colors feel too bright, pause, look at your hands. You might just find that you are free to fly. But we are not the only ones who travel these landscapes. We are not the only ones who run and fly and seek in the dark. Chapter 9, The Silent Menagerie. Let us step away from the human mind for a moment. Let us leave the complexities of logic and lucidity and look at the simpler, purer dreamers who share our homes and our world. Picture a dog sleeping on a rug in a patch of moonlight. He is lying on his side. His breathing is a rhythmic huffing sound, and then it begins. His paws twitch, his legs paddle the air, a phantom sprint. His nose wrinkles, sniffing a scent that isn't there. He lets out a soft, muffled bark, a woof that stays trapped in his throat. We watch this and we smile. We say, he is chasing rabbits. And science suggests we are right. For a long time, we wondered if animals truly dreamed, or if their sleep was just a blank void. But as we have peered closer into the brains of our fellow creatures, we have found that the architecture of sleep is not unique to humans. It is an ancient biological inheritance. Almost all mammals and birds experience REM sleep. They all enter that state where the body is still and the brain is wild. Researchers at MIT once looked into the brains of sleeping rats. They had spent the day watching the rats run through a maze, measuring the specific pattern of neurons that fired as they turned left, then right, and then found the food. Later, while the rats slept, the researchers watched the monitors, and there, in the silence of the lab, the pattern repeated. The exact same neurons fired. Left, right, food. The rat was running the maze again. It was replaying its day, consolidating the memory, learning the path. It was dreaming of its world. And it is not just mammals. In the trees, young zebra finches dream of songs. These birds learn to sing by listening to their elders, but they perfect their tunes in their sleep. During the night, the neurons in their vocal centers fire in the rhythm of the song, rehearsing the melody silently, over and over, so that when dawn breaks, they can sing it true. But perhaps the most beautiful dreamer of all lives beneath the waves, the octopus. This creature, so different from us, with a brain distributed into its 8 arms, also sleeps, and it also dreams. When an octopus enters its version of active sleep, it puts on a show. In the waking world, the octopus changes the color and texture of its skin to hide from predators or to communicate. It can become a rock, a coral, a shadow. When it sleeps, these changes happen spontaneously. An octopus dozing in a tank will suddenly flash bright yellow, then it will turn the mottled brown of the sand. Then it will ripple with the dark bands of a threat display. It is wearing its dream on its skin. We cannot know for sure what the octopus is seeing. Is it dreaming of a crab it hunted? Is it dreaming of hiding from a shark? We can only watch the colors shift like a silent movie projected onto its body. There is something profound. There is a profound comfort in this connection. It reminds us that dreaming is not a burden of human consciousness. It is not a side effect of our complex lives. It is a fundamental part of being alive. It connects the dog on the rug to the bird in the tree, to the octopus in the reef, to you, lying in your bed. We are all part of a vast, silent menagerie, closing our eyes against the dark and turning inward. We are all running mazes. We are all chasing rabbits. We are all practicing our songs for the morning. When you sleep tonight, you're joining a chorus that spans the entire animal kingdom. You are part of the great breathing rhythm of life on Earth. You are never truly alone in the dark. Chapter 10: The Shadow Side. We have spoken of dreams as libraries, as playgrounds, and as healers. But we must also acknowledge the rooms in the house that are kept locked, the corridors where the shadows stretch a little too long, the dreams that make us wake with a gasp, our hands clutching the sheets. The nightmare. It is a universal human experience. There is not a soul on this earth who has not, at some point, run from a monster that wasn't there. When we talk about nightmares, our instinct is to push them away. We view them as failures of sleep, glitches in the system that ruin our rest. But if we look at them through the lens of science and compassion, we might see them differently. We might see them as guardians. Remember the simulator. We discussed how the brain practices survival skills. A nightmare is simply the simulator running a high-intensity drill. If the brain wants to teach you how to handle fear, it cannot show you a picture of a kitten. It has to show you a storm. It has to make the danger feel real so that your emotional response is real. When you dream of being chased, or of falling, or of losing your voice, your brain is checking your wiring. It is asking, are the alarms working? Is the adrenaline pump ready? Can you endure this pressure? It is a fire drill. It is loud, it is unpleasant, and it disrupts the peace. But it is there to ensure that if a real fire ever comes, you know exactly where the exit is. But there are other kinds of shadows too, the shadows of grief. For those who have lost someone they love, the dream world can become a place of reunion. It is common after a loss to see the departed in our sleep. Sometimes these dreams are painful. The person is there, but they are distant or they do not speak. We wake up with the fresh ache of their absence. But often, these dreams are gifts. You sit at a table with them. You hear their laugh, not a memory of their laugh, but the sound itself, clear and bright. You feel the warmth of their hand. For a few minutes, the laws of death are suspended. The brain, in its mercy, has rebuilt them from the archives of your memory, letting you have one more conversation, one more moment of connection. Psychologists believe these dreams are part of the work of mourning. They are the mind trying to integrate the reality of loss with the persistence of love. They are a space where we can say the things we left unsaid. So if you find yourself in a darker dream tonight, try not to fear it. If you are running, know that you are practicing courage. If you are falling, know that you are practicing trust. If you are grieving, know that you are practicing healing. You are safe in your bed. The shadows cannot hurt you. They are merely clouds passing over the moon, dark for a moment, but destined to drift away. Chapter 11: The Frontier of the Mind. As we near the end of our journey, let us look forward. Let us look at the horizon where science meets science fiction. For thousands of years, the dream has been a private experience. It was the one thing in the world that was truly, completely yours. No one could see what you saw. No one could watch your internal movie. But the walls of that privacy are becoming translucent. In laboratories around the world, in quiet rooms filled with the hum of servers and the glow of monitors, scientists are beginning to peek behind the curtain. Using fMRI machines, massive magnets that can map the blood flow in the brain, researchers have begun to decode the visual language of sleep. In a groundbreaking experiment in Japan, scientists scanned the brains of people as they fell asleep. When the machine detected a visual pattern, they would wake the person up and ask, "What were you seeing?" The person might say, "I saw a car," or "I saw a man." The computer learned. It learned what a dream car looks like in the language of neurons. It learned the electrical signature of a dream man. And then they let the person sleep. The computer watched the brain activity. It saw the patterns emerge. And without waking the dreamer, the computer predicted they are seeing a car. It was right. We are not yet at the point where we can record your dreams like a movie on a DVD. The images we can decode are hazy, blurs of shape and color, like looking through thick fog. But the door has been cracked open. Imagine a future where you could wake up in the morning and press play. Imagine watching the flight you took over the city or the conversation you had with the talking dog. Imagine being able to show someone else the beautiful, impossible things your mind created. It is a wondrous thought, but it is also a quiet warning, because the dream is perhaps the last true sanctuary. It is the place where we are free to be irrational, to be strange, to be broken, to be wild, without judgment. If we pull the dream out into the light of day, do we lose some of its magic? Does a dream need to be seen to be real? Or is its power in its secrecy? Perhaps some things are meant to stay in the dark. Perhaps the value of the dream is not in the data it provides, but in the feeling it leaves behind. Science will continue to march forward. We will map more neurons, we will decode more signals, but I suspect that the heart of the dream, the deep emotional mystery of it, will always remain just out of reach. And that is a good thing. We need a little mystery. We need a place where we are unobserved, where we can simply be. Chapter 12: The Return. And so we come to the end of the cycle. We have descended the stairs. We have swum through the deep waters. We have walked the glowing streets of the city. We have met the alchemist, the librarian, and the pilot. We have asked the question, why do we dream? And the answer, it seems, is everything. We dream to remember. We dream to forget. We dream to heal our hearts. We dream to practice our courage. We dream to solve problems. We dream to play. It is not a glitch. It is not an accident. It is the most sophisticated, beautiful, and essential maintenance program in the natural world. It is your brain loving you. It is your mind working tirelessly every single night to make sure that you are ready for the joy, the pain, the confusion, and the beauty of being alive. So now, as you lie here, let all the theories fade away. You do not need to understand the science to receive the gift. You do not need to know how the engine works to let the car carry you home. Feel the weight of your body on the mattress. Feel the air cool against your skin. Feel the slow, steady rhythm of your own breath, in and out. You have done enough today. You have learned enough. You have carried enough. It is time to hand over the keys. The night shift is clocking in. The lights in the internal center are dimming. The stars in the internal city are beginning to shine. The river is waiting for you. It is warm and slow and safe. Let go of the shore. Drift, float, dream. Good night.
Hello, and welcome to the Midnight Scientists. Since you are here, it means you are ready to let the world stop spinning for a while. You are ready to unburden your mind, to set down the heavy things you have carried, and to simply listen. Find a comfortable place. Let your shoulders drop. Unclench your jaw. Let the muscles in your face soften, like wax warming near a gentle flame. Tonight, we are not here to solve problems. We are not here to memorize facts or prepare for tomorrow. We are here only to drift, to take a slow, meandering walk through the hidden architecture of the universe. We are going to tell a story about the stuff the world is made of. The matter that makes up your chair, your blanket, the air in your lungs, and the stars burning in the velvet dark above us. Chapter 1: The Illusion of Stillness. Imagine, if you will, that we are sitting by a global campfire, a small circle of warmth in a vast, cool night. Around us, the world feels solid. The ground beneath you feels firm. The walls of your room seem unmoving. But I'd like you to close your eyes and visualize deeper. Past the paint, past the wood, past the stone. The universe is playing a trick on us, a beautiful, comforting trick. It presents us with solidity, with things that stay put. But in truth, everything, absolutely everything, is vibrating. Let us begin with the idea of the solid. When we are children, we learn that a solid is something that holds its shape. A rock, a diamond, an old oak table. It feels dependable. It is the anchor in a fluid world. But nature is not quite so rigid. Imagine a diamond. In your mind's eye, see its structure. A lattice, a perfect repeating grid of carbon atoms. They are holding hands, locked in a geometry so tight, so perfect, that light itself has to bend through them. This is what we call a crystalline solid. Order, repetition, silence. But not all solids are like this. Some solids are tired. Some solids are confused. They are caught in a moment of hesitation that has lasted for centuries. Drift with me now to an old cathedral. The air is cool and smells of stone and incense. The light is dim, filtering through tall, stained glass windows. You may have heard the whisper, the old legend, that glass flows. People look at the bottom of these ancient panes, thickened and warped by time, and they say, "Look, the glass is a liquid. It is sliding down, slow as centuries." It is a beautiful thought, isn't it? The idea that even glass, hard and brittle to the touch, is secretly a river, moving so slowly that no human life is long enough to see the current. Science tells us this isn't strictly true. The thickness comes from how the glass was made, spun by hand and flattened imperfectly. But the poetry of the idea, that is true. Because glass is an amorphous solid. Visualize the atoms in a crystal again, soldiers in rows. Now, visualize the atoms in glass. They are a crowd, a chaotic, jumbled crowd that was dancing wildly when the music suddenly stopped. They froze. They are stuck where they are, disordered, irregular. They look solid, they feel solid, but deep down, their structure remembers the chaos of the liquid they once were. They are waiting. There is a patience in matter that we humans can barely comprehend. To understand this patience, we must travel. Let your mind float away from the cathedral, across the oceans, to a quiet room in the University of Queensland, Australia. There is a dusty corner there, and in that corner sits a funnel. Inside the funnel is a black, tar-like substance called pitch. Pitch is solid. You can hit it with a hammer and it will shatter like glass. It feels hard as rock. But in 1927, a professor placed a block of this pitch into a funnel and simply waited. He waited. The seasons changed, wars began and ended. Children were born, grew old, and had children of their own. And the pitch waited too, but it did not stay still. Very, very slowly, more slowly than the growth of a mountain, more slowly than the movement of continents, the pitch began to flow. It takes nearly 10 years for a single drop to form. Imagine standing in that room. The silence. The air is still. You are watching a drop of black tar that has been forming since before you were born. It hangs there, heavy with gravity, stretched by time. It is a solid that flows. It is a reminder that the line between stillness and motion is just a matter of patience. If you watched the mountains for 1 billion years, they would ripple like water.
If you watched the stars for 1 trillion years, they would stream like fireflies. Everything flows. Breathe that in. The air you breathe is matter too. Nitrogen, oxygen, argon. But here, in the solid world, we find things that defy our categories. Consider obsidian, volcanic glass. Born from the fiery throat of a volcano, ejected into the freezing air. It cooled too fast. It had no time to organize. It is a moment of violence, frozen into a black, glossy piece. When you touch it, it is smooth. It feels eternal. But it is just another form of arrested chaos. Why does this matter to us as we lie here in the dark? Because it tells us that nothing is truly stuck. We often feel stuck in our lives, stuck in our thoughts, rigid and unmoving. But deep down, even the hardest stone, even the most brittle glass, has a softness to it, a potential to move. Solidity is just a phase. It is a temporary arrangement. Drift deeper now. Imagine you can shrink down, smaller than a grain of sand, smaller than a dust mote, smaller than a wavelength of light. You are standing inside a block of iron. Around you, the atoms are massive, spherical, glowing with a dull, reliable hum. They are locked in place, yes, but they are shivering. Even at room temperature, every atom in the universe is shivering with thermal energy. They vibrate against their neighbors. They jostle. They hum. A solid is not a statue. It is a choir humming a low, steady note that holds the shape of the world together. If you listen closely, in the quiet of your room, you can almost feel it. The hum of existence, the stability of the floor, the walls, the bed. They are holding you up actively. It takes energy to be solid. It takes effort to hold a shape against the chaos of the universe. Appreciate that effort for a moment. The world is holding you. You don't have to hold yourself. You can let go. The ground has you. The bed has you. The atoms are doing the work so you don't have to. Let your weight sink into that support. We have spoken of things that hold their shape, of crystals with their perfect order, and glass with its frozen disorder. We have watched the slow, century-long drip of the pitch. But what happens when the hum gets louder? What happens when the choir begins to sing a faster rhythm? What happens when the vibration becomes too much for the atoms to hold hands? Then the grip loosens, the structure fails, and the solid surrenders. It becomes something else, something softer, something that takes the shape of whatever holds it. We are approaching the edge of the solid world now. We are standing on the banks of the great river of matter. The heat is rising, just a fraction. The bonds are breaking. Can you feel the shift, the loosening? The rigid world is melting away. The hard lines are softening into curves. We are about to enter the flow. Chapter 2. The Dance of the Fluids. There is a moment, a precise, delicate moment, when a solid gives up its fight. Imagine an ice cube resting on a warm saucer. For a long time, it holds its edges. It keeps its corners sharp, defined, separate from the world. But then, the warmth creeps in.
The vibrating atoms we spoke of, they begin to move too fast to hold hands. The grip slips. The corners soften. The rigid crystal lattice unbuckles. And then, release. The structure collapses, not with a crash, but with a sigh. The ice becomes water. It surrenders its shape to gravity. It spreads out, exploring the surface it rests on, seeking the lowest point, finding a new kind of freedom. This is the liquid state. In the world of sleep and dreams, the liquid is our guide. It is the state of matter that refuses to be pinned down. It has volume, yes, it takes up space, but it has no fixed shape. It is the ultimate shapeshifter. Pour water into a cup, it becomes the cup. Pour it into a bottle, it becomes the bottle. Pour it into the hollow of your hand, and it becomes a small, shimmering pool, reflecting the stars above. Drift with me now to the edge of a slow-moving river. The water is clear and cool. Watch how it moves around the rocks. It does not argue. It does not fight the obstacle. It simply flows around it, wrapping the stone in a cold embrace before moving on. There is a lesson here. Solids break when they are stressed, but liquids adapt. They flow. They find a way. But not all liquids flow the same way. The universe has given them different personalities, different memories how to move. Imagine a jar of golden honey. Tip the jar. Watch the honey spill. It does not rush like water. It folds over itself. It stretches into a long amber thread, thick and luxurious. It moves with a heavy, deliberate grace. Scientists call this viscosity. It is a measure of internal friction. It is a measure of how much the molecules want to stick together. In water, the molecules slide past each other easily, like strangers in a hurry. But in honey, the molecules are tangled. They are holding on to one another, reluctant to let go, dragging each other along. High viscosity is the physics of slowness. It is matter moving in slow motion without the need for a camera trick. Imagine diving into a pool of honey. You would not splash. You would sink, slowly, held by the golden weight of it. The noise of the world would be muffled instantly. You would be suspended in a warm, thick amber silence. Movements in high viscosity must be slow. If you thrash, you get nowhere. If you move gently, the fluid parts for you. It teaches us that sometimes the only way to move forward is to slow down. But nature, in her infinite playfulness, created liquids that break the rules. These are the non-Newtonian fluids, the rebels of the material world. Sir Isaac Newton, the father of classical physics, liked things to be predictable. He believed that a fluid's thickness, its viscosity, should stay the same no matter what you do to it. Water is water, whether you stir it gently or slap it with a paddle. But some fluids change their minds. Imagine a bowl filled with a simple mixture, cornstarch and water. It looks like milk. It looks innocent. If you dip your finger into it slowly, it feels like cream. Your finger sinks in without resistance. It is soft, welcoming. It behaves like a liquid. But now, imagine you try to strike it. Imagine you try to punch the surface. Instantly, it hardens. It becomes solid. It pushes back. This is a sheer thickening fluid. When you apply stress, when you rush, when you push, when you force it, the particles jam together. They lock up. They refuse to flow. They become a temporary wall of stone. But the moment you relax, the moment you stop fighting, the structure dissolves, the stone becomes liquid again, and you sink in. Is there a better metaphor for the mind at night? When we try to force sleep, when we stress about being awake, our minds become hard. They resist. The thoughts jam together like the cornstarch particles, creating a solid wall of anxiety. We bounce off the surface of sleep, unable to enter. But when we stop pushing, when we lie still, when we breathe and accept the moment, the resistance fades, the mind softens, and we sink, gently, deeply, into the liquid dark. Softness allows entry, surrender allows flow. There are other liquids that do the opposite. They are sheer thinning. Think of ketchup in a glass bottle. It sits there, stubborn, refusing to pour. It acts like a solid stuck in the neck of the bottle. But give it a shake, add energy, disturb it. Suddenly, it thins. It flows freely. The stress makes it more fluid. Paint is the same. It stays thick on the brush so it doesn't drip, but becomes thin and smooth when you roll it on the wall. These materials are responsive. They are listening to the forces around them. They are not passive. They are reacting to the touch of the world. Toothpaste, gels, quicksand, blood flowing through your veins. They are all dancing this complex dance of viscosity, thickening, thinning, flowing, stopping. It is a world of squish and ooze, a world where definitions are slippery. And then there are the materials that exist in the twilight, the amorphous materials we touched on before, the gels, the slimes, the polymers, long chains of molecules tangled like spaghetti. They are elastic. They remember their shape. If you stretch slime slowly, it flows like a liquid. If you pull it fast, it snaps like a solid rubber band. It creates a bridge between the two worlds. As you lie there now, imagine your body becoming heavy, like a fluid with high viscosity. Feel your muscles lengthening, relaxing, spreading out against the mattress. You are losing your rigidity. You are no longer a solid object holding tension. You are melting, just a little. Drift with me downstream. The river is widening now. The current is slowing. The water is deep, dark, and still. We are moving away from the simple, chaotic flow of water. We are moving toward a place where the liquid begins to remember the solid, a place where the flow finds a hidden order. Most people think order and flow are opposites, that you must choose, be a crystal or be a river, be still or be moving. But the universe loves a paradox. It loves the middle ground. Ahead of us, the water seems to shimmer with a strange, iridescent light. The molecules are lining up. They are preparing for a performance. We are entering the realm of the liquid crystal, the ghost in the machine, the state of matter that powers the very screen you might be watching, the state of matter that allows us to see the invisible. Are you ready to see how a liquid can learn to march in step?
Chapter 3. The Order in the Flow.
We tend to think of the universe as a place of choices, black or white, day or night, solid or liquid. A solid is rigid, its atoms or soldiers standing at attention in a perfect grid. A liquid is chaotic. Its atoms are a crowd dispersing after a show, wandering in every direction. But what if you didn't have to choose? What if you could keep the freedom of the crowd, but maintain the discipline of the soldier? Welcome to the world of liquid crystals. It sounds like a contradiction, doesn't it? A liquid crystal. It sounds like dry water or cold fire. But this state of matter is the master of compromise. It is the diplomat of the material world. Imagine a vast ocean filled with tiny rod-shaped rafts. In a normal liquid, these rafts would be spinning and drifting randomly, pointing north, south, east, and west without a care. But in a liquid crystal, something invisible guides them. They still drift, they still flow, but they all agree to point in the same direction. They are like a school of fish turning in unison. Individually, they are free to swim. Collectively, they are a single shimmering wave of intent. This is the nematic phase. The word comes from the Greek for thread, because under a microscope, these materials look like tangled silk. They possess the ability to flow like water, yet they interact with light as if they were a solid crystal. This delicate balance is what makes the screen you might be looking at right now possible. Pause for a moment. Look at the glow of your screen, or imagine it if your eyes are closed. That light is not magic. It is a choreography. Behind the glass, there are millions of tiny liquid crystal cells. They are waiting for a signal. When a tiny electric current touches them, they untwist. They change their alignment just enough to block light or let it pass through. Every image you see, a photograph of a loved one, a video of a sunset, the words of this story, is created by billions of molecules performing a synchronized dance. They are opening and closing the blinds on the windows of light millions of times a second without making a sound. They are obedient. They are precise, but they are fluid. If they were solid crystals, they would be too rigid to switch. If they were normal liquids, they would be too chaotic to control. They exist in the perfect middle ground, soft enough to move, ordered enough to listen. There is a lesson in this for us, too. We often feel we need to be rigid to be strong. We think we must have a spine of steel, unbending and hard. But liquid crystals teach us that true strength and true utility comes from flexibility. It comes from alignment. You can flow through your life, moving around obstacles while still keeping your internal compass pointed true north. You can be soft and structured at the same time. Nature discovered this trick long before we invented screens. Look at a soap bubble drifting in the air, swirling with rainbows of magenta, cyan, and gold. Look at the shiny metallic wing of a beetle. That iridescence, that shifting color that changes when you tilt your head, that is the liquid crystal phase at work. In these forms, the molecules stack in layers that twist slightly, like a spiral staircase. This twist catches the light and breaks it apart, reflecting only certain colors back to your eye. It is structure creating beauty out of nothing but geometry and light. And it is closer to you than you think. Drift deeper now. Past the screen, past the beetle wing. Drift into your own body. Your cells, the billions of tiny building blocks that make you, are wrapped in membranes. These membranes are not hard shells like eggshells. They are liquid fluid bilayers. They are liquid crystals. They allow nutrients to flow in. They allow waste to flow out. They ripple and bend when you move, but they hold their integrity. They protect the delicate machinery inside. You are, in a very real sense, made of liquid crystals. Your very biology relies on this state of matter that refuses to sit still, yet refuses to fall apart. As you lie here, feel the softness of your skin. Feel the pulse in your wrist. You are a masterpiece of soft matter physics. You are not a statue. You are a flowing, living, aligned river of atoms. There is a peace in this middle ground. The solid world is too hard, it breaks under pressure. The liquid world is too chaotic, it has no form. But here, in the liquid crystal, we find balance. We find a state of matter that is responsive. It reacts to energy. It reacts to temperature. It reacts to life. It is a state of waiting, of readiness. But the universe does not always stay in this gentle middle ground. Sometimes the energy continues to rise. The gentle vibration of the solid became the flowing slide of the liquid. The flowing slide became the frantic bouncing of the gas. But what happens if we keep adding heat? What happens if we push the atoms so hard, shake them so violently that they can no longer hold themselves together? What happens when we tear the electrons away from the heart of the atom? We are leaving the comfort of the earth now. We are leaving the cool rivers and the shimmering screens. The air is getting thinner. The sky is getting darker. But ahead of us, a new light is beginning to glow. A violet electric hum that crackles with the power of the stars. We are about to enter the fire. We are about to meet the most common and most forgotten state of matter in the universe.
Chapter 4. The Fourth State. We have walked through the quiet lands of the solid, swam through the adaptive rivers of the liquid, and drifted through the invisible clouds of gas. In these three familiar worlds, the atoms are intact. They are whole. They keep their electrons close, like secrets they are afraid to share. But the universe is not always so possessive. If you take a gas, say the air in a lightning storm or the hydrogen in a star, and you feed it energy, if you heat it, crush it, or blast it with voltage, a transformation occurs that changes the very nature of matter. The atoms can no longer hold on. The energy is too great. The electrons, those tiny buzzing sparks that orbit the nucleus, break free. The leash snaps. The atom is no longer a neutral, lonely thing. It becomes an ion, and the gas becomes a sea of charged particles swimming in a soup of free electrons. This is plasma. You may have heard it called the fourth state of matter. It sounds exotic, like something you'd only find in a science fiction novel. But look up. The sun is plasma. The stars are plasma. The glowing nebulas that birthed those stars are plasma. If you were to count every visible ounce of matter in the universe, 99.9% of it is plasma. We, living on this cool, solid rock, are the exception. The universe is not made of rock and water. It is made of fire and light. But plasma is not just fire. Fire is a chemical reaction, a burning of fuel. Plasma is something deeper. It is matter that has become electricity. Because the particles are charged, they are no longer indifferent to each other. In a gas, atoms bounce off one another like billiard balls. They don't care who they hit. But in a plasma, every particle feels every other particle. They are connected by invisible webs of electric and magnetic fields. If you wiggle a plasma here, it ripples over there. It moves like a living thing. It twists, it spirals. It organizes itself into filaments and sheets that stretch for light years. It is the state of matter that glows with its own internal life. You have seen this glow. Think of a rainy night in the city. The streets are slick and black. Above a quiet diner, a neon sign buzzes.
That red-orange glow, that is plasma. Inside the glass tube, a gas called neon is being tickled by electricity. The electrons are jumping up and down, dancing with the voltage, and as they dance, they release photons. They release light. It is a captured star in a glass tube, a tame little piece of the cosmos lighting the way for a late-night wanderer. There is a comfort in that hum, isn't there? The sound of a street lamp warming up, the sound of energy moving through the dark. It is the sound of the universe keeping the lights on. Now, let us leave the city. Let us drift upward, past the clouds, past the atmosphere, into the silence of space. We are floating toward the sun. Don't be afraid. In our story, the heat cannot touch you. You are safe. You are just a consciousness observing the grandeur. See the surface of the sun. It is not a solid ground. It is a roaring, shifting ocean of golden plasma. It boils and churns, rising and falling in cells the size of Texas. But look closer. Look at the edges. Do you see the loops? Great, towering arches of fire rising from the surface, twisting into the black sky and then diving back down. These are solar prominences. They are guided by magnetic fields. The plasma is flowing along invisible magnetic tracks like cars on a roller coaster. It is a display of unimaginable power, yet it has a grace to it, a structured magnetic elegance. The sun is not just burning, it is breathing. It is exhaling streams of charged particles, the solar wind that rush out into the solar system, washing over the planets, washing over us. And when that wind reaches Earth, it gives us one of the most beautiful sights the human eye can behold. Drift with me now to the far north. The air is biting cold, the ground is covered in snow, the sky is ink black and filled with stars. Wait. Watch the horizon. A pale green light begins to shiver. Then it grows. It rises up like a curtain being lifted by an invisible hand. The aurora borealis, the northern lights. This is plasma painting the sky. The solar wind is crashing into Earth's magnetic field, funneling down toward the poles and exciting the oxygen and nitrogen in our atmosphere. The green you see, that is oxygen, singing its song of green light. The red is nitrogen, humming a lower note. These curtains of light fold and ripple, dancing in silence. They are the visible footprint of the invisible connection between the sun and the earth, a kiss of plasma across 93 million miles of void. It reminds us that our planet is not isolated. We are wrapped in a magnetic cocoon, protected, yet intimately connected to the star that gives us life. Plasma is the state of matter that bridges the gap. It connects the atom to the star. It connects the lightning bolt to the thunder. It connects the vacuum of space to the atmosphere of home. As you lie in the dark, visualize that soft, protective glow. You are made of atoms that were once forged in plasma. The iron in your blood, the calcium in your bones, they were cooked in the hearts of ancient stars, in the crushing, hot pressure of a plasma core. You are cooled down stardust. You are plasma that has learned to sit still. But deep down, the energy is still there. The potential for light is still there. We have seen the heat of the universe. We have seen the electric dance of the ordinary stars. But the story of matter goes back further than the stars. To understand where we truly came from, we have to rewind the clock. We have to go back to a time before stars, before atoms, before protons and neutrons. We have to go back to the very first heartbeat of the universe. to a time when everything was squeezed into a space smaller than a single atom, and the heat was so intense that even physics itself was holding its breath. We are going to visit the primordial soup. The heat is rising, the structure is melting, the timeline is unraveling. We have traveled far. We have seen the solid earth, the flowing water, and the burning stars. But to see the true beginning of matter, we must close our eyes and let the timeline of the universe unwind. Imagine rewinding the clock. Watch the stars unburn and dissolve into gas. Watch the galaxies unwind their spirals and drift back together. Watch the vast darkness of space shrink, pulling everything closer, tighter, hotter. We are going back 13.8 billion years, back to the first few microseconds after the Big Bang. There are no planets here, no suns, no atoms. Even the protons and neutrons, the sturdy bricks that build the nucleus of every atom in your body, cannot exist here. It is too hot. It is too dense. In this moment, the universe is not a place of things. It is a soup. This is the quark-gluon plasma. It is a name that sounds technical, jagged, but the reality is soft, dense, and unimaginably bright. In the world we know today, quarks are shy. They are the tiny particles that make up protons and neutrons, but they are never found alone. They are always bound together by gluons, the glue particles of the strong nuclear force. They are locked in tight eternal embraces, 3 by 3. But in the infant universe, the temperature is trillions of degrees. The heat is so intense that the glue melts. The embrace is broken. For the first and only time in history, the quarks roam free. Imagine a sea of golden light, thicker than water, hotter than a billion suns. In this sea, there is no empty space. Everything is touching everything else. The universe is a single, continuous, glowing droplet. It is a state of perfect unity. Scientists have recreated this state, briefly, in the great particle colliders of the world. By smashing heavy ions together at near light speed, they summon a tiny, fleeting drop of this primordial soup. And what they found surprised them. They expected this super-hot, chaotic explosion to behave like a gas, wild and messy. But the quark-gluon plasma flowed. It flowed smoothly. It flowed elegantly. It behaved like a perfect liquid. It had almost zero friction. Despite the unimaginable violence of its energy, it moved with a grace that puts water to shame. Think about that. The most chaotic moment in the history of existence was also smooth. It suggests that at the very beginning, the universe was not a mess of separated, jagged pieces. It was a whole, a single, flowing, interconnected river of energy. We are all born from this soup. Every proton in your body, every neutron in the center of every atom of your fingertips crystallized out of this cooling plasma as the universe expanded. You are in a very real sense a cooled down droplet of the Big Bang. You carry the memory of that unity, the memory of a time when there was no here or there, no you or me, just us, just the flow. But the fire could not last. The universe, in its eagerness, began to stretch. It expanded outward, rushing into the void. And as it stretched, it cooled. The trillions of degrees dropped to billions, then millions. The quark-gluon plasma slowed down. The quarks, sensing the chill, reached out to one another. They found partners. They huddled together in threes, binding tight against the cold, forming the first protons and neutrons. The perfect liquid froze into the building blocks of matter. The golden fog cleared, and for the first time, there was darkness. But in that darkness, a new story was beginning. A story not of heat, but of cold. A story of what happens when the universe slows down so much that it almost stops. We are leaving the fire behind. We are drifting away from the heat of creation, floating forward in time into the deep, quiet chill of the void. Wrap your blanket tighter around you. The temperature is dropping. The noise is fading. We are going to a place where the atoms stop dancing and start to dream. A place of silence so profound it has its own geometry. Welcome to the cold. Chapter 6. The Great Slowing. Heat is a mask. It is a chaotic noise that covers up the true nature of things. When atoms are hot, they are too busy, too energetic, too distracted to show us who they really are. But when the heat fades, the noise stops, and the architecture reveals itself. Welcome to the Great Slowing. We are drifting away from the fires of the Big Bang, away from the roaring stars, and into the quiet, cool corners of reality. Here, the atoms slow down. They stop their frantic bouncing. They begin to listen to the subtle forces of attraction that they ignored when they were rushing around. They begin to build. Think of water. It is the most familiar substance in our lives, yet it is arguably the strangest. When water cools, it does something that almost no other substance does. Most things, when they freeze, pack tight. They huddle together to save space, becoming dense and heavy. But water? Water breathes. As it approaches freezing, the water molecules arrange themselves into a hexagon, a six-sided ring. They reach out to hold one another at a very specific distance, leaving open, airy spaces in between. This is why ice floats. It is lighter than the water it came from. It is a solid built on the principle of openness. Imagine a snowflake falling through the gray sky. Each arm, each delicate branch is a map of the water molecules locking into that hexagonal breath. No two are alike, not because of magic, but because the journey of falling, the changing humidity, the temperature shifts, sculpts the crystal in real time. It is a record of its own history frozen in geometry. But this familiar ice, the ice in your freezer, the ice on a winter pond, is just the beginning. It is known to scientists as Ice 1. Nature, however, has a hidden library of ices. Drift with me now, deeper. We are leaving the surface. We are sinking into the crushing depths of a superocean, or perhaps burying ourselves beneath the crust of a distant frozen moon like Europa. Here, the pressure begins to build. Pressure does strange things to matter. It forces intimacy. It leaves no room for the open, airy breath of the snowflake. If you squeeze ice hard enough, the molecules cannot maintain their hexagonal ring. The structure collapses, but it does not break into chaos. It rearranges. It snaps into new, denser shapes. Meet Ice 2, Ice 3, Ice 5. In these phases, the water molecules are forced into rhomboids, tetragonal columns, and cubic cages.
They are twisted and packed, shoulder to shoulder. And then there is ice 7. This is a ghost ice. It exists under such intense pressure, tens of thousands of times the pressure of Earth's atmosphere, that it can remain solid even when it is hot. Imagine a block of ice that burns your hand not with cold but with heat, yet refuses to melt because the pressure holds it in an iron grip. It forms deep inside planets made of water, locking away oceans in a hot, solid tomb. Why does this matter to us, resting here in the soft dark? Because it reminds us that we too have different phases. We have our open, airy days, our snowflake days, when we feel light and expansive. But we also have our high-pressure days, days when the weight of the world squeezes us. We often fear that pressure will break us. But look at the water. It does not break. It transforms. It finds a new structure. It finds a way to be solid, even in the crush. Under pressure, you do not cease to be yourself. You just find a denser, stronger version of your own geometry. But we are not done cooling down yet. Ice is cold, yes, but the atoms inside it are still shivering. They are still vibrating in their cages, humming with a little bit of leftover warmth. We want to go colder, much colder. We want to go to a place where the shivering stops, a place where the individual identity of the atom begins to blur. We are descending toward the theoretical limit of the universe, absolute zero. Minus 273.15 degrees Celsius, 0 Kelvin. It is a place where nature stops whispering and begins to sing a single unified note. Pull your thoughts inward. Quiet the noise. We are about to witness the moment where matter loses its ego.
Chapter 7. The Unbroken Wave. We are now approaching the coldest place in the universe. It is not on the dark side of the moon. It is not in the empty space between galaxies. It is here, on Earth, inside a small vacuum chamber surrounded by lasers and magnets. Scientists have built a refrigerator for atoms. They use beams of light not to heat things up, but to slow them down. They push against the atoms, gentle nudge by gentle nudge, stealing their energy, calming their shivering, until the temperature drops to a billionth of a degree above absolute zero. At this temperature, the rules of reality change. Imagine a ballroom filled with dancers. In a gas, the dancers are running wild, bumping into each other. In a liquid, they are swaying and sliding past one another. In a solid, they are standing still, but tapping their feet. But here, near absolute zero, the dancers stop moving entirely. They stop being individuals. In the strange mathematics of quantum mechanics, every particle is also a wave. When an atom has a lot of energy, its wave is short and tight, a tiny localized packet of existence. I am here, it says. I am me. But as the atom cools, its wave relaxes, it spreads out. It gets longer and softer. The edges of the atom begin to blur. And if you pack enough of these cold, blurry atoms together, something magical happens. Their waves touch, then they overlap, and finally, they merge. The I disappears. The me vanishes. There is only us. This is the Bose-Einstein condensate, the fifth state of matter. It is a cloud of thousands of atoms that have collapsed into a single quantum state. They act as one giant superatom. If you poke one part of the cloud, the whole cloud feels it instantly. They move in perfect unison. They sing the exact same note. It is the ultimate form of empathy. There is no separation anymore. The boundaries between self and other have dissolved completely into a single, unbroken wave of being. Close your eyes and try to imagine that feeling. Imagine letting go of your own edges. Imagine the boundary of your skin softening. Imagine that you are not a separate thing fighting to hold your place in the world, but part of a larger, slower, deeper wave. You are merging with the bed beneath you, merging with the air in the room, merging with the quiet of the night. You are a Bose-Einstein condensate of consciousness, still, unified, whole. This state of matter was predicted by Albert Einstein and Satyendra Nath Bose in the 1920s just by playing with numbers on a page. They saw the math and realized, if it gets cold enough, identity dissolves. It took 70 years for technology to catch up to their imagination, but when we finally made it in 1995, peering into that vacuum chamber, we saw exactly what they promised. A ghostly peak of matter standing still in the center of the trap, a monument to unity. In this state, matter can do things that seem impossible. It can interfere with itself like light. It can slow down light itself. It behaves like a memory of the universe before it broke into pieces. There is a profound peace in the condensate. It is the peace of belonging. It is the peace of knowing that deep down, separation is just an illusion caused by too much energy, too much noise. Cool down the noise, and we are all one. But now that we are one, now that the atoms have locked arms and become a single wave, how does this new ghost matter move? Does it trudge? Does it slide? No. It flows, but not like water. Water has friction. Water rubs against the riverbank. Water gets tired. This matter does not get tired. It has forgotten how to stop. Chapter 8. The Frictionless Path. We spend our lives fighting friction. Think of walking through deep snow. Think of swimming against a current. Even sitting still, there is the friction of the air. The friction of gravity pulling at your muscles, the friction of thoughts grinding against one another in your mind. In the ordinary world, everything resists. To move requires effort. To keep moving requires energy. If you stop paddling, the boat stops. If you stop pushing, the swing slows down. The universe is constantly trying to bring us to a halt. But in the deep cold, in the strange quantum basement of reality, there is a rebellion against this rule. Meet helium. We know helium as the gas that fills party balloons, the element of celebration and lightness. But when you cool helium down to just 2.17 degrees above absolute zero, a temperature colder than outer space, it undergoes a transformation that feels like magic. It becomes a superfluid. Imagine a cup of tea. If you stir it, the liquid swirls for a moment, then friction slows it down and it settles. Now imagine a cup of superfluid helium. If you stir it, it will spin, and it will spin, and it will spin. It will not stop in an hour. It will not stop in a year. If you could keep it cold enough, it would spin forever. Why? Because the atoms have entered that state of perfect unity we spoke of. They are a Bose-Einstein condensate. They are all marching in lockstep. Because they move as one, they cannot bump into each other. They cannot create the chaotic tumbling that causes friction. They have achieved zero viscosity. It is the physics of effortlessness. Drift with this idea. Imagine a movement that costs you nothing. Imagine a thought that flows through your mind without snagging on worry or doubt. Just pure, clean motion. But superfluid helium does not just spin, it escapes. If you pour this strange, ghostly liquid into a cup, it will not stay there. It will seemingly defy gravity. It will form a layer just one atom thick, the Rollin film, and it will climb up the inside of the cup, slide down the outside, and drip off the bottom to form a puddle below. It is a liquid that refuses to be contained. It flows through cracks so small that air cannot pass through them. It flows through the microscopic pores of solid glass. It is looking for stillness. It is looking for the lowest point, and no wall can stop it. And then there is the fountain effect. If you gently warm a tube of superfluid helium, it doesn't just expand. It rushes toward the heat with such enthusiasm, such speed, that it shoots upward in a continuous, frictionless jet, a fountain that rises without a pump, powered only by the desire of the atoms to find a new balance. It creates a spray of liquid light, silent and eternal. There is a profound lesson in the superfluid. It teaches us that resistance is not inevitable. The struggle we feel, the drag of the day, the heaviness of the body, is a product of heat. It is a product of chaos. When we cool down, when we align ourselves, the friction disappears. As you lie here, imagine your body becoming a superfluid. The tension in your shoulders, it flows away without resistance. The tightness in your jaw, it creeps away, escaping over the edges of your consciousness. Your breath flows in and out, a frictionless loop, requiring no effort, no will. It just happens. You are entering a state of zero resistance. You do not need to try to sleep. Trying creates friction. Trying is a solid-state behavior. Be the superfluid. Let gravity take you. Let the flow carry you over the rim of wakefulness, down into the soft, silent puddle of dreams. We have seen the matter that stops. We have seen the matter that flows forever. But nature is not done with her riddles. What if I told you there is a state of matter that is both rigid like a crystal, yet flows like a river? A ghost that can walk through walls, but still has a shape. We are about to enter the land of the impossible. We are about to meet the supersolid. In the waking world, we're taught to respect boundaries. A door is either open or shut. A light is on or off. You are either here or you are there. And in the world of matter, the greatest boundary of all has always been the line between the solid and the liquid. We understand solids. They are the statues. They hold their ground. Their atoms are locked in a rigid grid, loyal to their neighbors. We understand liquids. They are the rivers. They wander. Their atoms flow past one another, free and unattached. But the quantum world does not respect our boundaries. It looks at our rules and gently, quietly, breaks them. Welcome to the supersolid. It is a name that sounds like a superhero or perhaps a contradiction. How can something be super solid? Does it mean it is harder than diamond, more rigid than stone? No. It means something far stranger. It means it is a solid that flows. Imagine a block of ice sitting on a table. It looks perfectly still. It holds its shape. If you touch it, it feels hard. But if you could zoom in, if you could see the atoms with quantum eyes, you would see a ghost story. The atoms are arranged in a crystal lattice, yes, they have assigned seats, but they are not sitting in them. In a supersolid, the atoms are delocalized. They are in a state of deep quantum uncertainty. An atom is not just in this spot or that spot. It is, in a sense, hovering in all the spots at once. It is as if the dancers in our ballroom have formed a perfect square formation, but at the same time, they are gliding seamlessly through the formation, passing through one another like smoke. The structure remains. The flow continues. It is a statue that breathes. It is a stone that circulates. For decades, this was just a dream on a physicist's blackboard. It seemed too impossible to be real. But in the 21st century, using exotic atoms like dysprosium and erbium, scientists finally coaxed matter into this twilight state. They trapped a cloud of atoms and cooled them until they formed a droplet. The droplet grew little spikes, a crystal structure. It had shape. It had orientation. But inside, the matter was flowing without friction, swirling around the lattice like a superfluid. It is the ultimate paradox, stability and freedom existing in the same space at the same time. Think of what this means for the concept of stillness. We often try to force ourselves to be still to fall asleep. We try to freeze our bodies, freeze our thoughts. We think that if we move, we have failed. But the supersolid teaches us a softer way. You can be still on the outside while flowing on the inside. Your body can be heavy, sinking into the mattress, holding its shape like the crystal. But your breath, your blood, your dreams, they can flow like the superfluid. You do not have to choose. You can be the river and the riverbank. Hold that image in your mind, a structure made of flow, a stability made of movement. It is a confusing thought for the logical brain, and that's good. Confusing the logic is how we open the door to sleep. Let the how dissolve. Just stay with the is. The supersolid exists. The impossible lattice is real. And if matter can be two opposites at once, then surely you can be both awake and asleep, drifting in that delicious space between the two. But the quantum world is not done with us. We have messed with space. We have blurred the lines of where atoms are. Now we must mess with something even more fundamental. We are going to touch time itself. Imagine a clock that has no battery, a clock that ticks forever, not because it is powered, but because ticking is simply what it is. We are about to meet the time crystal.
Chapter 10. The Pulse of Eternity. Time is a river. We are used to thinking of it as something that flows in one direction, carrying us along with it. We measure it with clocks. Tick, tock, tick, tock. But ordinary clocks need energy. A pendulum needs a push. A battery needs a charge. A heart needs food. In the classical world, if you stop feeding a system energy, it eventually stops moving. It settles down. It finds its ground state, its place of rest, and it becomes silent. A crystal on a shelf does not change. It sits there, frozen in space, forever the same. But what if a crystal didn't just repeat itself in space? What if it repeated itself in time? Welcome to the time crystal.
It is a discovery so strange that when it was first proposed by Nobel laureate Frank Wilczek in 2012, many physicists said it was impossible. It sounded too much like a perpetual motion machine, a violation of the laws of thermodynamics. But the quantum world is a place where impossible is just a challenge. Imagine a line of atoms. In a normal material, if you leave them alone in their coldest, lowest energy state, they sit still. But in a time crystal, even at their absolute lowest energy, when they have nothing left to give, no heat to burn, no battery to drain, they pulse, they flip, up, down, up, down. They are ticking, not because they are being pushed, but because ticking is their natural state of rest. It is a heartbeat that costs nothing, a rhythm that is woven into the very fabric of their existence. Think of a gelatinous jellyfish drifting in the deep ocean. It pulses, open, shut, open, shut. Now imagine that jellyfish doesn't need to eat, it doesn't need to breathe. It simply pulses because that is what its atoms do. It will pulse until the end of the universe without losing a single ounce of energy. That is a time crystal. Scientists have created these in the lab using quantum processors and chains of ions. They hit them with a laser, a rhythmic nudge. But the time crystal doesn't just copy the laser's rhythm. It creates its own. It locks into a stable, repeating cycle that resists melting, resists chaos, resists stopping. It breaks the symmetry of time itself. Why is this comforting? Because it tells us that rhythm is fundamental. We often worry that if we stop striving, if we stop pushing, we will cease to be. We worry that without effort, we are nothing. But the time crystal tells us that existence has a pulse of its own. Your heart beats without your permission. Your breath cycles without your command. Your cells divide. Your neurons fire. Your dreams loop. There is a rhythm inside you that does not require your effort. It is the deep, ancient quantum metronome of life. You can stop driving the machine now. You can take your hands off the wheel. The engine will keep running. The pulse will keep beating. Let yourself sink with that eternal rhythm. Tick, tock, in, out, drift, deeper. The time crystal ticks in the silence of the void, a lighthouse blinking in the dark, signaling that even in the deepest rest, life continues. But we must move on. We have explored the strange loops of time. Now we must explore the strange shapes of space. We are entering the protected lands, the lands of topology.
Chapter 11. The Shape of Space. We live in a world of shapes. A box has sharp corners. A ball is round. A table is flat. We think of these things as distinct, separate things. If you crush a box, it is broken. If you shatter a plate, it is gone. But there is a branch of mathematics and a strange new family of materials that sees the world differently. It doesn't care about sharp corners or smooth curves. It cares about connections. It cares about holes. This is topology. To a topologist, a coffee mug and a donut are the exact same thing. Imagine holding a coffee mug made of soft, pliable clay. In your mind, slowly reshape it. You can shrink the cup part down. You can thicken the handle. You can stretch the clay, bend it, smooth it. As long as you don't tear it, and as long as you don't punch a new hole in it,
you can morph that mug smoothly into the shape of a donut. The single hole, the handle, becomes the whole of the donut. To nature, in these specific phases of matter, the shape doesn't matter. The topology matters. This realization has unlocked a hidden door in physics. It led to the discovery of topological insulators. These are materials that are baffling, brilliant contradictions. Imagine a block of material. Inside, in its deep interior, it is an insulator. It refuses to carry electricity. It is quiet, still, and resistant, like wood or rubber. But on its surface, on the very skin of the material, it is a perfect conductor. Electricity flows along the edges not just easily, but perfectly. It flows in a protected state. In a normal wire, electrons bump into impurities. They scatter, they get lost, they create heat. That is resistance. But in a topological insulator, the electrons on the edge are locked into a specific quantum path. They cannot scatter, they cannot turn back. They simply flow around obstacles like water flowing around a stone in a stream, rejoining the path instantly. They are protected by the geometry of the universe itself. There is something profoundly reassuring about this. It tells us that deep down, there are properties that cannot be broken. You can bend the material, you can stretch it, you can dirty it with impurities, you can heat it up. But the flow remains. The topology protects it. Think of your own life. You are stretched. You are bent by stress. You are pulled in different directions by responsibilities and worries. You feel like your shape is constantly being distorted. But topological physics whispers a secret. The shape doesn't matter. Your core topology, your essential self, remains unchanged. You have a protected state. Imagine that you have an inner calm that is topologically protected. No matter how much the outside world deforms, no matter how much noise or stress wraps around you, that inner path remains open. It cannot be broken. It cannot be scattered. Visualize that flow now, a stream of light running along the edges of your consciousness. It is safe. It is continuous. We have explored the solids that flow, the liquids that lock, the crystals that tick, and the shapes that protect. We have looked deep into the microscopic heart of matter. But now, the room is getting too small. The laboratory is feeling cramped. To find the final secrets of matter, we must leave the earth entirely. We must go to where matter is scarce, lonely, and beautiful. We are going to the empty spaces. We are going to the void between the stars. The air is gone. The sound is gone. There is only dust and silence and the deep, deep dark. Chapter 12. The Void Between. We have spent our time examining the busy, crowded world of atoms here on Earth. We have looked at crystals packed tight, liquids jostling for space, and plasmas roaring with heat. But to see the true face of matter, we must go where there is almost nothing to see. We must leave the planet. Drift up, away from the blue atmosphere, past the moon, past the orbits of the... Chapter 12. The Void Between. We have spent our time examining the busy, crowded world of atoms here on Earth. We have looked at crystals packed tight, liquids jostling for space, and plasmas roaring with heat. But to see the true face of matter, we must go where there is almost nothing to see. We must leave the planet. Drift up, away from the blue atmosphere, past the moon, past the orbits of the planets, Leave the sun behind until it is just one bright star among millions. We are entering the interstellar medium. When we look up at the night sky, we see the stars. We see the points of light. We think of space as a vacuum, an empty black canvas where the stars hang. But space is not empty. It is breathing. The space between the stars is filled with a ghost ocean. It is a thin, tenuous mist of gas and dust that stretches for thousands of light years. Here, matter is lonely. On Earth, in a single cubic centimeter of air, the size of a sugar cube, there are quintillions of atoms bumping into each other billions of times a second. It is a crowded, noisy party. But out here, in that same sugar cube of space, you might find only one atom, just one, floating alone. It might travel for years before it meets another. It drifts in the silence, bathed in the faint, ancient light of distant galaxies. This is matter at its most solitary. And yet, this lonely matter is the most important stuff in the cosmos. It is the reservoir. It is the clay from which new worlds are sculpted. Floating among these lonely atoms is cosmic dust. It is not like the dust under your bed. This is stardust. Tiny grains of carbon, silicon, and iron, microscopic diamonds and flecks of graphite. They are the soot left behind by dying stars that exploded long ago. They are cold, unimaginably cold. In the shadows of space, the temperature drops to just a few degrees above absolute zero. The dust grains are covered in frost, layers of frozen water, frozen methane, frozen ammonia. These are the molecular clouds. Look at them. Vast, dark silhouettes against the starry background. They look like holes in the sky, patches of ink spilled on the canvas. But they are not holes. They are nurseries. Inside these dark clouds, the dust is gathering. It is safe here. It is shielded from the harsh radiation of the stars. In the cold and the dark, the atoms can finally slow down enough to touch. Gravity, the patient sculptor, begins to work. It gently pulls the dust together. Drift closer, closer, closer. Over millions of years, the cloud gets denser. It gets heavier. The lonely atoms find partners. They begin to spin. And eventually, deep in that cold heart, a spark ignites. A new star opens its eyes. But that is a violent future. For now, in our story, we are staying with the quiet. Imagine yourself floating in one of these dark clouds. It is silent. It is still. You are wrapped in a blanket of cosmic frost. There is no urgency here. The clock of the universe ticks so slowly that a human lifetime passes in the blink of an eye. There is peace in this emptiness. We often fear being alone. We fear the silence. But the interstellar medium teaches us that emptiness is not nothing. It is potential. It is the space where the next star is waiting to be born. You can let your mind become like that space. Vast, open, quiet, ready to receive, but content to just be. But as we drift through the dark, we realize something unsettled. We can see the stars, we can see the gas, we can see the dust. But when we do the math, when we weigh the galaxies, the numbers don't add up. There is something else out here, something we cannot see, something we cannot touch, something that doesn't shine, doesn't reflect, and doesn't interact with light at all. It is passing right through you right now. We are about to enter the shadow world. We are about to meet the ghosts of the cosmos. Chapter 13. The Dark and the Strange. We stand now at the edge of knowledge. We have walked through the world of light. We have touched the ice, splashed in the water, and warmed our hands by the plasma fire. We have counted the atoms we can see. But the universe has a secret. Imagine walking into a dark room. You cannot see anything, but you can feel a presence. You can feel the floor dipping under the weight of someone or something standing next to you. You reach out your hand, but you touch only air. This is the mystery of dark matter. When astronomers look at the galaxies spinning in the deep black, they see something impossible. The galaxies are spinning too fast. By all the laws of physics, the stars should be flung out into the void like water from a spinning bicycle wheel. There isn't enough visible matter. There aren't enough stars or gas clouds to hold them together. Gravity should be too weak. And yet, the galaxies hold. They spin with a majestic, heavy grace. Something is holding them, something invisible, something massive. We call it dark matter, but a better name might be the invisible scaffolding. It is everywhere. It passes through the earth, through your house, through your body right now as you listen to this. Millions of dark particles streaming through you every second. They do not interact with light. They do not interact with atoms. They are the ghosts of the physical world. They interact only with gravity. They are the heavy, silent hand that cradles the galaxy, keeping the stars from drifting away. There is a strange comfort in this. It means that what we see, the bright, flashy, noisy world of light, is not all there is. We are supported by the unseen. We are held together by a mystery that refuses to show its face. But if dark matter is the ghost, then strange matter is the monster. But a beautiful monster. Drift with me to the heart of a dying star. A neutron star. Here, gravity is so strong that atoms are crushed. The electrons are smashed into the protons, turning them into neutrons. The star becomes a city-sized atomic nucleus, denser than anything in the universe. But what happens if you squeeze even harder? Deep in the core, the pressure might become so intense that the neutrons themselves break. They dissolve into a soup of their ingredients, quarks. Up quarks, down quarks, and strange quarks. This is strange matter. It is a theoretical phase of matter that is perfectly, terrifyingly stable. In fact, it might be the most stable substance in the universe. It is matter that has found its ultimate resting place. Some physicists speculate about strangelets, tiny droplets of this matter drifting through the cosmos. If a strangelet were to touch ordinary matter, its stability is so contagious that it would instantly convert the ordinary matter into more strange matter. It is the Midas touch of physics. A rock so perfect that everything it touches wants to become it. But do not fear. Space is vast, and strangelets are rare if they exist at all. Instead, let the concept lull you. Imagine a stability that cannot be broken. A calm so deep that it absorbs everything into itself. You can find that stability in your own mind. You can create a core of silence so heavy, so dense that the noise of the world simply melts when it touches it. We have journeyed from the mundane to the magical, from the ice cube to the invisible ocean. But there is one final phase we must explore.
It is not a phase of matter exactly. It is a phase of you. Because none of this exists without a witness. The ice does not crack without a listener. The star does not shine without an eye to catch the light. The quantum wave does not collapse without an observer. We are going to turn the camera around. We are going to look at the one thing that changes everything. We are going to look at the observer. There is a famous riddle. If a tree falls in the forest and no one is around to hear it, does it make a sound? In the classical world, we might say yes. The air vibrates, the sound waves travel, the physics happens whether we are there or not. But in the quantum world, the answer is not so simple. We have spoken of phases, solid, liquid, gas. We define them by how they look, how they act. But quantum mechanics teaches us that looking is an active verb. The observer effect. When you measure a quantum system, you change it. Before you look, an electron might be in many places at once, a cloud of probability. But the moment you look, the moment you ask, "Where are you?" it snaps into position. It freezes. Your attention creates reality. There is a phenomenon called the quantum Zeno effect. If you watch an unstable atom continuously, if you never take your eyes off it, it will never decay. It will never change. Your observation pins it in place, like a butterfly on a board. Think about that. The gaze of the observer can stop time. It can hold matter still. Now turn that gaze inward. You are the observer of your own body. You are the watcher of your own mind. All day long, you have been observing the world, watching screens, watching traffic, watching faces. Your attention has been scattered, pinning down 1,000 different realities. But now, close your eyes. Stop observing the outside world. Let the room dissolve. Let the furniture lose its shape. Let the walls fade. Turn your attention to the darkness behind your eyelids. What phase of matter are you now? You are not solid. You are not rigid. You are not liquid. You are not flowing anywhere. You are entering the dark phase, the phase of potential. By withdrawing your attention from the world, you allow the world to soften again. You allow the wave functions of your life to spread out again. You stop forcing reality to be sharp and defined. You let it become blurry. You let it become a dream. This is the final transition, the shift from being awake to being asleep. It is a phase transition, just like melting or freezing. It is a change of state. Your brain waves slow down. Your temperature drops. Your muscles lose their tension. Your consciousness disconnects from the sensory world and drifts inward. You are becoming a universe of one. There is no more science to learn tonight. There are no more facts to memorize. The laboratory is closing. The lights are dimming. The experiments are over. It is time to simply exist. Chapter 15. The Final Drift. Look back one last time at the path we have walked. See the solids, the crystals, and the glass.
resting in their stillness. We leave them to their long, slow wait. Sleep well, stones. See the liquids, the rivers and the oceans flowing endlessly to the sea. We leave them to their journey. Flow on, waters. See the gases, the clouds and the breath expanding into the sky. We let them go. Drift away, clouds. See the plasmas, the stars and the lightning burning with ancient fire. We leave them to their light. Shine on, stars. See the strange and the dark, the ghosts and the shadows. We leave them to their mystery. Be at peace, shadows. And now, see yourself. You are the sum of all of this. You have the bones of the solid, the blood of the liquid, the breath of the gas, the spark of the plasma, and the mystery of the dark. You are a universe wrapped in skin, lying in a bed, drifting through space. Everything is slowing down. The atoms in your hands are heavy. The atoms in your legs are heavy. The atoms in your eyelids are heavy. There is no more friction. You are a superfluid of sleep. There is no more time. You are a crystal of eternity. There is no more separation. You are a condensate of peace. Let go of the shape of you. Let go of the name you carry. Let go of the day that has passed. Let go of the tomorrow that has not yet come. There is only this, the dark, the warm, the quiet. Drift, float, sink. The experiment is a success. The data is collected. The results are clear. You are safe. You are tired. You are ready. Good night to the atoms. Good night to the stars. Good night to you. Sleep well. Hello, and welcome to the Midnight Scientists. Before we begin our journey tonight, I invite you to settle into the space around you. Adjust your posture. Let your shoulders drop away from your ears. If you are in a city apartment, listen for a moment to the distant, muffled hum of the world outside, the low frequency of life continuing elsewhere. If you are in a quiet village, notice the profound weight of the silence, the way it seems to press gently against the windows. Imagine for a moment the thousands of kilometers that might separate you from the next person hearing these words. Somewhere, across an ocean or a continent, another mind is drifting just as yours is. There is a vastness between you, a distance made of mountains, rivers, and the curvature of the earth itself. And yet, in this moment, you are sharing a structure. You are held together by the same sequence of thoughts, the same rhythm of breath. Tonight, we are going to explore the edges of that connection. We are going to look at the very fabric of distance and ask if it is as solid as it seems. Visualize, if you will, a void. Not a frightening void, but a calm, velvet black expanse. It is a place of absolute stillness, far removed from the clutter of the everyday world. In the center of this stillness, two tiny points of light appear. They are born from a single event, perhaps a high-energy photon striking a crystal or a delicate atomic bouquet. These are our particles. They are twins, born of the same mathematical womb. In the language of the laboratory, they are a system. But for us tonight, they are simply two travelers. As they emerge into the world, they begin to drift apart. Imagine them moving slowly, with a grace that only the microscopic world possesses. One moves to the left, towards the distant horizon of your mind. The other moves to the right. They do not look back. There are no tethers between them, no invisible silver threads, no radio waves, no whispers. They are, to all classical appearances, entirely separate entities. 1 kilometer passes, then 10, then 1,000. Now imagine an observer, Let us call her Alice. She sits in a quiet laboratory watching the traveler that moved to the left. She decides to ask it a question. In the quantum world, asking a question is called a measurement. She wants to know which way the particle is spinning. In her mind, she expects the particle to have its own identity, its own real state. She assumes that whatever the particle is doing, it is doing it independently of its twin, which is now thousands of miles away. But as Alice performs her measurement, something happens that defies every intuition we have about the world. The moment she finds her particle is spinning up, its twin, vastly distant and untouched, instantly assumes the opposite state. It spins down. There is no delay. There is no time for a signal to race across the gap. If Alice had a friend, Bob, watching the second particle on the other side of the planet, he would see the result the very microsecond she made her choice. Imagine the implications of this. It is as if two coins, flipped in different cities, always landed on opposite sides, even though nothing linked them. It is as if two hearts, separated by a lifetime of distance, beat in a perfect, synchronized counterpoint. This is the phenomenon that Erwin Schrödinger, in the quiet of the 1930s, gave a name that would haunt physics forever. He called it Verschränkung. In English, we know it as entanglement. Schrödinger did not see this as a mere detail. He believed it was the characteristic trait of quantum mechanics, the thing that forced us to say goodbye to the world of separate, lonely objects. Visualize the great Albert Einstein, a man who loved the order of the cosmos, sitting in his study. He is troubled. He looks at the mathematics and sees this immediate connection across space. He calls it spukhafte Fernwirkung, spooky action at a distance. To Einstein, the world was a collection of separate parts. A chair is a chair, a moon is a moon. Each has its own properties, influenced only by what touches it. This is the principle of locality. It is the comfort of knowing that what happens there cannot change what is happening here unless something, a light beam, a force, a physical push, travels the distance between them. But the travelers we are watching tonight do not seem to care for Einstein's comfort. They suggest a universe that is more like a single, seamless tapestry. If you pull a thread on one side, the pattern shifts on the other, regardless of how wide the tapestry may be. Drift with me now away from the laboratory and back into the history of how we came to think this way. Before we can understand the spookiness of entanglement, we must understand the world we thought we lived in. The world of Isaac Newton, of solid cannonballs and predictable planets, a world where everything was in its place and every place was its own. In that world, distance was a wall. In the quantum world, distance might just be an illusion. As we move forward, we will ask, if nothing travels between the particles, how do they know? Is there a secret code written in their hearts? Or is the space between them not really space at all? Consider this as you drift. If two things are created together, can they ever truly be apart?
As you continue to drift, let the velvet blackness of the quantum void fade for a moment. Instead, I invite you to visualize a grand, ancient library. The air here is cool and carries the faint, comforting scent of old paper and polished oak. Outside the tall, arched windows, the stars move in slow, majestic circles, precisely where the charts say they should be. This is the home of classical physics. For centuries, this was the architecture of the human mind. It was a world of separability, a beautiful and orderly island where every object had its own name, its own place, and its own life, entirely independent of the things around it. Imagine a single silver coin resting on a mahogany table. It has a weight you can feel, a diameter you can measure, and a position you can define with absolute certainty. If you were to take another coin and place it in a drawer in the next room, common sense tells you that the two coins have nothing to do with one another. What happens to the coin on the table, a scratch, a polish, a flip, cannot possibly change the coin in the drawer. They are separate systems. They possess what Einstein called their own real states. This was the great promise of Isaac Newton. Visualize Newton in the late 17th century, watching the world with a quiet, mathematical intensity. To him, the universe was a vast, intricate clockwork. Planets orbited the sun not because of mysterious telepathic bonds, but because of forces that could be calculated with the precision of a master watchmaker. In Newton's world, if a cannonball curved through the air, it was because of the push of gunpowder and the pull of the earth. If the moon stayed in its path, it was because gravity reached across the distance. But even gravity, as vast as it was, respected the individuality of things. The earth remained the earth, the sun remained the sun. They were separate bodies, interacting through forces, but never losing themselves in one another. This separability is the bedrock of our intuition. It is the reason you feel safe, knowing that your house stays where you left it, even when you are miles away. It is the reason we believe that the moon exists even when no one is looking at it. It is the philosophy of the sum of parts, the belief that if you understand every individual piece of a machine, you understand the whole machine. There are no ghosts in the gears, no hidden connections that defy the boundaries of space and time. But as the centuries turned, the library of classical reason grew even more sophisticated. Drift forward now to the 19th century. Imagine the world beginning to hum with a new kind of energy. You see James Clerk Maxwell standing amidst a forest of copper wires and magnetic coils. He is uncovering the secret language of light itself. Maxwell showed us that the space between things is not empty. It is filled with fields, invisible, continuous oceans of electricity and magnetism. When you move a magnet, you create a ripple in this field. That ripple travels outward like a wave on a pond until it touches something else. This was the birth of true locality. It meant that for one thing to affect another, a signal had to travel. Information had to move through the field, crossing the centimeters or the light years at a finite pace. And then, in 1905, Albert Einstein added the final heavy lock to the door of this classical world. Visualize a beam of light racing across the dark. Einstein realized that this beam is the fastest messenger in the universe. It moves at approximately 300,000 kilometers every second. To our human minds, this is instantaneous, but to the universe, it is a strict speed limit. Imagine two events occurring at opposite ends of a galaxy. If light cannot travel between them in time, Einstein told us then those two events can have no causal link. They are space-like separated. They are truly, fundamentally alone. This is the heart of relativity. The geometry of space and time ensures that the here and the now are protected from the there and the then by the absolute barrier of light's velocity. In this world, everything is tidy, everything is local, everything is separate. It is a comfortable way to live. It aligns with the way we touch the world, the way we build our cities, and the way we understand our own bodies. We are islands of matter, interacting through the messengers of light and force, but always anchored in our own coordinates. But as we sit in this grand library of classical reason, notice a small tremor in the floorboards. A tiny, microscopic crack is beginning to form in the foundation. For all its beauty, this classical world began to fail when we looked too closely at the very small. We found that nature, at its deepest level, does not speak the language of billiard balls and clockwork. It speaks the language of waves that cannot be unpicked, of states that refuse to be divided. The island of reason is about to be flooded by a stranger, deeper ocean. We are moving toward a place where the sum of the parts is no longer enough, where two travelers can drift light years apart and yet remain, in a way that haunts our logic, the same thing. Before we leave this library, consider the comfort of the wall and the distance. Enjoy the certainty of the here and the there, because in the next chapter, we are going to watch the walls dissolve. We are going to ask what happens to our reality when the speed limit of light is respected, but the particles don't seem to need a signal at all.
Close your eyes for a moment and return to that grand library of reason we visited before. Feel the weight of the oak tables and the stillness of the air. Everything here is accounted for. Everything has its place. But now, I want you to notice a small, persistent flickering at the edge of your vision. Imagine a small piece of iron resting in a dark furnace. As the furnace heats, the iron begins to glow. First, a dull, deep red, then a vibrant orange, finally, a brilliant, blinding white. To the scientists in the library at the end of the 19th century, this glow was a problem, a small, nagging wrinkle in their perfect tapestry. According to the old laws, the energy pouring out of that hot iron should have grown infinitely stronger as the frequency increased. It should have drifted into the ultraviolet, releasing a torrent of energy that nature simply didn't provide. They called it the ultraviolet catastrophe. It was a sign that the clockwork universe was starting to stutter. In the year 1000, a man named Max Planck stepped toward the furnace. Imagine him, a quiet, meticulous thinker, staring into the heat. To solve the riddle, he proposed something that he initially thought was merely a mathematical trick, a clever way to make the numbers behave. He suggested that energy does not flow like a continuous, smooth river. Instead, it moves in tiny, indivisible packets. He called them quanta. Visualize a staircase. In the classical world, you could stand anywhere on a ramp at any height you chose. But Planck's world was a set of stairs. You could stand on the first step or the second, but never in the empty space between them. Nature, it seemed, was granular. It had a minimum size. He discovered a number,
a proportionality constant we now call Planck's constant, denoted by the letter h. It is a number so small that it escapes our daily senses, roughly 6.6 times 10 to the minus 34 joule seconds. Imagine a decimal point followed by 33 zeros before you reach a digit. It is the heartbeat of the microscopic world. Because it is so small, the stairs of our daily life look like a smooth ramp. We don't feel the grains of energy when we turn on a lamp or feel the sun on our skin. But at the foundation of reality, the river had turned into a spray of droplets. Drift with me now into the 1920s. The library is changing. The walls are becoming translucent, and the books are no longer filled with certainties, but with probabilities. Imagine you are standing in a room made of pure light. This is the abstract space the mathematicians call Hilbert space. It is not a place you can walk through with your feet, but a place you can explore with your mind. In this space, a particle is no longer a tiny billiard ball with a definite location. Instead, it is a state vector, a shimmering arrow pointing through a forest of possibilities. Think of a wave traveling across a vast dark ocean. This is the wave function, the mathematical soul of the quantum world. Before Alice or Bob, our observers, look at a particle, the particle does not have a position. It is the wave. It exists in a state of superposition. Visualize a coin spinning on a table so fast that it is a blur. While it spins, it is neither heads nor tails. It is a ghost of both, a shimmering blend of possibilities. This is not because we are ignorant of the result. It is because in the quantum world, the blur is the reality. In this room of light, the great Heisenberg and Schrödinger are at work. Heisenberg gives us the uncertainty principle. He tells us that the more we know about where a particle is, the less we can know about where it is going. It is as if the universe has a built-in privacy policy. You can see the texture of the fabric, or you can see the speed of the loom, but never both at once. Schrödinger, meanwhile, gives us the equation for the wave itself. He describes how these clouds of probability move and grow. But then something even stranger emerges. Imagine two of these spinning coins, these blurs of possibility, brought close together. As they spin, they begin to influence one another. Their waves overlap. Their probability clouds touch and merge. According to the new rules of Hilbert space, when two systems interact, they no longer have their own separate wave functions. They join together. They become a single composite wave, a single arrow in a much larger, more complex room. This is the birth of the non-factorizable state. Think of two drops of ink falling into a glass of water. At first, they are separate points of color, but as they swirl, they entangle. You can no longer describe the first drop without describing the second. They have lost their individuality to the relationship. The island of reason is left far behind. We are now sailing on an ocean where relations are more fundamental than things, where the here and the there are beginning to lose their meaning. Consider this as you drift deeper. If the universe is built from waves that can overlap and merge, then where does one object truly end and another begin? In the next chapter, we will follow Einstein as he realizes the consequences of this merging. We will watch him struggle with a reality that suggests two things can be light years apart and yet remain a single, indivisible wave. We will look into the spooky heart of the mystery.
As you settle deeper into your rest, imagine the scene shifting once more. The translucent walls of the quantum room fade, replaced by the quiet wood-paneled study of a house in Princeton, New Jersey. The year is 1935. Outside, a gentle rain might be falling, pattering against the glass, but inside, the air is thick with the scent of pipe tobacco and the heavy silence of profound thought. Visualize a man sitting at a desk littered with papers. He has a wild mane of white hair and eyes that seem to see far beyond the walls of the room. This is Albert Einstein. He is a man who believes in a universe of geometry, order, and logic. To him, the moon is there even when he isn't looking at it. Things are real. Things are separate. Things are local. But he has seen the mathematics of the wave function, and it troubles him deeply. He sees that if quantum mechanics is the final word, then two particles, our travelers, can remain a single entity no matter how far they drift. Einstein decides to challenge this. Along with two colleagues, Boris Podolsky and Nathan Rosen, he crafts a paper that will become one of the most famous in the history of science. It is known as the EPR paper. Drift with Einstein for a moment as he builds his argument. He starts with a simple, almost poetic premise, the criterion of reality. Imagine you are walking through a forest. You see a leaf fall. You don't need to touch the leaf to know it is falling. You can predict its path. Einstein argued that if we can predict the value of a physical quantity with certainty without disturbing the system in any way, then there must be an element of reality corresponding to that quantity. In simpler terms, he believed that things have properties like position or spin, regardless of whether we choose to measure them. He believed the universe doesn't wait for us to ask a question before it decides what the answer is. Now, recall our two entangled travelers. Einstein imagined them moving light years apart. He realized that according to quantum theory, if Alice measures her particle and finds it is spinning up, Bob's particle, far away, must immediately be spinning down. Because Alice could choose to measure her particle at any moment, and Bob's particle would instantly respond, Einstein argued that Bob's particle must have already possessed that spin all along. If Bob's particle changed its state instantly without any signal traveling from Alice, it would violate the speed limit of light. It would be what he called spukhafte Fernwirkung, spooky action at a distance. Visualize Einstein pacing his study, shaking his head. To him, this was a sign that quantum mechanics was incomplete. He believed there must be a secret code. Imagine each particle carrying a hidden set of instructions, a tiny invisible manual written at the moment of their birth. When they were created together, the manual told them, if they ask you,
You be up and you be down. In this view, the connection is not spooky at all. It is just a shared history, like two identical clocks set together and then moved to different rooms. They tick in unison, not because they are talking to each other across the walls, but because they were synchronized at the start. These are what we call hidden variables. Einstein wanted a universe where things were separate and local. He wanted to believe that Bob's particle had its own real state that Alice could not reach with her measurement. He wanted a world where the tapestry was made of individual threads, not a single indivisible sheet. But on the other side of the Atlantic, in Copenhagen, Niels Bohr was listening. Bohr did not agree. Imagine Bohr as a man comfortable with ambiguity, a man who believed that we cannot speak of a particle's properties until we have performed the measurement. To Bohr, the measurement context was everything. You cannot separate the leaf from the act of looking at it. The two giants of physics were locked in a quiet, profound battle of the mind. Einstein insisted that the world was made of separate, objective parts. Bohr insisted that the world was a holistic, relational whole, where separability was a dream we had to wake up from. For Einstein, entanglement was a flaw in the theory, a ghost in the machine, that proved we needed a better, more real explanation. But for the quantum world, entanglement was not a flaw. It was the truth. As you drift now, imagine the tension between these two ideas. On one hand, the comfort of the secret code, the hidden manual that keeps everything local and safe. On the other hand, the vast, shimmering mystery of a universe where distance is not a barrier, and two things can remain one across the span of the stars. Einstein's spookiness was meant as a criticism, but as the decades passed, the spookiness refused to go away. Consider this. Is it more comforting to believe we are all separate islands with secret codes, or to believe we are all part of the same unbroken wave? In the next chapter, we will leave the quiet study of Einstein and move into the 1960s to a man named John Bell, who found a way to take this philosophical argument and turn it into a mathematical test. We will find out if the universe really does have a secret code, or if it is even stranger than Einstein could have imagined.
As the rain in Princeton fades from your mind, imagine the world beginning to turn faster. The wood-paneled study dissolves, replaced by the humming, high-energy atmosphere of the 1960s. We find ourselves in Switzerland, at the edge of the Alps, where the European Organization for Nuclear Research, CERN, is coming to life. But we are not standing in the middle of a massive particle accelerator. Instead, imagine a quiet office, tucked away from the noise of the machinery. There is a man here named John Bell. Visualize John Bell as a quantum rebel. He is a physicist who spent his days working on the practical, heavy machinery of the subatomic world, but his nights were spent staring into the same dark mystery that haunted Einstein. He was a man of quiet, sharp intensity, with a mind that refused to accept that the debate between Einstein and Bohr was just a matter of opinion or philosophy. For nearly 30 years, the world had lived with the EPR paradox. Most physicists had simply moved on, using the math of quantum mechanics to build transistors and lasers, ignoring the spooky ghosts in the basement. They treated quantum theory like a black box. It worked, so why worry about what was happening inside? But Bell could not look away. He wanted to know if Einstein's secret code, those hidden variables, actually existed. He wanted to know if the universe was truly made of separate, independent parts, or if it was bound together in a way we couldn't yet see. Drift with Bell now as he performs a miracle of thought. Imagine him sitting with a pencil and paper, setting a trap for the universe. He realized that if Einstein was right, if every particle carried a hidden manual that told it how to behave, then there were certain mathematical limits to how connected two distant things could appear to be. Visualize a game of chance. Imagine Alice and Bob are in different rooms, and they are each given a pair of dice that were once rolled together. If the dice have a secret connection, a hidden instruction that says, "always match," their results will be correlated. But Bell realized that there is a statistical ceiling, a maximum amount of correlation that is possible if the dice are separate local objects. He called this ceiling an inequality. It was a simple, elegant limit. In your mind, imagine a high wall. On one side of the wall is the classical world, the world of local realism, where things have their own properties and signals can't exceed the speed of light. On the other side is the quantum world. Bell calculated that if Einstein's secret code was real, the particles between Alice and Bob could never jump over that wall. They would always stay below a certain number. But then he looked at the equations of quantum mechanics, the very equations Einstein had doubted. To his astonishment, the math predicted that under the right conditions, the particles would ignore the wall entirely. They would be more correlated than any local separate system could ever be. This was the oracle. For the first time, the mystery was no longer a matter of interpretation. It was a matter of measurement. Bell had shown that we could actually ask the universe, "Do you have a secret code, or are you truly spooky?" Imagine the weight of that realization. If we could perform this experiment, we wouldn't just be testing a theory, we would be testing the very definition of reality. We would find out if the island of reason was truly an island, or if everything was secretly connected by an underwater landscape we had never mapped. Bell published his findings in 1964 in a small journal that few people read at the time. He wasn't sure if anyone would ever be able to build the experiment. The technology required to create and measure single pairs of entangled photons across large distances didn't exist yet. His paper sat like a dormant seed, waiting for the world to catch up. As you drift, visualize Bell's inequality as a lonely lighthouse on a dark coast. It doesn't tell us how the connection works, but it tells us where the boundaries of the old world end. It tells us that either the universe is non-local, meaning things are connected across space instantly, or that things don't have definite properties until they are looked at. Think of the patience required to hold such a thought. For years, Bell's work was a quiet whisper in the background of a busy world, but the seeds were beginning to stir. In the next chapter, we will leave the quiet halls of CERN and enter the laboratories of the 1970s and 80s. We will watch as a new generation of scientists, the experimentalists, take Bell's lighthouse and use it to search the dark. We will witness the first time the universe was asked the question and the startling, unmistakable answer it gave back. We will watch as the wall Einstein built is finally gently crossed. Imagine the abstract geometry of Bell's lighthouse beginning to solidify into something real. The high intellectual peaks of the Swiss Alps dissolve, and we find ourselves descending into a much humbler space. We are in a basement at the Institut d'Optique in Orsay, just south of Paris. The year is 1982. The air here is different. It is cool and slightly damp, carrying the faint metallic scent of electronics and the sharp, clean ozone of high-voltage equipment. The room is dim, lit only by the soft green and red glows of instrument panels. In the center of the room, stretching across a heavy, vibration-proof table, is a forest of mirrors, lenses, and crystals. This is the world of Alain Aspect. Visualize Aspect as a man of immense patience. While the rest of the world was busy with the loud, visible progress of the late 20th century, he and his team were engaged in a quiet, delicate hunt. They were trying to catch a ghost. They were trying to perform the experiment that John Bell had dreamed of 2 decades earlier. At one end of the table, imagine a source, a small chamber where calcium atoms are being coaxed into a specific state. When these atoms decay, they emit 2 photons at once. These are our travelers, our entangled twins. Drift with these photons now. They are not like the billiard balls of Newton's world. They are tiny, indivisible pulses of light, shimmering with a shared secret. They race away from the source in opposite directions, moving at the absolute speed limit of the universe. As they fly, they head toward 2 polarizers. Think of these as gates that only allow light to pass if its vibration is aligned in a certain way. Now, recall Einstein's fear. He believed that the only way these photons could coordinate their behavior is if they shared a secret code from the start. But Aspect had a plan to close the door on that explanation. Imagine the polarizers shifting. While the photons are already in flight, racing at 300,000 kilometers per second, the orientation of the gates is changed. This happens so fast that no signal moving at the speed of light could possibly travel from one gate to the other to tell it what to do. If the universe was local and separate, as Einstein hoped, then Alice's measurement could not possibly affect Bob's. They would be isolated islands. They would obey Bell's inequality. They would stay below the wall. But as the detectors began to click, the rhythm told a different story. Visualize the data points appearing on a glowing screen, one by one. The correlations were too strong. The photons were matching their states with a precision that defied the boundaries of space. They were jumping over Bell's wall. They were ignoring the lighthouse and sailing into the spooky dark. Aspect and his team had done it. They had asked the universe the ultimate question, and the universe had answered with a resounding, undeniable yes. Quantum entanglement was not a mathematical glitch, it was a physical reality. Imagine the quiet in that Paris basement when the results were finalized. The island of reason had not just been flooded, it had been revealed as part of a much larger, stranger geography. The particles were light years apart in potential, yet they acted as if they were still sitting in the same palm. This result didn't just change a few equations,
It shifted the ground beneath our feet. It meant that the here and the there were not the absolute categories we thought they were. It meant that distance, for all its practical importance, was not a fundamental barrier to connection. As you drift with the memory of those clicking detectors, consider what this means for the vacuum of space. If two photons can remain one even as they race toward the edges of the galaxy, then the emptiness between them is not really empty. It is filled with a structure we are only just beginning to name. In this moment, as you rest, realize that the very atoms in your body once interacted with the atoms in the stars. According to the rules of the Paris basement, you are not a separate island. You are part of a shared cosmic state. In the next chapter, we will explore the no signaling rule. We will ask, if this connection is real and immediate, why can't we use it to talk to the stars? Why does the universe give us this deep connection, yet keep its secrets so carefully guarded? We will look at the bridge that quantum mechanics built between its own spookiness and the ironclad laws of Einstein's light.
Take a deep breath and let the image of the Paris basement fade. The clicking of the detectors, the hum of the cooling systems, the sharp scent of ozone. Let them all dissolve into the quiet of the night. We find ourselves now in a place of pure abstraction, a space where the logic of the universe reveals its most careful boundaries. Imagine two travelers, Alice and Bob, standing on opposite sides of a vast, tranquil ocean. They are separated by thousands of kilometers of dark, surging water. Each holds a small, glowing lantern. In the world we have just discovered, the world of Elaine Aspect and John Bell, we know that these lanterns are entangled. When Alice shutters her lantern to reveal a green light, Bob's lantern far across the horizon instantly glows red. There is no delay. There is no crossing of the waves. The connection is immediate, defying every wall of space and every tick of the clock. Naturally, you might ask, if the connection is instant, why can't Alice use her lantern to send a message to Bob? A warning, a greeting, a secret, faster than the speed of light. This is where the universe reveals a breathtaking piece of cosmic architecture. It is called the no signaling theorem. Visualize Alice in her lonely station. She wants to tell Bob yes. She decides that if she measures her particle and finds it spinning up, it will mean yes. If she finds it spinning down, it will mean no. She reaches out to her particle with hope. But here is the catch, the quiet iron rule of the quantum world. Alice has no control over what she finds. When she performs her measurement, the result is truly, fundamentally random. It is like flipping a coin that has no memory and no weight. One moment it is up, the next moment it is down. She cannot force the particle to be up to send her message. She is a witness to the result, not its master. Drift with this thought for a moment. Alice looks at her particle and sees up. Across the ocean, Bob's particle instantly becomes down. The connection has happened. The universe has kept its promise.
But Bob, looking at his own lantern, sees only a down. To him, this result looks just as random as any other. He has no way of knowing if Alice has even performed her measurement yet. He sees a sequence of ups and downs that look like static on a television screen, white noise in the dark. It is only when Alice and Bob eventually meet, traveling by boat or by radio, moving at the slow sublight speeds of the classical world, that they can compare their notes. Only then, when they lay their lists beside each other, do the patterns emerge. Only then do they see that every time Alice had an up, Bob had a down. The connection is real, but it is a silent one. It is a correlation, not a conversation. Imagine the universe as a grand librarian who allows you to look at two copies of the same book at opposite ends of the library. You see that they are identical, page for page, word for word, but you are forbidden from writing in the margins. You can see the shared structure, but you cannot use it to change the story elsewhere. Why would the universe work this way? Visualize Albert Einstein's light beams once more. If we could send a message faster than light, the very structure of time would begin to unravel. In some frames of reference, the message would arrive before it was sent. Cause would follow effect. The past would be at the mercy of the future. The no signaling rule is the bridge that quantum mechanics builds to keep Einstein's world safe. It allows the spookiness of entanglement to exist, but it places a veil over it. It ensures that while the foundations of reality are deeply, instantly connected, the information we use to build our lives must still respect the slow, majestic pace of the speed of light. It is a form of cosmic censorship. The universe allows itself to be whole, but it requires us to be local. As you drift now, consider the beauty of this balance. We live in a world where everything is quietly, profoundly linked at the root, and yet we are granted the individuality of our own here and now. We are connected, but we are not overwhelmed. We are part of a single wave, but we are allowed to be our own droplets. Imagine the information in the universe as a hidden melody. Entanglement is the rhythm that holds the song together, even if the instruments are on different stages. But to hear the melody, you still have to wait for the sound to travel through the air. In this silence, there is a profound peace. The connection is there, whether we can use it or not. It is a feature of the architecture, a silent messenger that tells us we are never truly alone, even if the stars are too far to reach in a single breath. In the next chapter, we will move from the no signaling rule into the world of contextuality. We will ask, if properties don't exist until we look at them, what does that say about the reality of the things we touch? Is the moon only there when we look at it? Or is the universe asking us a different kind of question?
Imagine the vast, tranquil ocean of the last chapter slowly beginning to mist over. The horizons of Alice and Bob's world dissolve into a soft white haze, and as you drift through this mist, you find yourself standing in the middle of a garden at dusk. The air is cool and still, smelling of damp earth and night-blooming jasmine. In the center of this garden sits a single ornate wooden box. In our everyday classical life, we assume that this box has a real state. We believe that it has a weight, a color, and a certain number of secret items inside it, regardless of whether we are there to open it or not. This is what philosophers call non-contextual realism. It is the simple, honest belief that a chair is a chair, a coin is a coin, and the moon is the moon, even when the garden is empty and the world is asleep. But now, I want you to visualize something strange. Imagine you approach the box. You decide you want to measure its weight. You lift it, and it feels heavy, like it is filled with stones. But then imagine a friend approaches the box from the other side. They don't care about the weight, they want to measure its color. When they look at it, the box suddenly appears light as a feather to them, and its surface turns a brilliant, shimmering blue. If you were to ask the box both questions at once, its weight and its color, it might give you one set of answers. But if you were to ask about its weight and its scent instead, the answer for its weight might change entirely. The box does not have a fixed set of properties waiting in a manual. Instead, the properties emerge from the context of the question you choose to ask. This is the heart of contextuality, a mystery that goes even deeper than the spookiness of entanglement. In 1967, two thinkers named Simon Kochen and Ernst Specker sat down to challenge the very foundation of how we define a thing. They weren't looking at distant particles across an ocean, they were looking at a single particle right in front of them. Visualize them working at a chalkboard, their shadows long in the afternoon light. They asked, can we assign definite, secret values to every possible property of a quantum system such that those values don't care about the context of our measurement? Their answer was a quiet, mathematical no. They proved that in the quantum world, the result of a measurement depends on which other measurements you are performing at the same time. You cannot think of a particle as a little ball with a list of pre-written labels. The labels only appear when you ask for them, and they shift depending on what else you are curious about. Drift with this thought for a moment. It suggests that the universe is not a collection of static objects sitting on a shelf. It is more like a grand interactive dialogue. Think of a prism. When it sits in the dark, does it have a rainbow? We might say yes, but the rainbow only exists when the light strikes the glass at a specific angle. The rainbow is a relationship between the light, the glass, and the observer's eye. It is contextual. Einstein famously asked his friend Abraham Pais, "Do you really believe the moon is not there when you are not looking at it?" In the world of Kochen and Specker, the answer is a subtle, mesmerizing one. Perhaps the moon is there, but the way it is there, its precise position, its exact glow, its very moonness, is part of a shared state between the moon and the rest of the universe, including us. Imagine you are walking through a forest of shifting shadows. In the classical world, the trees stay trees and the shadows stay shadows. But in the contextual world, the tree might only become a tree when you reach out to touch the bark. This is not a lack of reality. It is a richer, more intricate kind of reality. It means that we are not just spectators watching a movie. We are participants. We are part of the context that gives the world its shape. Consider the peace in this realization. If the properties of the world are contextual, then the universe is never truly finished. It is constantly being defined and redefined by the relationships within it. Entanglement told us that things are connected across space. Contextuality tells us that things are connected across meaning. As you drift now, visualize your own life.
your thoughts, your memories, the very way you feel in this moment, are they not contextual? Do you not feel different in the light of the sun than you do in the quiet of the night? Are you not a different version of yourself depending on who is there to hear your voice? The quantum world is simply reflecting a truth we feel in our own hearts, that nothing exists in a vacuum. Everything is part of a context. Everything is defined by its neighbor. In the next chapter, we will leave the garden of shifting shadows and move into the cold, quiet mechanics of decoherence. We will ask, if the world is so shimmering and contextual, why does it look so solid? Why do the tables and chairs of our lives stay so stubbornly in place? We will look at how the environment, the very air around us, acts as a silent witness that forces the quantum world to behave like the classical one we know.
Imagine the garden of shifting shadows from the last chapter slowly beginning to settle. The mist that blurred the edges of the box and the trees is lifting, burned away by a cold, clear morning light. As you drift through this transition, you find yourself back in a place that feels familiar. You are sitting in a quiet room. Perhaps it is your own bedroom or a study filled with books. Notice the objects around you. A heavy stone paperweight on a desk, a glass of water, a clock ticking steadily on the wall. In this room, the world feels solid. The paperweight doesn't change its weight depending on who looks at it. The water doesn't shimmer between being a liquid and a ghost. The clock doesn't exist in a superposition of 3 o'clock and 4 o'clock. Here, the island of reason seems to have returned with a vengeance. But if everything is built from quantum particles, from the contextual blurs and entangled waves we have been studying, why don't we see the spookiness in our morning coffee? The answer lies in a beautiful, invisible process called decoherence. Visualize that paperweight on your desk. In a vacuum, perfectly isolated from the rest of the universe, it might be able to exist in a shimmering quantum state. But the paperweight is never truly alone. It is being bombarded. Every second, billions upon billions of air molecules are striking its surface. Countless photons of light are bouncing off it. Heat from the room is vibrating through its atoms. In the quantum world, every one of these tiny collisions is an interaction. And as we know, when two things interact, they become entangled. The paperweight is constantly, relentlessly entangling itself with the air, the light, and the floor. In the 1970s and 80s, thinkers like H. Dieter Z. and Wojciech Zurek realized that the environment is not just a background. It is a silent witness. Imagine you are trying to keep a secret in a crowded room. If you are alone, the secret is yours. But as soon as one person hears you, the secret is shared. If 1,000 people hear you, the secret is no longer a secret. It is public knowledge. Decoherence is the leaking of quantum secrets into the environment. When a single air molecule hits our quantum traveler, it carries away a tiny bit of information about where that particle is. When billions of molecules do it, the wave of the particle, that beautiful blur of possibilities, is scattered into the surroundings. The coherence, the togetherness of the quantum state is dissolved. Drift with this image, a drop of ink falling into a vast, rushing river. For a split second, the drop is a concentrated point of color, but the river immediately pulls it apart, stretching it, thinning it, until the ink is so spread out that you can no longer see it. The ink hasn't disappeared, it is just so entangled with the river that you can no longer pick it out. This is why we don't see superpositions in our daily lives. The environment measures everything,
all the time with such ferocity that the quantum blurs are forced to settle into definite states before we can even blink. Zurich called this quantum Darwinism. He suggested that the environment selects certain states to survive. These are the pointer states, the ones that are the most robust, the ones that can be copied thousands of times into the environment without falling apart. Position is a pointer state. This is why things have places in our world. Imagine the environment as a grand broadcasting system. Because so many photons are bouncing off the paperweight and carrying information to so many different places, everyone who looks at the desk agrees on where the paperweight is. The objectivity of our world is born from this redundant, overwhelming entanglement. The classical world is not a different world from the quantum one. It is simply the quantum world seen through the lens of a trillion witnesses. Consider the peace in this realization, the stability of your life, the floor that holds your weight, the air that fills your lungs is a gift from this silent witnessing. The universe is so deeply connected that it uses its own connectivity to create the illusion of separation. It is as if the universe is holding a billion mirrors up to itself at every moment, and in the glare of all those reflections, the shimmering ghosts of the quantum world find a place to rest. They become the solid, dependable things we touch and name. But as you drift deeper, realize that even though the spookiness is hidden, it is still there, beneath the surface. The entanglement hasn't vanished, it has just moved into the environment. We are all swimming in a sea of correlations that are simply too complex for us to see. The paperweight is still entangled with the air, and the air is entangled with the walls, and the walls are entangled with the earth. In the next chapter, we will look at what happens when we try to push back against this decoherence. We will move into the high-tech, ultra-cold world of quantum information. We will ask, if the environment is a witness we want to escape, how do we build a box quiet enough to hold a quantum secret? We will look at the birth of the qubit and the quest to build a computer that thinks in waves.
Take a long, slow breath and let the world of the silent witness drift into the background. Imagine the room you were sitting in, the ticking clock, the air molecules, the scattering photons, all beginning to slow down. The colors of the walls soften and fade into a pale, clinical white. You are moving now into a place of extreme, engineered silence. Visualize a laboratory deep in the heart of a modern research institute. This is not the basement of Orsay or the quiet study of Einstein. This is a cathedral of glass, steel, and high-tech isolation. In the center of the room stands a massive cylindrical structure made of polished stainless steel and gold. It looks like a grand inverted chandelier, shimmering with an intricate web of wires and coaxial cables. This is a dilution refrigerator, a vault designed to reach temperatures colder than the deepest reaches of outer space. As you drift closer, imagine the temperature falling. It drops past the freezing point of water, past the point where air itself turns into a liquid, and down toward the absolute floor of the universe, absolute zero. At this depth, nearly all thermal motion ceases. The chaotic bombardment of air molecules we discussed in the last chapter has been stilled. The witnesses have been banished.
In the very heart of this cold, quiet machine, resting on a small silicon chip, is our new traveler, the qubit. In the classical world of your laptop or your phone, information is a series of bits. A bit is like a light switch. It is either on or it is off. It is a 0 or it is a 1. It is a world of either or, a world where every question has a single definite answer. But a qubit, a quantum bit, is different. Imagine a sphere. Let us call it the Bloch sphere. Imagine a point at the very top of the sphere representing the number 0, and a point at the very bottom representing 1. In the classical world, you are restricted to those two poles. You are either at the top or the bottom. But the qubit is allowed to exist anywhere on the surface of that sphere. It can be a shimmering blend of both 0 and 1 at the same time. This is the state of superposition. Drift with this image. A qubit is like a musical note that is not just a C or a G, but a rich, resonant chord containing both C and G. It is a wave of information that hasn't yet been forced to choose a side. Now imagine bringing a second qubit into this ultra-cold vault. Through a delicate pulse of microwave energy, we bring them together. We perform a gate, a quantum handshake. In this moment, the two qubits become entangled. They are no longer two separate notes. They are a single, complex harmony. If you change the state of one, the other responds instantly, even here in the silence of the vault. But unlike the accidental entanglement of the natural world, this is engineered entanglement. This is a connection we have built with intention. Why go to such lengths? Why build these massive golden refrigerators just to hold a few shimmering waves? Because entanglement is a resource, a new kind of fuel for the human mind. Imagine a computer that doesn't just check one path at a time through a maze, but instead explores every possible path simultaneously. Because the qubits are entangled, the computer can feel the structure of a problem across all its parts at once. It can see patterns that a classical machine, limited to its zeros and ones, would take billions of years to uncover. But as you watch the shimmering qubits, notice how fragile they are. Even here, at the edge of absolute zero, the silence is not perfect. A single stray photon, a tiny grain of heat, can find its way into the vault. When it strikes the qubit, it measures it. It acts as a witness. And in that instant, the entanglement is broken. The chord collapses into a singular, lonely note. The blur on the Bloch sphere is forced to one of the poles. The secret has leaked. This is the constant battle of the quantum engineer, to keep the world away, to maintain the silence long enough for the qubits to finish their work. Consider the metaphor of a dream. While you sleep, your mind exists in a state of superposition. You can be in two places at once. You can be a different version of yourself. The logic of the either-or dissolves. But as soon as the alarm clock rings, as soon as the first light of morning touches your eyes, the dream is measured. It collapses into the singular reality of the waking day. Quantum computing is our attempt to build a machine that dreams. As you drift now in the absolute silence of the vault, visualize the potential held in these connections. We are no longer just observing the spookiness of nature. We are beginning to speak its language. We are using entanglement to encode secrets that can never be broken and to solve riddles that have haunted us for centuries. We have moved from the island of reason to the sanctuary of the cold, and in so doing, we have turned a philosophical mystery into a technological tool. But there is still one question that lingers in the frost. If we can use entanglement to process information, can we use it to move that information across the stars? In the next chapter, we will leave the laboratory and look at the extraordinary feat of quantum teleportation. We will ask, is it possible to move a state from one place to another without moving the thing itself? Can we use the spooky bridge to step across the void? We will look at how we send a quantum secret across the earth and eventually into the heavens.
Imagine for a moment that you are standing on the edge of a great salt-cracked desert. The sky above is a deep, bruised purple, and the stars are beginning to pierce through the twilight like cold diamonds. The air is perfectly still, so quiet that you can almost hear the soft tectonic shifting of the earth beneath your feet. In the classical world, the world of our daily lives, to move from one side of this desert to the other, you must cross the space between. You must take steps. You must endure the time it takes for your body to traverse the kilometers. Every atom of you must be physically carried from where you are to where you wish to be. This is the only way we have ever known to travel. But tonight, we're looking at a different kind of journey. We're looking at a way to arrive without ever having moved. This is the mystery of quantum teleportation. Visualize two observers again, our faithful guides, Alice and Bob. They are separated now by a distance so vast it defies the imagination. Alice is here on this desert floor. Bob is far away, perhaps on a station orbiting a distant moon. Before they parted, they shared a gift, a pair of entangled photons. One stays with Alice in her desert camp. The other is carried by Bob into the heavens. This is their bridge. It is a silent, invisible connection that spans the void, a shared mathematical state that ignores the thousands of miles between them. Now, imagine that Alice has a third particle. Let us call it the traveler. This traveler is special. It holds a delicate, unique quantum secret, a specific spin, a shimmering orientation on the Bloch sphere that has never existed in exactly this way before. Alice wants to send this secret to Bob, but as we know from the no-cloning theorem, she cannot simply make a copy of it. Nature is a jealous guardian of its originals. It forbids the duplication of a quantum soul. To move the secret, Alice must do something radical. Drift with me into the heart of Alice's laboratory. Visualize her bringing the traveler close to her half of the entangled bridge. She performs what scientists call a Bell state measurement. Imagine the traveler and the entangled particle touching. Their probability clouds merge. In that instant, they become deeply, inextricably entwined. But there is a heavy price for this connection. To measure them together, Alice must destroy the traveler's original identity. In the quantum world, the act of sending is an act of sacrifice. As Alice records her results, the original traveler, the one that sat in her hand, is shattered.
Its specific shimmer, its unique secret, vanishes from the desert floor. It is gone, dissolved into the static of the environment. But look across the void to Bob. The moment Alice performed her measurement, Bob's entangled particle, his half of the bridge, felt a tremor. Because it was linked to Alice's particle, it has been instantly transformed. It is not yet the traveler, but it has become a scrambled version of it. It is holding the secret, but it is holding it behind a locked door. Now, Alice picks up a classical phone. She sends a simple message to Bob, 2 bits of information moving at the slow, majestic speed of light. She tells him, "I have measured the state. Here is the key you need to unlock yours." Bob receives the message. He applies a specific transformation to his particle, a gentle nudge of a magnetic field, a soft pulse of light. And in that moment, a miracle occurs. His particle, which has been with him on the moon all along, suddenly assumes the exact identity of the traveler that was destroyed in Alice's desert floor. Every shimmer, every spin, every delicate nuance of the original is now present in Bob's hand. The state has traveled, but the matter has stayed behind. Visualize the profound nature of this leap. Nothing physical crossed the void. No atom of the traveler moved through the vacuum. Only the information, the very essence of what the traveler was, has been reconstructed on the other side of the stars. It is as if a grand architect sent the blueprints for a cathedral across the ocean, and the stones on the other side rearranged themselves to match the design perfectly, while the original cathedral crumbled into dust. In 1993, Charles Bennett and his colleagues first described this bridge in the language of mathematics. They showed us that while we cannot clone reality, we can relocate it. And this is not just a dream. Imagine a mountain peak in Tibet, 13,000 feet above the sea. In 2017, scientists fired a green laser beam from that peak towards a satellite named Mikas, orbiting 500 kilometers above the Earth. Using this bridge of light, they successfully teleported a quantum state from the ground into space. The traveler reached the heavens without ever leaving the mountain. As you drift now, consider the beauty of this reconstruction. It suggests that what we are, our identity, our secrets, our very essence, might not be tied to the specific atoms we are made of, but to the patterns of our connections. If we can move the pattern, have we moved the thing? In the silence of the night, realize that the universe is a place of constant, shimmering reconstruction. We are being